1. Introduction to Data Analysis 1.1 Overview of Data Analysis. Data analysis is a crucial process in understanding and making sense of the vast amount of information available to us. It involves the systematic examination, interpretation, and evaluation of data to uncover patterns, relationships, and insights that can inform decision-making and drive meaningful outcomes. Data analysis can be broadly categorized into two main approaches: quantitative analysis and qualitative analysis. 1.1.1 Quantitative analysis. Quantitative analysis is a methodical approach to data analysis that focuses on numerical data and mathematical models. It involves the collection and analysis of data that can be measured and expressed in numerical terms. This type of analysis is often used to uncover patterns, trends, and relationships within a dataset, as well as to make predictions and draw conclusions based on statistical evidence. In quantitative analysis, data is typically collected through structured surveys, experiments, or observations. The data is then organized, cleaned, and transformed into a format suitable for analysis. Various statistical techniques and mathematical models are applied to the data to identify patterns, calculate measures of central tendency and dispersion, and test hypotheses. One of the key advantages of quantitative analysis is its ability to provide precise and objective results. The use of statistical techniques allows researchers to quantify relationships and draw conclusions based on empirical evidence. This makes it particularly useful in fields such as economics, finance, market research, and social sciences, where numerical data is abundant and decision-making relies on accurate and reliable information. Some common techniques used in quantitative analysis include descriptive statistics. Descriptive statistics summarize and describe the main features of a dataset. Measures of central tendency, such as mean, median, and mode, provide information about the average or typical value of a variable. Measures of dispersion, such as standard deviation and variance, indicate the spread or variability of the data. Inferential statistics. Inferential statistics involve making inferences or generalizations about a population based on a sample. Hypothesis testing is a common inferential statistical technique used to test the significance of relationships or differences between variables. Confidence intervals provide a range of values within which a population parameter is likely to fall. Correlation and regression analysis. Correlation analysis examines the strength and direction of the relationship between two or more variables. Regression analysis is used to model and predict the relationship between a dependent variable and one or more independent variables. ANOVA and chi-square tests. ANOVA, analysis of variance, is used to compare means between two or more groups. Chi-square tests are used to determine if there is a significant association between categorical variables. Quantitative analysis is not without limitations. It relies heavily on numerical data and may overlook important qualitative aspects of a phenomenon. It also assumes that the data is representative of the population being studied and that the statistical models used are appropriate for the data. Additionally, quantitative analysis may not capture the complexity and richness of human experiences and behaviors, which are better explored through qualitative analysis. 1.1.2 Qualitative analysis. Qualitative analysis is an interpretive approach to data analysis that focuses on non-numerical data, such as text, images, audio, and video. It involves the exploration and understanding of the meanings, contexts, and perspectives embedded within the data. Qualitative analysis aims to uncover the underlying themes, patterns, and relationships that emerge from the data, providing a deeper understanding of the subject under investigation. Qualitative analysis is often used in fields such as anthropology, sociology, psychology, and market research, where the focus is on understanding human behavior, attitudes, and experiences. It is particularly useful when exploring complex social phenomena, cultural practices, and subjective experiences that cannot be easily quantified. The process of qualitative analysis begins with data collection through methods such as interviews, focus groups, observations, or document analysis. The data is then transcribed, coded, and categorized into themes or patterns. These themes are further analyzed and interpreted to generate insights and understand the underlying meanings and contexts. Some common techniques used in qualitative analysis include coding and categorizing. Coding involves assigning labels or categories to segments of data based on their content or meaning. This helps in organizing and structuring the data for further analysis. Categories can be predefined or emerge from the data itself. Thematic analysis. Thematic analysis involves identifying and analyzing recurring themes or patterns within the data. Themes are broader concepts or ideas that capture the essence of the data and provide insights into the research question. Content analysis. Content analysis is a systematic approach to analyzing textual or visual data. It involves identifying and categorizing specific elements, such as words, phrases, or images, to uncover patterns, trends, or meanings. Grounded theory. Grounded theory is an inductive approach to qualitative analysis that aims to develop theories or explanations based on the data itself. It involves constant comparison and iterative analysis to generate new insights and theories. Qualitative analysis offers several advantages. It allows researchers to explore complex phenomena in depth, capture the richness and diversity of human experiences, and generate new theories or explanations. It also provides flexibility in data collection and analysis, allowing for emergent themes and unexpected findings to be explored. However, qualitative analysis also has limitations. It is time-consuming and labor-intensive, requiring extensive data collection, transcription, and analysis. The interpretation of qualitative data is subjective and can vary between researchers. Generalizability of findings is also a concern, as qualitative analysis often focuses on specific contexts or individuals rather than large populations. In summary, both quantitative and qualitative analysis play important roles in data analysis. Quantitative analysis provides precise and objective results based on numerical data, while qualitative analysis offers a deeper understanding of complex phenomena through the exploration of non-numerical data. The choice between the two approaches depends on the research question, the nature of the data, and the desired outcomes. 1.2 Types of data. Data is the foundation of any analysis, and understanding the different types of data is crucial for conducting effective data analysis. In this section, we will explore the two main types of data, quantitative and qualitative data. 1.2.1 Quantitative data. Quantitative data refers to numerical information that can be measured and expressed using numbers. This type of data is often collected through structured methods such as surveys, experiments, or observations. Quantitative data can be further classified into two subtypes, discrete and continuous data. 1.2.1.1 Discrete data. Discrete data consists of whole numbers or values that can only take on specific, separate values. It represents information that can be counted or categorized into distinct groups. Examples of discrete data include the number of students in a class, the number of cars in a parking lot, or the number of books on a shelf. Discrete data is often represented using bar charts, histograms, or pie charts. 1.2.1.2 Continuous data. Continuous data, on the other hand, represents measurements that can take on any value within a specific range. It can be measured at any point along a continuum and is not restricted to specific values. Examples of continuous data include height, weight, temperature, or time. Continuous data is often represented using line graphs, scatter plots, or box plots. Quantitative data is particularly useful for conducting statistical analysis and making objective conclusions. It allows for mathematical calculations such as averages, percentages, and correlations. By analyzing quantitative data, researchers can identify patterns, trends, and relationships between variables. 1.2.2 Qualitative data. Qualitative data, also known as categorical or non-numerical data, provides descriptive information about characteristics, attributes, or qualities. Unlike quantitative data, qualitative data cannot be measured using numbers. It is collected through methods such as interviews, focus groups, observations, or document analysis. 1.2.2.1 Nominal data. Nominal data is the simplest form of qualitative data and represents categories or labels that cannot be ranked or ordered. Each category is distinct and unrelated to the others. Examples of nominal data include gender, male or female, marital status, single, married, divorced, or favorite color. Nominal data is often represented using bar charts or pie charts. 1.2.2.2 Ordinal data. Ordinal data, on the other hand, represents categories that can be ranked or ordered based on a specific criterion. The categories have a natural order or hierarchy. Examples of ordinal data include educational attainment, elementary, high school, bachelor's degree, master's degree, customer satisfaction ratings, very satisfied, satisfied, neutral, dissatisfied, very dissatisfied, or movie ratings, 1 star, 2 stars, 3 stars, 4 stars, 5 stars. Ordinal data can be represented using bar charts or stacked bar charts. Qualitative data provides rich and detailed insights into people's opinions, experiences, and behaviors. It allows researchers to explore complex phenomena, understand context, and capture nuances that quantitative data may not reveal. Qualitative data analysis involves techniques such as coding, categorizing, and thematic analysis to identify patterns, themes, and relationships within the data. 1.2.3 Combining quantitative and qualitative analysis. While quantitative and qualitative data analysis are often treated as separate approaches, they can also be combined to provide a more comprehensive understanding of a research question or problem. This approach, known as mixed methods research, involves collecting and analyzing both types of data concurrently or sequentially. By combining quantitative and qualitative data, researchers can gain a deeper understanding of the phenomenon under investigation. Quantitative data can provide statistical evidence and generalizability, while qualitative data can provide context, meaning, and in-depth insights. This integration of data types allows for a more holistic and nuanced analysis. In conclusion, understanding the different types of data is essential for conducting effective data analysis. Quantitative data provides numerical information that can be measured and analyzed using statistical techniques, while qualitative data offers descriptive insights into people's experiences and behaviors. By combining both types of data, researchers can gain a more comprehensive understanding of the research question at hand. 1.3 Quantitative analysis. Quantitative analysis is a fundamental aspect of data analysis that involves the use of mathematical and statistical techniques to analyze numerical data. It focuses on the measurement and interpretation of data in a quantitative manner, allowing researchers to draw objective conclusions and make informed decisions based on the results. 1.3.1 Key concepts in quantitative analysis. Before delving into the various techniques used in quantitative analysis, it is important to understand some key concepts that underpin this approach. Variables. In quantitative analysis, variables are the characteristics or attributes that are being measured or observed. These variables can be classified into two types: independent variables and dependent variables. Independent variables are the factors that are manipulated or controlled by the researcher, while dependent variables are the outcomes or responses that are influenced by the independent variables. Data types. Quantitative analysis deals primarily with numerical data. There are two main types of numerical data: discrete and continuous. Discrete data consists of whole numbers or counts, such as the number of students in a class or the number of cars sold in a month. Continuous data, on the other hand, can take any value within a range, such as height, weight, or temperature. Measurement scales. Quantitative analysis also involves understanding the different measurement scales used to collect data. The four main measurement scales are nominal, ordinal, interval, and ratio. Nominal scales categorize data into distinct categories or groups, such as gender or marital status. Ordinal scales rank data in a specific order, but the intervals between the categories may not be equal, such as a Likert scale. Interval scales have equal intervals between the categories, but there is no true zero point, such as temperature measured in Celsius. Ratio scales have equal intervals and a true zero point, such as weight or income. 1.3.2 Data collection for quantitative analysis. To conduct quantitative analysis, researchers need to collect relevant data. There are various methods for collecting quantitative data, including surveys, experiments, and observations. Surveys. Surveys involve gathering data by asking questions to a sample of individuals or organizations. Surveys can be conducted through various means, such as face-to-face interviews, telephone interviews, online questionnaires, or paper-based surveys. Surveys provide researchers with a large amount of data that can be analyzed quantitatively. Experiments. Experiments are controlled studies conducted to test hypotheses and determine cause and effect relationships. In an experiment, researchers manipulate the independent variable and measure the effect on the dependent variable. This allows researchers to draw conclusions about the relationship between variables. Experimental designs can range from simple to complex, depending on the research question and resources available. Observations. Observations involve systematically watching and recording behaviors or events. Researchers can conduct observations in a natural setting or create a controlled environment for observation. Observational data can be collected through direct observation, where the researcher is physically present, or through indirect observation, such as analyzing existing data or records. 1.3.3 Data analysis techniques in quantitative analysis. Once the data is collected, researchers can apply various techniques to analyze the quantitative data and derive meaningful insights. Some common techniques used in quantitative analysis include descriptive statistics. Descriptive statistics summarize and describe the main features of the data. Measures of central tendency, such as mean, median, and mode, provide information about the average or typical value of a variable. Measures of dispersion, such as range, variance, and standard deviation, indicate the spread or variability of the data. Descriptive statistics help researchers understand the basic characteristics of the data and identify any patterns or trends. Inferential statistics. Inferential statistics involve making inferences or generalizations about a population based on a sample of data. Hypothesis testing is a common inferential statistical technique that allows researchers to test whether there is a significant difference between groups or variables. Confidence intervals provide a range of values within which the true population parameter is likely to fall. Correlation and regression analysis examine the relationship between variables and can be used to make predictions or forecasts. Data visualization. Data visualization is the graphical representation of data to facilitate understanding and interpretation. Charts, graphs, and plots are commonly used to visually represent quantitative data. Data visualization techniques help researchers identify patterns, trends, and outliers in the data. They also make it easier to communicate complex findings to a wider audience. 1.3.4 Advantages and limitations of quantitative analysis. Quantitative analysis offers several advantages in data analysis. It provides a systematic and objective approach to analyzing data, allowing for precise measurement and quantification. It enables researchers to test hypotheses, make predictions, and generalize findings to a larger population. Quantitative analysis also allows for statistical comparisons and provides a solid foundation for decision-making. However, quantitative analysis also has its limitations. It may oversimplify complex phenomena by reducing them to numerical values. It may not capture the full richness and context of qualitative data. Quantitative analysis relies heavily on the quality and accuracy of the data collected, and any errors or biases in the data can affect the validity of the results. Additionally, quantitative analysis may not be suitable for studying subjective experiences or understanding the underlying reasons and motivations behind certain behaviors. In conclusion, quantitative analysis is a powerful tool in data analysis that allows researchers to analyze numerical data, draw objective conclusions, and make informed decisions. By understanding the key concepts, data collection methods, analysis techniques, and the advantages and limitations of quantitative analysis, researchers can effectively utilize this approach to gain valuable insights from their data. 1.4 Qualitative Analysis. Qualitative analysis is a research method used to understand and interpret non-numerical data. Unlike quantitative analysis, which focuses on numerical data and statistical analysis, qualitative analysis aims to uncover the deeper meanings, patterns, and themes within the data. It provides a rich and detailed understanding of the subject matter, allowing researchers to explore complex phenomena and capture the perspectives and experiences of individuals. 1.4.1 Characteristics of qualitative analysis. Qualitative analysis involves the collection and analysis of qualitative data, which can take various forms, including interviews, observations, documents, and audiovisual materials. The data collected in qualitative research is typically in the form of words, images, or symbols, and it is often subjective and context-dependent. Here are some key characteristics of qualitative analysis. Subjectivity. Qualitative analysis acknowledges that researchers and participants bring their own perspectives, biases, and interpretations to the research process. Researchers must be aware of their own subjectivity and strive to minimize its influence on the analysis. Inductive approach. Qualitative analysis follows an inductive approach, meaning that it starts with specific observations and gradually develops broader theories or concepts based on those observations. It allows for the emergence of new insights and theories from the data. Contextual understanding. Qualitative analysis emphasizes the importance of understanding the social, cultural, and historical context in which the data was collected. It seeks to uncover the meaning and significance of the data within its specific context. Holistic perspective. Qualitative analysis aims to capture the complexity and richness of the data by considering the multiple dimensions and interconnections within the data. It takes a holistic perspective, recognizing that different aspects of the data are interconnected and influence each other. 1.4.2 Approaches to qualitative analysis. There are several approaches to qualitative analysis, each with its own techniques and methods. The choice of approach depends on the research question, the nature of the data, and the theoretical framework guiding the study. Here are some commonly used approaches. Coding and categorizing. Coding involves systematically categorizing and labeling segments of data based on their content or meaning. It helps to identify patterns, themes, and relationships within the data. Researchers can use manual coding or software tools to assist in the process. Thematic analysis. Thematic analysis involves identifying and analyzing recurring patterns or themes within the data. It aims to uncover the underlying meanings and concepts that emerge from the data. Researchers may use a deductive or inductive approach to thematic analysis. Content analysis. Content analysis focuses on analyzing the content of textual or visual data. It involves systematically categorizing and quantifying the content based on predefined criteria. Content analysis can be used to analyze documents, media, or any other form of textual or visual data. Grounded theory. Grounded theory is an approach to qualitative analysis that aims to develop theories or concepts based on the data itself. It involves a systematic process of data collection, coding, and analysis, leading to the development of new theories or concepts that are grounded in the data. 1.4.3 Rigor and trustworthiness in qualitative analysis. Ensuring rigor and trustworthiness is crucial in qualitative analysis to enhance the credibility and validity of the findings. Here are some strategies to enhance rigor in qualitative analysis. Triangulation. Triangulation involves using multiple sources of data, methods, or researchers to validate the findings. By using different perspectives and approaches, researchers can strengthen the credibility of their analysis. Member checking. Member checking involves sharing the findings with participants to verify the accuracy and interpretation of the data. It allows participants to provide feedback and ensure that their perspectives are accurately represented. Peer review. Peer review involves seeking feedback and critique from other researchers in the field. Peer review helps to identify potential biases, errors, or alternative interpretations in the analysis. Reflexivity. Reflexivity involves reflecting on the researcher's own biases, assumptions, and perspectives throughout the research process. Researchers should be transparent about their own positionality and how it may have influenced the analysis. 1.4.4 Advantages and limitations of qualitative analysis. Qualitative analysis offers several advantages and limitations that researchers should consider when choosing this approach. Advantages. In-depth understanding. Qualitative analysis allows for a deep and nuanced understanding of the research topic. It provides rich and detailed insights into the experiences, perspectives, and meanings of individuals. Flexibility. Qualitative analysis is flexible and adaptable, allowing researchers to explore unexpected findings and adapt their approach accordingly. It allows for the exploration of complex and dynamic phenomena. Contextualization. Qualitative analysis emphasizes the importance of understanding the context in which the data was collected. It provides a holistic view of the research topic, considering the social, cultural, and historical factors that shape it. Limitations. Subjectivity. Qualitative analysis is subjective and influenced by the researcher's interpretations and biases. It requires researchers to be aware of their own subjectivity and take steps to minimize its impact. Generalizability. Qualitative analysis typically involves a small sample size and focuses on specific contexts or individuals. The findings may not be generalizable to a larger population or different contexts. Time and resource intensive. Qualitative analysis can be time-consuming and resource-intensive. It requires careful planning, data collection, and analysis, which can be challenging for researchers with limited time and resources. In conclusion, qualitative analysis is a valuable research method that allows researchers to explore complex phenomena, uncover meanings, and capture the perspectives and experiences of individuals. It provides a rich and detailed understanding of the research topic, complementing quantitative analysis and contributing to a comprehensive approach to data analysis. 2. Data collection methods. 2.1 Primary data collection. Primary data collection is the process of gathering original data directly from the source for the purpose of analysis. This data is collected specifically for the research or analysis at hand and is not previously available or published. Primary data collection methods allow researchers to obtain first-hand information and insights, enabling them to address specific research questions or objectives. There are two main approaches to primary data collection: quantitative and qualitative. Each approach has its own unique characteristics, methods, and advantages. In this section, we will explore both quantitative and qualitative analysis in detail. 2.1.1 Quantitative analysis. Quantitative analysis involves the collection and analysis of numerical data. It focuses on measuring and quantifying variables, allowing for statistical analysis and objective conclusions. This approach is commonly used in fields such as economics, finance, psychology, and market research. Surveys and questionnaires. One of the most common methods of collecting quantitative data is through surveys and questionnaires. Surveys involve asking a set of structured questions to a sample of individuals or organizations. The responses are then analyzed to identify patterns, trends, and relationships. Surveys can be conducted through various mediums, including online platforms, telephone interviews, or face-to-face interactions. Experiments. Experiments are another important method of quantitative data collection. In an experiment, researchers manipulate one or more variables to observe the effect on another variable. This allows for the establishment of cause and effect relationships. Experiments are often conducted in controlled environments to ensure the validity and reliability of the results. Observations. Observational studies involve systematically observing and recording behaviors, events, or phenomena. Researchers can either be passive observers, where they simply observe and record without interfering, or active observers, where they actively engage with the subjects being observed. Observational studies are particularly useful when studying natural or real-life settings where experiments may not be feasible or ethical. Secondary data analysis. In addition to collecting primary data, quantitative analysis also involves the use of secondary data. Secondary data refers to data that has been collected by someone else for a different purpose but can be used for the current analysis. This can include data from government agencies, research institutions, or publicly available datasets. Secondary data analysis allows researchers to leverage existing data to answer research questions or validate their findings. Statistical analysis. Quantitative analysis relies heavily on statistical techniques to analyze and interpret the collected data. Statistical analysis involves the use of mathematical models, formulas, and software to summarize and analyze the data. Common statistical techniques used in quantitative analysis include descriptive statistics, inferential statistics, regression analysis, and hypothesis testing. These techniques help researchers identify patterns, relationships, and trends in the data, allowing for objective and evidence-based conclusions. Quantitative analysis offers several advantages. It provides precise and measurable data, allowing for statistical analysis and generalization to a larger population. It also allows for the identification of cause and effect relationships and the testing of hypotheses. However, quantitative analysis may not capture the full complexity of human experiences or provide in-depth insights into individual perspectives. This is where qualitative analysis comes into play. 2.1.2 Qualitative analysis. Qualitative analysis involves the collection and analysis of non-numerical data. It focuses on understanding the meanings, interpretations, and experiences of individuals or groups. This approach is commonly used in fields such as sociology, anthropology, psychology, and market research. Interviews. One of the most common methods of collecting qualitative data is through interviews. Interviews involve engaging in a conversation with individuals or groups to gather their perspectives, experiences, and opinions. Interviews can be structured, semi-structured, or unstructured, depending on the level of flexibility in the questioning process. The responses are then analyzed to identify themes, patterns, and insights. Focus groups. Focus groups involve bringing together a small group of individuals to discuss a specific topic or issue. The group dynamics and interactions allow for the exploration of different perspectives and the generation of rich qualitative data. Focus groups are particularly useful when studying social dynamics, group norms, or collective experiences. Observations. Similar to quantitative analysis, observations are also used in qualitative analysis. However, in qualitative research, observations focus on understanding behaviors, interactions, and contexts rather than quantifying them. Observations can be conducted in natural or controlled settings and can be either participant observations, where the researcher actively engages with the subjects, or non-participant observations, where the researcher remains an observer. Document analysis. Document analysis involves the systematic examination of written or visual materials, such as texts, photographs, videos, or artifacts. These materials can provide valuable insights into cultural, historical, or social contexts. Document analysis can be used to complement other qualitative data collection methods or as a standalone method, depending on the research objectives. Thematic analysis. Qualitative analysis often involves the process of thematic analysis. Thematic analysis involves identifying and analyzing patterns, themes, and categories within the collected data. This process allows researchers to uncover underlying meanings, interpretations, and experiences. Thematic analysis can be done manually or with the assistance of qualitative analysis software. Qualitative analysis offers several advantages. It allows for a deeper understanding of individual experiences, perspectives, and contexts. It provides rich and detailed data that can capture the complexity and nuances of human behavior. Qualitative analysis is particularly useful when exploring new or emerging research areas, generating hypotheses, or gaining insights into subjective experiences. However, qualitative analysis may be time-consuming, subjective, and challenging to generalize to a larger population. In conclusion, primary data collection methods encompass both quantitative and qualitative analysis. Quantitative analysis focuses on numerical data, statistical analysis, and objective conclusions, while qualitative analysis focuses on non-numerical data, in-depth insights, and subjective experiences. Both approaches have their own strengths and limitations, and researchers often use a combination of quantitative and qualitative methods to gain a comprehensive understanding of the research topic. 2.2 Secondary data collection. Secondary data collection is an essential aspect of data analysis. It involves gathering and analyzing data that has already been collected by someone else for a different purpose. This type of data can be obtained from various sources, such as government agencies, research institutions, academic journals, and online databases. Secondary data collection offers several advantages, including cost-effectiveness, time efficiency, and the ability to access a wide range of data. In this section, we will explore the different sources of secondary data, the process of collecting and evaluating secondary data, and the considerations involved in using secondary data for analysis. 2.2.1 Sources of secondary data. There are numerous sources from which secondary data can be obtained. These sources can be broadly categorized into internal and external sources. Internal sources refer to data that is collected and stored within an organization or institution, such as sales records, customer databases, or previous research studies conducted by the organization. External sources, on the other hand, include data collected by external entities, such as government agencies, research institutions, or commercial organizations. Some common sources of secondary data include government databases. Government agencies collect and maintain vast amounts of data on various topics, such as population demographics, economic indicators, health statistics, and crime rates. These databases, such as the U.S. Census Bureau or the World Health Organization, provide valuable secondary data for analysis. Research institutions, universities, research institutes, and think tanks often conduct studies and surveys on a wide range of topics. These organizations publish their findings in academic journals or make them available through their websites. Researchers can access these publications to gather secondary data for their analysis. Commercial databases. Many commercial organizations collect and sell data for market research purposes. These databases contain information on consumer behavior, market trends, and industry statistics. Examples of commercial databases include Nielsen, Euromonitor, and Statista. Online platforms. The Internet has become a vast repository of information, making it a valuable source of secondary data. Online platforms such as social media, online forums, and blogs can provide insights into consumer opinions, trends, and preferences. Additionally, online repositories like data.gov or Kaggle offer a wide range of datasets for analysis. Published literature. Academic journals, books, and conference proceedings are rich sources of secondary data. Researchers can review existing literature to gather relevant data and build upon previous studies. 2.2.2 Collecting and evaluating secondary data. Collecting secondary data involves identifying relevant sources, accessing the data, and extracting the required information for analysis. The process may vary depending on the source and format of the data. Here are some steps to consider when collecting and evaluating secondary data. Define research objectives. Clearly define the research objectives and the specific data requirements. This will help in identifying the most relevant sources and data. Identify suitable sources. Determine the most appropriate sources of secondary data based on the research objectives. Consider factors such as reliability, relevance, and accessibility of the data. Access the data. Once the sources have been identified, obtain access to the data. This may involve contacting the data custodians, subscribing to databases, or accessing publicly available sources. Evaluate data quality. Assess the quality and reliability of the secondary data. Consider factors such as the credibility of the source, the methodology used for data collection, and the representativeness of the sample. Extract and transform data. Extract the relevant data from the source and transform it into a format suitable for analysis. This may involve cleaning the data, standardizing variables, and merging datasets if necessary. Document data sources. Maintain a record of the sources and details of the secondary data used. This documentation is crucial for transparency, reproducibility, and acknowledging the contributions of the original data collectors. 2.2.3 Considerations in using secondary data. While secondary data collection offers numerous advantages, there are also some considerations to keep in mind when using this type of data for analysis. Data relevance. Ensure that the secondary data is relevant to the research objectives and the specific research questions being addressed. Carefully evaluate the suitability of the data for the analysis at hand. Data quality. Assess the quality and reliability of the secondary data. Consider factors such as the accuracy of the data, the representativeness of the sample, and the methodology used for data collection. Data limitations. Recognize the limitations of secondary data. It may not always provide the exact information required for the analysis, and there may be gaps or inconsistencies in the data. Data bias. Be aware of potential biases in the secondary data. The original data collection process may have been influenced by various factors, such as sampling bias or measurement bias. Consider these biases when interpreting the results. Ethical considerations. Respect the ethical considerations associated with using secondary data. Ensure that the data is used in accordance with legal and ethical guidelines, and consider the privacy and confidentiality of the individuals or organizations involved in the original data collection. In conclusion, secondary data collection is a valuable approach in data analysis, providing researchers with access to a wide range of data sources. By understanding the sources of secondary data, the process of collecting and evaluating it, and the considerations involved in its use, researchers can effectively utilize secondary data to gain insights and make informed decisions. 2.3 Sampling techniques. Sampling is a crucial step in the data collection process, as it involves selecting a subset of individuals or items from a larger population. The goal of sampling is to gather representative data that can be used to make inferences about the entire population. In this section, we will explore different sampling techniques commonly used in data analysis. 2.3.1 Simple random sampling. Simple random sampling is one of the most basic and widely used sampling techniques. It involves randomly selecting individuals from the population, where each individual has an equal chance of being chosen. This method ensures that every member of the population has an equal opportunity to be included in the sample. To perform simple random sampling, researchers can use various methods such as random number generators or random selection from a list. This technique is particularly useful when the population is homogeneous and there are no specific characteristics that need to be considered. 2.3.2 Stratified sampling. Stratified sampling is a technique used when the population can be divided into distinct subgroups or strata. In this method, the population is first divided into homogeneous groups based on certain characteristics or variables of interest. Then, a random sample is selected from each stratum in proportion to its size in the population. Stratified sampling ensures that each subgroup is adequately represented in the sample, which can be useful when there are significant differences between the subgroups. For example, if a study aims to analyze the opinions of students from different grade levels, stratified sampling can ensure that each grade level is represented proportionally in the sample. 2.3.3 Cluster sampling. Cluster sampling involves dividing the population into clusters or groups and randomly selecting entire clusters to be included in the sample. Unlike stratified sampling, where individuals are selected from each subgroup, cluster sampling involves selecting groups as the sampling unit. This technique is often used when it is impractical or costly to sample individuals directly. For example, if a researcher wants to study the eating habits of people in a city, they may randomly select a few neighborhoods and include all individuals within those neighborhoods in the sample. Cluster sampling can be an efficient way to gather data, especially when the clusters are representative of the population. However, it is important to consider the potential for increased variability within clusters compared to simple random sampling. 2.3.4 Systematic sampling. Systematic sampling involves selecting individuals from a population at regular intervals. The first individual is randomly selected, and then subsequent individuals are chosen based on a predetermined pattern. For example, if a researcher wants to sample every 10th person from a list, they would randomly select a starting point and then select every 10th person thereafter. Systematic sampling can be a convenient and efficient method, especially when the population is large and there is a clear ordering or structure. However, it is important to ensure that there is no hidden pattern or periodicity in the population that could bias the sample. 2.3.5 Convenience sampling. Convenience sampling, also known as accidental or haphazard sampling, involves selecting individuals who are readily available and convenient to include in the sample. This method is often used when time, cost, or accessibility constraints make it difficult to implement other sampling techniques. While convenience sampling is easy to implement, it can introduce bias into the sample. The individuals selected may not be representative of the entire population, leading to potential inaccuracies in the analysis. Therefore, caution should be exercised when interpreting the results obtained from convenience sampling. 2.3.6 Purposive sampling. Purposive sampling, also known as judgment or selective sampling, involves selecting individuals who possess specific characteristics or qualities of interest to the researcher. This method is often used in qualitative research, where the focus is on understanding specific phenomena or exploring particular cases. Purposive sampling allows researchers to target individuals who can provide valuable insights or unique perspectives on the research topic. However, it is important to acknowledge that the sample may not be representative of the entire population, and the findings may not be generalizable. 2.3.7 Snowball sampling. Snowball sampling, also known as chain referral sampling, is a technique used when the population of interest is difficult to reach or locate. In this method, initial participants are selected based on specific criteria, and then they are asked to refer other individuals who meet the criteria. Snowball sampling is often used in studies involving rare or stigmatized populations, where traditional sampling methods may not be feasible. While this technique can be useful for accessing hard-to-reach populations, it is important to recognize that the sample may be biased and may not represent the entire population. Conclusion. Sampling techniques play a crucial role in data analysis, as they determine the quality and representativeness of the data collected. Each sampling method has its own strengths and limitations, and the choice of technique depends on the research objectives, population characteristics, and available resources. Researchers should carefully consider the sampling technique that best suits their study and ensure that the sample is representative of the population of interest. By employing appropriate sampling techniques, researchers can gather reliable and valid data that can be effectively analyzed to draw meaningful conclusions. 2.4 Data validation and cleaning. Data validation and cleaning are crucial steps in the data analysis process. Before conducting any analysis, it is essential to ensure that the data is accurate, complete, and reliable. This section will discuss the importance of data validation and cleaning, as well as various techniques and best practices for performing these tasks. 2.4.1 Data validation. Data validation involves checking the integrity and accuracy of the data collected. It is essential to validate the data to identify any errors, inconsistencies, or missing values that may affect the analysis results. By validating the data, analysts can ensure that the data is reliable and suitable for analysis. There are several techniques for data validation, including 2.4.1.1 Range checks. Range checks involve verifying that the values fall within an acceptable range. For example, if you are analyzing data on the age of participants, you can check if the age values are within a reasonable range, such as 18 to 100 years. Values outside this range may indicate errors or outliers that need to be investigated further. 2.4.1.2 Consistency checks. Consistency checks involve comparing data across different variables or sources to identify any inconsistencies. For example, if you have collected data on the height and weight of individuals, you can check if the weight values are consistent with the height values. Inconsistencies may indicate data entry errors or other issues that need to be resolved. 2.4.1.3 Completeness checks. Completeness checks involve ensuring that all required data fields are filled in. Missing values can significantly impact the analysis results, so it is crucial to identify and address any missing data. Techniques such as imputation can be used to estimate missing values based on other available data. 2.4.1.4 Format checks. Format checks involve validating the format of the data. For example, if you are analyzing data on dates, you can check if the date values are in the correct format, e.g., DDYYYY. Format checks help identify any data entry errors or inconsistencies in the data. 2.4.2 Data cleaning. Data cleaning involves correcting or removing errors, inconsistencies, and outliers in the data. It is a critical step in preparing the data for analysis. By cleaning the data, analysts can ensure that the data is accurate, reliable, and suitable for analysis. There are several techniques for data cleaning, including 2.4.2.1 Removing duplicate entries. Duplicate entries can occur due to data entry errors or system issues. It is essential to identify and remove duplicate entries to avoid skewing the analysis results. Techniques such as deduplication can be used to identify and remove duplicate entries based on specific criteria. 2.4.2.2 Handling missing values. Missing values can occur due to various reasons, such as non-response or data entry errors. It is crucial to handle missing values appropriately to avoid bias in the analysis results. Techniques such as imputation can be used to estimate missing values based on other available data. Alternatively, if the missing values are significant, they can be excluded from the analysis. 2.4.2.3 Correcting inconsistent values. Inconsistent values can occur due to data entry errors or inconsistencies in the data collection process. It is essential to identify and correct inconsistent values to ensure the accuracy of the analysis results. Techniques such as data transformation or recoding can be used to correct inconsistent values based on predefined rules or criteria. 2.4.2.4 Handling outliers. Outliers are extreme values that deviate significantly from the other data points. Outliers can occur due to measurement errors, data entry errors, or genuine extreme values. It is crucial to identify and handle outliers appropriately to avoid bias in the analysis results. Techniques such as winsorization or trimming can be used to handle outliers by replacing extreme values with more reasonable values. 2.4.3 Best Practices for Data Validation and Cleaning. To ensure the effectiveness of data validation and cleaning, it is essential to follow best practices. Some best practices for data validation and cleaning include: start with a data validation plan. Define the validation criteria and techniques to be used before conducting the analysis. This will help ensure consistency and efficiency in the validation process. Use automated validation tools. Utilize software or tools that can automate the data validation process. These tools can help identify errors, inconsistencies, and missing values more efficiently. Document the validation process. Keep a record of the validation process, including the techniques used, the issues identified, and the actions taken to resolve them. This documentation will help ensure transparency and reproducibility in the analysis. Involve domain experts. Consult with subject matter experts to validate the data and identify any domain-specific issues or considerations. Their expertise can help ensure the accuracy and relevance of the analysis results. Regularly update and maintain the data. Data validation and cleaning should be an ongoing process. Regularly update and maintain the data to ensure its accuracy and reliability over time. By following these best practices, analysts can ensure that the data used for analysis is accurate, reliable, and suitable for making informed decisions. Conclusion. Data validation and cleaning are critical steps in the data analysis process. By validating the data for accuracy, completeness, and consistency, and cleaning it to remove errors, inconsistencies, and outliers, analysts can ensure that the data is reliable and suitable for analysis. Following best practices in data validation and cleaning is essential to maintain the integrity and quality of the data throughout the analysis process. 3. Descriptive statistics. 3.1 Measures of central tendency. In data analysis, measures of central tendency are used to describe the typical or central value of a dataset. These measures provide insights into the average or most representative value of a variable. The three commonly used measures of central tendency are the mean, median, and mode. 3.1.1 Mean. The mean, also known as the average, is calculated by summing up all the values in a dataset and dividing it by the total number of observations. It is the most commonly used measure of central tendency and is sensitive to extreme values. The formula for calculating the mean is: mean equals sum of all values, total number of observations. The mean is useful when the dataset is normally distributed and does not have extreme outliers. It provides a good representation of the central value when the data is symmetrically distributed around the mean. 3.1.2 Median. The median is the middle value in a dataset when it is arranged in ascending or descending order. It is not affected by extreme values or outliers and is a robust measure of central tendency. To calculate the median, the data must first be sorted, and then the middle value is determined. If the dataset has an even number of observations, the median is the average of the two middle values. The median is particularly useful when the dataset contains extreme values or when the distribution is skewed. It provides a better representation of the central value in such cases compared to the mean. 3.1.3 Mode. The mode is the value that appears most frequently in a dataset. Unlike the mean and median, the mode can be used for both numerical and categorical data. In some cases, a dataset may have multiple modes, making it multimodal. The mode is useful when identifying the most common value or category in a dataset. It is often used in market research to determine the most popular product or in survey analysis to identify the most common response. 3.1.4 Choosing the appropriate measure. The choice of measure of central tendency depends on the nature of the data and the research question. Each measure has its strengths and limitations, and it is important to consider the characteristics of the dataset before selecting the appropriate measure. When the data is normally distributed and does not contain extreme values, the mean provides a good representation of the central value. However, if the data is skewed or contains outliers, the median may be a better choice as it is less affected by extreme values. In cases where the data is categorical or consists of discrete values, the mode is the most appropriate measure of central tendency. It helps identify the most common category or value in the dataset. 3.1.5 Interpreting measures of central tendency. Measures of central tendency provide valuable insights into the central value of a dataset. However, it is important to interpret these measures in the context of the research question and the characteristics of the data. The mean is often interpreted as the average value of the dataset. For example, if the mean income of a sample is $50,000, it indicates that, on average, individuals in the sample earn $50,000. The median, on the other hand, represents the middle value of the dataset. If the median age of a population is 35 years, it means that half of the population is younger than 35 and half is older. The mode represents the most frequently occurring value or category in the dataset. For instance, if the mode of a dataset is red, it indicates that red is the most common category. It is important to note that while measures of central tendency provide a summary of the data, they do not capture the entire distribution. Therefore, it is essential to consider other measures, such as measures of dispersion, to gain a comprehensive understanding of the dataset. In conclusion, measures of central tendency, including the mean, median, and mode, are essential tools in data analysis. They help describe the central value of a dataset and provide insights into the typical or most representative value. The choice of measure depends on the characteristics of the data and the research question at hand. Interpreting these measures in the context of the data is crucial for drawing meaningful conclusions from the analysis. 3.2 Measures of dispersion. In data analysis, measures of dispersion are used to understand the spread or variability of a dataset. While measures of central tendency, such as mean and median, provide information about the central value of the data, measures of dispersion give insights into how the data points are distributed around the central value. By examining the dispersion, analysts can gain a deeper understanding of the variability and range of the data, which is crucial for making accurate interpretations and drawing meaningful conclusions. 3.2.1 Range. The range is the simplest measure of dispersion and is calculated by subtracting the minimum value from the maximum value in a dataset. It provides a quick overview of the spread of the data but is sensitive to outliers. For datasets with extreme values, the range may not accurately represent the overall dispersion. 3.2.2 Interquartile range, IQR. The interquartile range, IQR, is a robust measure of dispersion that is less affected by outliers compared to the range. It is calculated by subtracting the first quartile, Q1, from the third quartile, Q3, of the dataset. The quartiles divide the data into 4 equal parts, with Q1 representing the 25th percentile and Q3 representing the 75th percentile. The IQR provides a measure of the spread of the middle 50% of the data, making it useful for identifying the range of typical values. 3.2.3 Variance. Variance is a commonly used measure of dispersion that quantifies the average squared deviation of each data point from the mean. It provides a measure of how much the data points deviate from the mean value. To calculate the variance, the difference between each data point and the mean is squared, and the average of these squared differences is taken. The variance is expressed in squared units, which can make it difficult to interpret. To obtain a more interpretable measure, the square root of the variance, known as the standard deviation, is often used. 3.2.4 Standard deviation. The standard deviation is a widely used measure of dispersion that is calculated as the square root of the variance. It provides a measure of the average distance between each data point and the mean. The standard deviation is expressed in the same units as the original data, making it easier to interpret compared to the variance. A smaller standard deviation indicates that the data points are closer to the mean, while a larger standard deviation suggests a greater spread or variability. 3.2.5 Coefficient of variation. The coefficient of variation, CV, is a relative measure of dispersion that is used to compare the variability of datasets with different means and units of measurement. It is calculated by dividing the standard deviation by the mean and multiplying by 100 to express it as a percentage. The CV allows analysts to assess the relative variability of datasets and determine if the dispersion is high or low compared to the mean. A higher CV indicates a greater relative variability, while a lower CV suggests a more consistent dataset. 3.2.6 Range-based measures. In addition to the range itself, there are other measures of dispersion that are based on the range. These measures include the mean absolute deviation, MAD, and the median absolute deviation, MAD. The MAD is calculated by taking the average of the absolute differences between each data point and the mean or median, respectively. These measures provide a robust measure of dispersion that is less influenced by extreme values compared to the standard deviation. 3.2.7 Percentiles. Percentiles are measures of dispersion that divide the data into equal parts based on their rank. For example, the 25th percentile represents the value below which 25% of the data falls. Percentiles provide information about the spread of the data at specific points and can be used to identify outliers or extreme values. Common percentiles include the quartiles Q1, Q2, Q3, which divide the data into 4 equal parts, and the median Q2, which represents the middle value. 3.2.8 Box plots. Box plots, also known as box and whisker plots, are graphical representations of the measures of dispersion. They provide a visual summary of the minimum, first quartile, median, third quartile, and maximum values of a dataset. The box in the plot represents the interquartile range, IQR, while the whiskers extend to the minimum and maximum values within a certain range. Box plots are useful for comparing the dispersion of multiple datasets and identifying outliers. 3.2.9 Variability ratios. Variability ratios, such as the coefficient of variation, CV, and the range-to-mean ratio, are used to compare the dispersion of different datasets. These ratios provide a standardized measure of dispersion that allows analysts to assess the relative variability of datasets with different scales and units. By comparing the variability ratios, analysts can determine which dataset has a higher or lower dispersion relative to its mean. In summary, measures of dispersion are essential in data analysis as they provide insights into the spread and variability of a dataset. By understanding the dispersion, analysts can make more accurate interpretations and draw meaningful conclusions from the data. The range, interquartile range, variance, standard deviation, and other measures discussed in this section offer different perspectives on the dispersion of data and can be used in combination to gain a comprehensive understanding of the dataset. 3.3 Data visualization. Data visualization is a powerful tool in the field of data analysis that allows us to present complex information in a visual format. It involves the use of charts, graphs, and other visual elements to represent data in a way that is easy to understand and interpret. Data visualization plays a crucial role in both quantitative and qualitative analysis, as it helps to uncover patterns, trends, and insights that may not be immediately apparent in raw data. 3.3.1 Importance of data visualization. Data visualization is important for several reasons. Firstly, it helps to simplify complex data sets by presenting them in a visual format. This makes it easier for analysts and decision makers to understand the information and draw meaningful conclusions. By representing data visually, patterns and relationships can be identified more easily, leading to better insights and informed decision-making. Secondly, data visualization enhances communication. Visual representations of data are often more engaging and memorable than raw numbers or text. They can effectively convey information to a wide range of audiences, including those who may not have a strong background in data analysis. By presenting data in a visually appealing and accessible manner, data visualization helps to facilitate effective communication and knowledge sharing. Thirdly, data visualization enables the exploration of data from different perspectives. By using various types of charts, graphs, and interactive visualizations, analysts can manipulate and interact with the data to uncover hidden patterns and relationships. This exploratory approach allows for a deeper understanding of the data and can lead to new insights and discoveries. 3.3.2 Types of data visualization. There are numerous types of data visualizations that can be used depending on the nature of the data and the insights being sought. Some common types of data visualizations include bar charts. Bar charts are used to compare different categories or groups. They consist of rectangular bars of varying lengths, with each bar representing a category and the length of the bar indicating the value or frequency of that category. Line charts. Line charts are used to show trends over time. They consist of a series of data points connected by lines, with the x-axis representing time and the y-axis representing the value or frequency of the data. Pie charts. Pie charts are used to show the proportion of different categories within a whole. They consist of a circle divided into sectors, with each sector representing a category and the size of the sector indicating the proportion of that category. Scatter plots. Scatter plots are used to show the relationship between two variables. They consist of a series of data points plotted on a two-dimensional graph, with each data point representing the values of the two variables. Heat maps. Heat maps are used to show the density or intensity of a variable across different categories or regions. They consist of a grid of cells, with each cell representing a category or region and the color or shading of the cell indicating the value or intensity of the variable. Tree maps. Tree maps are used to show hierarchical relationships within a dataset. They consist of nested rectangles, with each rectangle representing a category or subcategory and the size of the rectangle indicating the value or proportion of that category. These are just a few examples of the many types of data visualizations that can be used. The choice of visualization depends on the specific goals of the analysis and the nature of the data being analyzed. 3.3.3 Guidelines for effective data visualization. While data visualization can be a powerful tool, it is important to follow certain guidelines to ensure that the visualizations are effective and accurate representations of the data. Here are some guidelines to consider. Simplicity. Keep the visualizations simple and uncluttered. Avoid unnecessary elements or embellishments that can distract from the main message. Accuracy. Ensure that the visualizations accurately represent the data. Use appropriate scales, labels, and legends to provide clear and accurate information. Relevance. Choose visualizations that are relevant to the data and the insights being sought. Consider the nature of the data and the goals of the analysis when selecting the appropriate visualization type. Consistency. Use consistent colors, fonts, and styles across different visualizations to maintain a cohesive and professional look. Interactivity. Consider using interactive visualizations that allow users to explore the data and uncover insights on their own. This can enhance engagement and understanding. Accessibility. Ensure that the visualizations are accessible to a wide range of audiences, including those with visual impairments or other disabilities. Provide alternative text or descriptions for visual elements to make them accessible to screen readers. By following these guidelines, analysts can create effective and impactful data visualizations that enhance understanding, communication, and decision-making. 3.3.4 Tools for data visualization. There are numerous tools available for creating data visualizations, ranging from simple spreadsheet software to advanced data visualization platforms. Some popular tools include Microsoft Excel. Excel is a widely used spreadsheet software that offers basic data visualization capabilities. It provides a range of chart types and customization options to create simple visualizations. Tableau. Tableau is a powerful data visualization platform that allows users to create interactive and dynamic visualizations. It offers a wide range of chart types, advanced analytics, and data blending capabilities. Power BI. Power BI is a business intelligence tool by Microsoft that enables users to create interactive dashboards and reports. It offers a range of data visualization options and integrates with various data sources. Python. Python is a popular programming language for data analysis and visualization. It offers libraries such as Matplotlib, Seaborn, and Plotly, which provide extensive capabilities for creating static and interactive visualizations. R. R is another programming language commonly used for data analysis and visualization. It offers packages such as ggplot2 and Plotly, which provide a wide range of visualization options. These are just a few examples of the many tools available for data visualization. The choice of tool depends on factors such as the complexity of the analysis, the level of interactivity required, and the user's familiarity with the tool. In conclusion, data visualization is a crucial component of both quantitative and qualitative analysis. It helps to simplify complex data, enhance communication, and enable the exploration of data from different perspectives. By following guidelines for effective data visualization and using appropriate tools, analysts can create impactful visualizations that facilitate understanding, communication, and decision-making. 3.4 Data interpretation. Data interpretation is a crucial step in the data analysis process. Once you have collected and analyzed your data using various quantitative and qualitative techniques, the next step is to interpret the findings. Data interpretation involves making sense of the results and drawing meaningful conclusions from the data. 3.4.1 Understanding quantitative analysis results. Quantitative analysis involves the use of numerical data to understand patterns, relationships, and trends. When interpreting quantitative analysis results, it is important to consider the following. 1. Measures of central tendency. Measures of central tendency, such as mean, median, and mode, provide information about the average or typical value of a dataset. When interpreting these measures, it is important to consider the distribution of the data. For example, if the data is skewed, the median may be a more appropriate measure of central tendency than the mean. 2. Measures of dispersion. Measures of dispersion, such as range, variance, and standard deviation, provide information about the spread or variability of the data. When interpreting these measures, it is important to consider the context of the data and the research question. For example, a large standard deviation may indicate a high degree of variability in the data, which could have implications for the generalizability of the findings. 3. Statistical significance. In quantitative analysis, statistical tests are often used to determine whether the observed differences or relationships in the data are statistically significant. When interpreting statistical significance, it is important to consider the p-value, which indicates the probability of obtaining the observed results by chance alone. A p-value less than 0.05 is typically considered statistically significant. 4. Effect size. In addition to statistical significance, it is important to consider the effect size when interpreting quantitative analysis results. Effect size measures the magnitude of the observed difference or relationship. A large effect size indicates a strong relationship or difference, while a small effect size indicates a weak relationship or difference. Interpreting effect sizes can help determine the practical significance of the findings. 3.4.2 Making sense of qualitative analysis results. Qualitative analysis involves the interpretation of non-numerical data, such as text, images, or observations. When interpreting qualitative analysis results, it is important to consider the following. 1. Themes and patterns. Qualitative analysis often involves identifying themes and patterns in the data. Themes are recurring ideas or concepts that emerge from the data, while patterns are regularities or similarities in the data. When interpreting qualitative analysis results, it is important to identify and describe these themes and patterns, as they provide insights into the research question or topic of interest. 2. Contextual understanding. Qualitative analysis often involves understanding the context in which the data was collected. This includes considering the social, cultural, and historical factors that may have influenced the data. When interpreting qualitative analysis results, it is important to consider the broader context and to provide a rich description of the data. 3. Triangulation. Triangulation is a technique used in qualitative analysis to enhance the validity and reliability of the findings. It involves using multiple sources of data or multiple researchers to confirm or corroborate the findings. When interpreting qualitative analysis results, it is important to consider the different perspectives or sources of data that were used and to compare and contrast the findings. 4. Reflexivity. Reflexivity is an important aspect of qualitative analysis, which involves reflecting on the researcher's own biases, assumptions, and perspectives. When interpreting qualitative analysis results, it is important to acknowledge and reflect on the researcher's role in shaping the findings. This can help ensure transparency and rigor in the interpretation process. 3.4.3 Integrating quantitative and qualitative analysis. In some cases, researchers may use both quantitative and qualitative analysis techniques to gain a more comprehensive understanding of the data. When integrating quantitative and qualitative analysis, it is important to consider the following. 1. Complementarity. Quantitative and qualitative analysis techniques can complement each other by providing different perspectives or insights into the data. When interpreting the findings, it is important to consider how the quantitative and qualitative results align or diverge and to explore the reasons behind any discrepancies. 2. Triangulation. Triangulation can also be used to integrate quantitative and qualitative analysis. By using multiple sources of data or multiple analysis techniques, researchers can enhance the validity and reliability of the findings. When interpreting the integrated results, it is important to consider the strengths and limitations of each analysis technique and to provide a balanced interpretation. 3. Contextualization. Integrating quantitative and qualitative analysis can help provide a more nuanced and contextualized understanding of the data. When interpreting the integrated results, it is important to consider the broader context and to explore how the quantitative and qualitative findings relate to the research question or topic of interest. In conclusion, data interpretation is a critical step in the data analysis process. Whether you are analyzing quantitative or qualitative data, it is important to consider the appropriate techniques and methods for interpreting the results. By carefully considering measures of central tendency, measures of dispersion, statistical significance, effect size, themes, patterns, context, triangulation, reflexivity, complementarity, and contextualization, researchers can draw meaningful conclusions and insights from their data analysis. 4. Inferential statistics. 4.1 Hypothesis testing. Hypothesis testing is a fundamental concept in inferential statistics that allows us to make conclusions about a population based on sample data. It involves formulating a hypothesis, collecting data, and using statistical techniques to determine whether the evidence supports or contradicts the hypothesis. 4.1.1 Introduction to hypothesis testing. In hypothesis testing, we start with two competing hypotheses, the null hypothesis H0 and the alternative hypothesis HA. The null hypothesis represents the status quo or the absence of an effect, while the alternative hypothesis represents the claim or the presence of an effect. The goal of hypothesis testing is to assess the evidence provided by the sample data and make a decision about which hypothesis is more likely to be true. This decision is based on the calculated test statistic and the associated p-value. 4.1.2 Steps in hypothesis testing. Hypothesis testing involves several steps that guide us through the process of evaluating the evidence and making a decision. These steps include formulating the null and alternative hypotheses. The first step is to clearly define the null and alternative hypotheses based on the research question or problem at hand. The null hypothesis typically assumes no difference or no effect, while the alternative hypothesis suggests the presence of a difference or effect. Choosing the significance level. The significance level, denoted as alpha, determines the threshold for rejecting the null hypothesis. Commonly used significance levels are 0.05 and 0.01, representing a 5% and 1% chance of making a type 1 error, respectively. Selecting the appropriate test statistic. The choice of test statistic depends on the nature of the data and the research question. Common test statistics include the t-test, z-test, chi-square test, and f-test. Collecting and analyzing the data. Once the hypotheses and test statistic are defined, data is collected and analyzed using appropriate statistical techniques. The test statistic is calculated based on the sample data, and its value is compared to the critical value or p-value to make a decision. Calculating the p-value. The p-value represents the probability of obtaining a test statistic as extreme as the one observed, assuming the null hypothesis is true. If the p-value is less than the significance level, we reject the null hypothesis in favor of the alternative hypothesis. Making a decision. Based on the calculated p-value and the chosen significance level, a decision is made regarding the acceptance or rejection of the null hypothesis. If the p-value is less than the significance level, we reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. 4.1.3 Types of errors in hypothesis testing. Hypothesis testing is not a foolproof method, and errors can occur. There are two types of errors that can be made in hypothesis testing. Type 1 error. A type 1 error occurs when we reject the null hypothesis when it is actually true. This is also known as a false positive. The significance level alpha determines the probability of making a type 1 error. A lower significance level reduces the chance of making a type 1 error but increases the chance of a type 2 error. Type 2 error. A type 2 error occurs when we fail to reject the null hypothesis when it is actually false. This is also known as a false negative. The probability of making a type 2 error is denoted as beta, and is influenced by factors such as sample size, effect size, and the chosen significance level. 4.1.4 Common hypothesis tests. There are various hypothesis tests that are commonly used depending on the nature of the data and the research question. Some of the most frequently used hypothesis tests include 1. Sample t-test. This test is used to determine whether the mean of a single sample is significantly different from a hypothesized population mean. Independent samples t-test. This test is used to compare the means of two independent samples and determine whether they are significantly different from each other. Paired samples t-test. This test is used to compare the means of two related samples, such as before and after measurements, and determine whether there is a significant difference. Chi-square test. This test is used to determine whether there is a significant association between two categorical variables. Analysis of variance ANOVA. ANOVA is used to compare the means of 3 or more groups and determine whether there are significant differences among them. Pearson correlation test. This test is used to determine whether there is a significant linear relationship between 2 continuous variables. Simple linear regression. This test is used to model the relationship between a dependent variable and an independent variable and determine whether there is a significant linear relationship. These are just a few examples of the many hypothesis tests available. The choice of the appropriate test depends on the research question, the type of data, and the assumptions underlying the test. 4.1.5 Assumptions in hypothesis testing. Hypothesis tests are based on certain assumptions that must be met for the results to be valid. Some common assumptions include random sampling. The data should be collected using a random sampling method to ensure that the sample is representative of the population. Independence. The observations in the sample should be independent of each other. This assumption is particularly important in hypothesis tests involving paired or dependent samples. Normality. The data should follow a normal distribution. This assumption is necessary for tests such as the t-test and ANOVA. If the data is not normally distributed, transformations or non-parametric tests may be used. Homogeneity of variance. The variances of the groups being compared should be equal. Violation of this assumption may require the use of alternative tests, such as Welch's t-test. It is important to assess these assumptions before conducting a hypothesis test and consider appropriate remedies if any assumptions are violated. In conclusion, hypothesis testing is a powerful tool in data analysis that allows us to draw conclusions about populations based on sample data. By following a systematic approach and considering the appropriate statistical techniques, researchers can make informed decisions and contribute to the body of knowledge in their respective fields. 4.2 Confidence intervals. In inferential statistics, confidence intervals play a crucial role in estimating population parameters based on sample data. A confidence interval provides a range of values within which the true population parameter is likely to fall. It is a measure of the uncertainty associated with estimating population parameters from sample data. 4.2.1 Understanding confidence intervals. A confidence interval consists of 2 parts, a point estimate and a margin of error. The point estimate is the best estimate of the population parameter based on the sample data. It is usually calculated using a sample statistic, such as the sample mean or proportion. The margin of error represents the range of values within which the true population parameter is likely to fall. The level of confidence associated with a confidence interval indicates the probability that the interval contains the true population parameter. Commonly used levels of confidence are 90%, 95%, and 99%. For example, a 95% confidence interval means that if we were to repeat the sampling process multiple times, we would expect the true population parameter to fall within the interval in 95% of the samples. 4.2.2 Calculating confidence intervals. The calculation of a confidence interval depends on the type of data and the parameter of interest. Here, we will discuss the calculation of confidence intervals for the population mean and proportion. Confidence interval for the population mean. To calculate a confidence interval for the population mean, we need to know the sample mean, the sample standard deviation or standard error, and the sample size. The formula for calculating a confidence interval for the population mean is text confidence interval equals text sample mean PM text margin of error. The margin of error is determined by the level of confidence and the standard deviation, or standard error, of the population. If the population standard deviation is known, the margin of error can be calculated using the z-score corresponding to the desired level of confidence. If the population standard deviation is unknown, the margin of error can be calculated using the t-score and the sample standard deviation. Confidence interval for the population proportion. To calculate a confidence interval for the population proportion, we need to know the sample proportion and the sample size. The formula for calculating a confidence interval for the population proportion is text confidence interval equals text sample proportion PM text margin of error. The margin of error is determined by the level of confidence and the sample proportion. It can be calculated using the z-score corresponding to the desired level of confidence. 4.2.3 Interpreting confidence intervals. Interpreting a confidence interval involves understanding the range of values and the level of confidence associated with it. The confidence interval provides a range within which we can be reasonably confident that the true population parameter lies. If the confidence interval is narrow, it indicates that the estimate is precise and provides a relatively small range of values within which the true parameter is likely to fall. On the other hand, if the confidence interval is wide, it indicates that the estimate is less precise and provides a larger range of values. It is important to note that a confidence interval does not guarantee that the true population parameter falls within the interval. It only provides a measure of the uncertainty associated with the estimation process. Additionally, different confidence intervals may overlap, indicating that the estimates are not significantly different from each other. 4.2.4 Importance of confidence intervals. Confidence intervals are essential in data analysis for several reasons. Estimating population parameters. Confidence intervals allow us to estimate population parameters based on sample data. They provide a range of values within which the true parameter is likely to fall, giving us a measure of the uncertainty associated with the estimation. Comparing groups. Confidence intervals can be used to compare groups or populations. By calculating confidence intervals for the means or proportions of different groups, we can determine if there is a significant difference between them. Decision-making. Confidence intervals provide valuable information for decision-making. For example, in marketing research, confidence intervals can help determine the range of potential market shares for a new product. Generalizability. Confidence intervals help us generalize the findings from a sample to the larger population. By estimating the population parameter within a range, we can make inferences about the entire population. Assessing statistical significance. Confidence intervals can be used to assess the statistical significance of a result. If the confidence interval does not include a specific value, it suggests that the result is statistically significant. 4.2.5 Limitations of confidence intervals. While confidence intervals are valuable tools in data analysis, they have certain limitations. Sample size. Confidence intervals are influenced by the sample size. Smaller sample sizes result in wider intervals and less precise estimates. Sampling bias. Confidence intervals assume that the sample is representative of the population. If the sample is biased or not representative, the confidence interval may not accurately estimate the population parameter. Assumptions. Confidence intervals rely on certain assumptions, such as the normality of the data and independence of observations. Violation of these assumptions can affect the accuracy of the interval. Interpretation. Interpreting confidence intervals requires understanding the concept of probability and uncertainty. Misinterpretation of confidence intervals can lead to incorrect conclusions. Despite these limitations, confidence intervals provide valuable information in data analysis and are widely used in various fields, including business, healthcare, social sciences, and market research. In the next section, we will explore correlation and regression analysis, which are statistical techniques used to examine the relationship between variables and make predictions based on the data. 4.3 Correlation and regression analysis. In the field of data analysis, correlation and regression analysis are powerful statistical techniques used to examine the relationship between variables. These techniques are widely employed in various disciplines, including social sciences, economics, psychology, and healthcare, to name a few. Correlation analysis helps us understand the strength and direction of the relationship between two or more variables, while regression analysis allows us to predict the value of a dependent variable based on the values of one or more independent variables. 4.3.1 Correlation analysis. Correlation analysis is a statistical method used to measure the degree of association between two or more variables. It helps us understand how changes in one variable are related to changes in another variable. The result of a correlation analysis is expressed as a correlation coefficient, which ranges from -1 to +1. A correlation coefficient of +1 indicates a perfect positive correlation, meaning that as one variable increases, the other variable also increases proportionally. On the other hand, a correlation coefficient of -1 indicates a perfect negative correlation, whereas one variable increases, the other variable decreases proportionally. A correlation coefficient of 0 indicates no correlation or a weak relationship between the variables. Correlation analysis can be performed using various methods, such as Pearson's correlation coefficient, Spearman's rank correlation coefficient, and Kendall's tau coefficient. Pearson's correlation coefficient is the most commonly used method and is suitable for analyzing the relationship between two continuous variables that follow a linear pattern. Spearman's rank correlation coefficient and Kendall's tau coefficient are non-parametric methods that are used when the variables are not normally distributed or when the relationship is not linear. Correlation analysis is useful in many ways. It helps researchers identify relationships between variables, determine the strength and direction of the relationship, and assess the significance of the relationship. Correlation analysis can also be used to identify outliers or influential data points that may affect the relationship between variables. 4.3.2 Regression analysis. Regression analysis is a statistical technique used to model the relationship between a dependent variable and one or more independent variables. It allows us to predict the value of the dependent variable based on the values of the independent variables. Regression analysis is widely used in various fields to make predictions, understand the impact of independent variables on the dependent variable, and test hypotheses. There are different types of regression analysis, including simple linear regression, multiple linear regression, and logistic regression. Simple linear regression is used when there is a linear relationship between the dependent variable and one independent variable. Multiple linear regression is used when there is a linear relationship between the dependent variable and two or more independent variables. Logistic regression is used when the dependent variable is binary or categorical. Regression analysis involves estimating the coefficients of the regression equation, which represent the relationship between the independent variables and the dependent variable. The coefficients can be interpreted as the change in the dependent variable associated with a one-unit change in the independent variable, holding all other variables constant. The regression equation can be used to make predictions and understand the impact of the independent variables on the dependent variable. Regression analysis also provides measures of goodness of fit, such as the coefficient of determination, R², which indicates the proportion of the variance in the dependent variable that can be explained by the independent variables. A higher R² value indicates a better fit of the regression model to the data. Regression analysis has numerous applications. It is used in economics to analyze the relationship between variables such as income and consumption. In healthcare, regression analysis is used to predict patient outcomes based on various factors. In marketing, it is used to understand the impact of advertising on sales. Regression analysis is a versatile tool that can be applied to a wide range of research questions and problems. 4.3.3 Assumptions and limitations. Both correlation and regression analysis have certain assumptions and limitations that need to be considered when interpreting the results. In correlation analysis, the assumptions include linearity, normality, and independence of observations. The relationship between variables should be linear, the variables should follow a normal distribution, and the observations should be independent. In regression analysis, the assumptions include linearity, independence of errors, homoscedasticity, constant variance of errors, and normality of errors. Violation of these assumptions can affect the validity of the regression model and the interpretation of the results. It is important to assess the assumptions and, if violated, consider alternative methods or transformations of the variables. Another limitation of both correlation and regression analysis is that they only measure the association between variables and cannot establish causality. Correlation does not imply causation, and regression analysis can only suggest a relationship but cannot prove causation. It is important to consider other evidence and conduct further research to establish causal relationships. In conclusion, correlation and regression analysis are valuable tools in data analysis that help us understand the relationship between variables and make predictions. Correlation analysis measures the strength and direction of the relationship, while regression analysis models the relationship and allows for prediction. Understanding the assumptions and limitations of these techniques is crucial for accurate interpretation and application in research and decision-making. 4.4 ANOVA and chi-square tests. In data analysis, there are various statistical tests that can be used to analyze different types of data. Two commonly used tests are the analysis of variance (ANOVA) and the chi-square test. These tests are used to analyze quantitative and qualitative data, respectively, and provide valuable insights into the relationships and differences within a dataset. 4.4.1 Analysis of variance (ANOVA). ANOVA is a statistical test used to determine whether there are any significant differences between the means of three or more groups. It is particularly useful when comparing means across multiple categories or levels of a categorical variable. ANOVA assesses the variation between groups and within groups to determine if the differences observed are statistically significant. The basic principle behind ANOVA is to compare the variation between groups, known as the between-group variation, with the variation within groups, known as the within-group variation. If the between-group variation is significantly larger than the within-group variation, it suggests that there are significant differences between the groups being compared. ANOVA calculates an F statistic, which is the ratio of the between-group variation to the within-group variation. The F statistic is then compared to a critical value to determine if the differences between the groups are statistically significant. If the calculated F statistic is greater than the critical value, it indicates that there are significant differences between the groups. There are different types of ANOVA tests, depending on the design of the study. The most common types include one-way ANOVA, two-way ANOVA, and repeated measures ANOVA. One-way ANOVA is used when there is only one independent variable, while two-way ANOVA is used when there are two independent variables. Repeated measures ANOVA is used when the same participants are measured multiple times. ANOVA is widely used in various fields, including psychology, biology, social sciences, and business. It allows researchers to compare means across multiple groups and determine if there are any significant differences. By identifying these differences, researchers can gain insights into the factors that contribute to variations in the data. 4.4.2 Chi-square test. The chi-square test is a statistical test used to determine if there is a significant association between two categorical variables. It is particularly useful when analyzing qualitative data, such as survey responses or categorical data. The chi-square test compares the observed frequencies of different categories with the expected frequencies to determine if there is a significant difference. The test calculates a chi-square statistic, which measures the discrepancy between the observed and expected frequencies. This statistic is then compared to a critical value to determine if the association between the variables is statistically significant. There are different types of chi-square tests, depending on the research question and the nature of the data. The most common types include the chi-square test for independence and the chi-square test for goodness of fit. The chi-square test for independence is used to determine if there is a relationship between two categorical variables. The chi-square test for goodness of fit is used to determine if the observed frequencies of a single categorical variable differ significantly from the expected frequencies. The chi-square test is widely used in various fields, including market research, social sciences, and healthcare. It allows researchers to analyze the association between categorical variables and identify any significant relationships. By understanding these relationships, researchers can make informed decisions and draw meaningful conclusions from the data. Both ANOVA and chi-square tests are powerful tools in data analysis, providing valuable insights into the relationships and differences within a dataset. While ANOVA is used to compare means across multiple groups, the chi-square test is used to analyze the association between categorical variables. By applying these tests appropriately, researchers can uncover patterns, make informed decisions, and draw meaningful conclusions from their data. 5. Qualitative data analysis. 5.1 Coding and categorizing. In the field of qualitative data analysis, coding and categorizing are fundamental processes that help researchers make sense of the data they have collected. Coding involves the systematic process of assigning labels or tags to segments of data, while categorizing involves grouping these coded segments into meaningful categories. This section will explore the importance of coding and categorizing in qualitative analysis and provide an overview of different coding techniques. 5.1.1 Introduction to coding. Coding is a crucial step in qualitative data analysis as it allows researchers to organize and make sense of the vast amount of information collected during the research process. By assigning codes to specific segments of data, researchers can identify patterns, themes, and relationships within the data. Coding helps to transform raw data into meaningful and manageable units that can be analyzed and interpreted. There are two main types of coding in qualitative analysis: inductive coding and deductive coding. Inductive coding, also known as open coding, involves the development of codes directly from the data without any preconceived categories or theoretical frameworks. Deductive coding, on the other hand, involves the application of pre-existing categories or theoretical frameworks to the data. 5.1.2 Steps in the coding process. The coding process typically involves several steps that researchers follow to ensure consistency and accuracy in their analysis. These steps include familiarization with the data. Researchers begin by immersing themselves in the data, reading and rereading the transcripts, field notes, or other sources of qualitative data. This step helps researchers gain a deep understanding of the data and identify initial ideas or concepts. Initial coding. In this step, researchers start assigning codes to segments of data that are relevant to their research questions or objectives. This initial coding is often done in an open-ended manner, allowing for the emergence of new codes and themes. Codebook development. As the coding process progresses, researchers develop a codebook that documents the codes and their definitions. The codebook serves as a reference guide for consistent coding throughout the analysis. Coding consistency. Researchers ensure consistency in coding by regularly reviewing and discussing their coding decisions. This step helps to minimize bias and increase intercoder reliability when multiple researchers are involved in the analysis. Code revision and refinement. As the analysis progresses, researchers may revise and refine the codes to capture the nuances and complexities of the data. This iterative process allows for a more nuanced understanding of the data and the emergence of new themes or categories. 5.1.3 Coding techniques. There are various coding techniques that researchers can employ during the qualitative analysis process. Some commonly used coding techniques include descriptive coding. Descriptive coding involves assigning labels or tags to segments of data based on their content or characteristics. This technique helps researchers identify and describe the main themes or concepts present in the data. Conceptual coding. Conceptual coding involves assigning codes based on theoretical concepts or frameworks. Researchers apply pre-existing theories or concepts to the data to identify patterns or relationships. Pattern coding. Pattern coding involves identifying recurring patterns or sequences of events in the data. Researchers assign codes to these patterns to understand the underlying processes or dynamics. Emotional coding. Emotional coding involves capturing the emotional content or affective responses present in the data. Researchers assign codes to segments of data that express emotions or feelings. Process coding. Process coding involves capturing the steps or stages involved in a particular phenomenon or process. Researchers assign codes to segments of data that describe the progression or evolution of a phenomenon. 5.1.4 Categorizing and theme development. Once the coding process is complete, researchers move on to the categorizing stage. Categorizing involves grouping the coded segments of data into meaningful categories or themes. This process helps researchers organize and make sense of the data by identifying commonalities and differences within the coded segments. Categorizing can be done in various ways, depending on the research objectives and the nature of the data. Some common approaches to categorizing include hierarchical categorizing. Hierarchical categorizing involves organizing the codes into a hierarchical structure, with broader categories at the top and more specific subcategories below. This approach allows for a systematic and structured analysis of the data. Axial categorizing. Axial categorizing involves identifying the relationships between codes and creating connections between different categories. This approach helps researchers understand the interconnections and relationships within the data. Thematic development. Thematic development involves identifying overarching themes or patterns that emerge from the coded segments. Researchers analyze the categories and codes to identify the main themes that represent the essence of the data. The process of categorizing and theme development is iterative and may involve revisiting and refining the categories as the analysis progresses. Researchers often engage in discussions and reflections to ensure the accuracy and validity of the categories and themes identified. In conclusion, coding and categorizing are essential processes in qualitative data analysis. They allow researchers to organize, analyze, and interpret the data collected during the research process. By assigning codes to segments of data and grouping them into meaningful categories, researchers can identify patterns, themes, and relationships within the data. The coding process involves several steps, including familiarization with the data, initial coding, codebook development, coding consistency, and code revision. Different coding techniques, such as descriptive coding, conceptual coding, pattern coding, emotional coding, and process coding, can be employed to capture different aspects of the data. Categorizing and theme development involve grouping the coded segments into meaningful categories or themes, allowing for a deeper understanding of the data. 5.2 Thematic analysis. Thematic analysis is a qualitative data analysis method that involves identifying and analyzing patterns, themes, and meanings within a dataset. It is a flexible and widely used approach that allows researchers to explore and understand the rich and complex nature of qualitative data. Thematic analysis can be applied to various types of qualitative data, including interviews, focus groups, surveys, and written documents. 5.2.1 Introduction to thematic analysis. Thematic analysis is a systematic and iterative process that involves several steps. The first step is familiarization with the data, where researchers immerse themselves in the dataset to gain a deep understanding of its content. This involves reading and rereading the data, taking notes, and identifying initial ideas or patterns. The next step is generating initial codes, which involves identifying and labeling meaningful units of data. These codes can be descriptive, interpretive, or conceptual, depending on the level of analysis. Researchers can use various techniques to generate codes, such as line-by-line coding, focused coding, or theoretical coding. Once the initial codes are generated, the next step is to search for themes. Themes or patterns are recurring ideas that emerge from the data. Researchers can identify themes by grouping similar codes together and looking for connections and relationships between them. Themes can be explicit or implicit, and they can capture both manifest and latent content within the data. After identifying themes, the next step is to review and refine them. This involves examining the themes in relation to the dataset as a whole and ensuring that they accurately represent the data. Researchers may need to revise, combine, or split themes to ensure they capture the complexity and nuances of the data. The final step is to define and name the themes. This involves creating clear and concise descriptions of each theme and providing illustrative examples from the data. Researchers may also develop a thematic map or diagram to visually represent the relationships between themes. 5.2.2 Analyzing themes. Once the themes have been identified and defined, researchers can begin analyzing and interpreting them. This involves exploring the relationships between themes, examining variations within themes, and considering the broader context and implications of the themes. Researchers can use various techniques to analyze themes, such as content analysis, narrative analysis, or discourse analysis. These techniques allow researchers to delve deeper into the meaning and significance of the themes and to uncover underlying patterns and structures within the data. During the analysis process, researchers may also consider the frequency and distribution of themes within the dataset. They may calculate the prevalence of each theme or explore how themes vary across different subgroups or categories within the data. This can provide valuable insights into the significance and relevance of the themes. It is important to note that thematic analysis is an iterative process, meaning that researchers may need to revisit and refine their analysis as they gain a deeper understanding of the data. This iterative approach allows for a more nuanced and comprehensive analysis of the themes and ensures that the analysis remains grounded in the data. 5.2.3 Validity and reliability in thematic analysis. Ensuring the validity and reliability of thematic analysis is crucial to maintain the rigor and credibility of the findings. Validity refers to the accuracy and truthfulness of the analysis, while reliability refers to the consistency and stability of the analysis. To enhance validity, researchers can employ various strategies, such as member checking, where participants are given the opportunity to review and provide feedback on the themes and interpretations. Researchers can also engage in peer debriefing, where colleagues or experts in the field review and critique the analysis. Additionally, researchers can maintain an audit trail, documenting the decision-making process and providing a transparent account of the analysis. To enhance reliability, researchers can employ techniques such as intercoder reliability, where multiple coders independently analyze the data and compare their findings. This helps to ensure that the themes and interpretations are consistent across different coders. Researchers can also use software programs to assist with the analysis, which can help to enhance the reliability and consistency of the coding process. 5.2.4 Reporting thematic analysis. Reporting thematic analysis involves presenting the findings in a clear and coherent manner. Researchers should provide a detailed description of the analysis process, including the steps taken, the techniques used, and the decisions made. They should also provide a comprehensive account of the themes, including their definitions, examples, and relationships. In addition to describing the themes, researchers should also discuss the implications and significance of the findings. They should consider how the themes relate to existing theories or literature, and they should discuss any new insights or contributions that the analysis has made. Researchers should also acknowledge any limitations or potential biases in the analysis and provide recommendations for future research. Overall, thematic analysis is a valuable qualitative data analysis method that allows researchers to explore and understand the rich and complex nature of qualitative data. By identifying and analyzing themes, researchers can gain insights into the meanings, patterns, and relationships within the data. Thematic analysis provides a flexible and systematic approach to analyzing qualitative data and can be applied to a wide range of research questions and contexts. 5.3 Content analysis. Content analysis is a research method used to analyze qualitative data in a systematic and objective manner. It involves the examination and interpretation of textual, visual, or audio content to identify patterns, themes, and meanings. Content analysis is widely used in various fields, including social sciences, communication studies, marketing, and media studies. In this section, we will explore the process of content analysis, its applications, and the steps involved in conducting a content analysis study. 5.3.1 Understanding content analysis. Content analysis is a valuable tool for researchers who want to gain insights from qualitative data. It allows researchers to analyze large volumes of data efficiently and identify recurring themes, patterns, and trends. By systematically categorizing and coding the content, researchers can draw meaningful conclusions and make inferences about the data. Content analysis can be applied to various types of data, including written documents, interviews, speeches, social media posts, advertisements, and visual media such as photographs or videos. It provides a structured approach to analyze and interpret the content, making it easier to compare and contrast different sources of data. 5.3.2 Steps in conducting content analysis. Conducting a content analysis study involves several key steps. These steps ensure that the analysis is systematic, reliable, and valid. The following are the typical steps involved in conducting content analysis. Defining the research question. The first step in content analysis is to clearly define the research question or objective. This helps in determining the scope of the analysis and the specific content to be analyzed. Selecting the sample. Content analysis often involves analyzing a large volume of data. Therefore, it is important to select a representative sample that reflects the population of interest. The sample can be randomly selected or purposefully chosen based on specific criteria. Developing coding categories. Coding categories are the building blocks of content analysis. They represent the themes, concepts, or variables that the researcher wants to analyze. The coding categories should be comprehensive, mutually exclusive, and clearly defined to ensure consistency in coding. Training coders. Content analysis often requires multiple coders to analyze the data. It is essential to train the coders to ensure inter-coder reliability. Training sessions should include discussions on coding rules, examples, and practice exercises to familiarize the coders with the coding categories. Coding the data. Once the coding categories are established, the coders can start coding the data. Coding involves systematically assigning the relevant codes to segments of the content based on the coding categories. This process can be done manually or by using software tools designed for content analysis. Analyzing the data. After coding the data, the next step is to analyze the coded content. This involves summarizing the data, identifying patterns, and exploring relationships between different codes or categories. Various statistical techniques can be used to analyze the data, such as frequency analysis, cross-tabulation, or thematic analysis. Interpreting the findings. The final step in content analysis is to interpret the findings. This involves drawing conclusions, making inferences, and discussing the implications of the analysis. The interpretation should be based on the patterns and themes identified in the data and should be supported by evidence from the content. 5.3.3 Applications of content analysis. Content analysis has a wide range of applications in research and practice. Some common applications include media analysis. Content analysis is often used to analyze media content, such as news articles, television programs, or social media posts. It helps researchers understand media representations, biases, and trends. Marketing research. Content analysis is used in marketing research to analyze customer reviews, social media conversations, or advertising campaigns. It helps companies gain insights into consumer preferences, brand perception, and market trends. Qualitative research. Content analysis is a valuable tool in qualitative research, where it helps researchers analyze interview transcripts, focus group discussions, or open-ended survey responses. It allows for a systematic analysis of qualitative data and the identification of recurring themes or patterns. Policy analysis. Content analysis is used in policy analysis to analyze policy documents, legislative texts, or public speeches. It helps researchers understand policy priorities, discourses, and the implementation of policies. Social sciences. Content analysis is widely used in social sciences to analyze historical documents, literature, or archival data. It helps researchers explore social, cultural, or political phenomena and understand their historical context. 5.3.4 Strengths and limitations of content analysis. Content analysis has several strengths that make it a valuable research method. Some of the strengths include efficiency. Content analysis allows researchers to analyze large volumes of data efficiently. It provides a systematic and structured approach to analyze qualitative data, saving time and effort. Objectivity. Content analysis aims to be objective and systematic in its approach. By using predefined coding categories and clear rules, it reduces the potential for bias and subjectivity in the analysis. Versatility. Content analysis can be applied to various types of data, including written, visual, or audio content. It can be used in different research fields and disciplines, making it a versatile research method. Despite its strengths, content analysis also has some limitations that researchers should consider. Subjectivity in coding. Despite efforts to be objective, content analysis involves some level of subjectivity in coding. Different coders may interpret the content differently, leading to variations in coding. Limited context. Content analysis focuses on the content itself and may not capture the full context in which the content was produced. It may miss important nuances or meanings that can only be understood in their broader context. Reliability and validity. Ensuring reliability and validity in content analysis can be challenging. Intercoder reliability should be established to ensure consistency in coding, and the validity of the findings should be supported by evidence from the content. In conclusion, content analysis is a valuable research method for analyzing qualitative data. It provides a systematic and objective approach to analyze large volumes of data and identify patterns, themes, and meanings. By following the steps outlined in this section, researchers can conduct content analysis studies effectively and draw meaningful conclusions from the data. 5.4 Grounded Theory. Grounded theory is a qualitative research method that aims to develop theories or explanations based on the data collected. Unlike other qualitative analysis approaches that start with preconceived theories or hypotheses, grounded theory allows researchers to derive theories directly from the data. This method is particularly useful when exploring complex social phenomena or when existing theories are limited or non-existent. 5.4.1 Overview of grounded theory. Grounded theory was developed by sociologists Barney Glaser and Anselm Strauss in the 1960s as a response to the limitations of traditional deductive research methods. The goal of grounded theory is to generate theories that are grounded in the data itself, rather than relying on preconceived notions or existing theories. It involves a systematic and iterative process of data collection, coding, and analysis to develop a theory that explains the observed phenomena. The key principle of grounded theory is constant comparison, which involves comparing new data with previously collected data to identify patterns, categories, and relationships. This iterative process allows researchers to refine their theories and develop a deeper understanding of the phenomenon under investigation. 5.4.2 Steps in grounded theory analysis. Grounded theory analysis typically involves several key steps. Data collection. The first step in grounded theory analysis is to collect relevant data. This can be done through various methods such as interviews, observations, or document analysis. The data collected should be rich and detailed to provide a comprehensive understanding of the phenomenon. Open coding. In this step, researchers analyze the data line by line and identify concepts or categories that emerge from the data. This process involves open coding, where researchers assign labels or codes to different parts of the data to capture the underlying meaning. Axial coding. Once the initial codes have been identified, researchers move on to axial coding. This involves categorizing and organizing the codes into broader themes or categories. Researchers also explore the relationships between different categories and identify any subcategories that may emerge. Selective coding. In the final stage of grounded theory analysis, researchers focus on developing a central theory that explains the phenomenon under investigation. This involves selectively coding the data to identify the core categories and their relationships. Researchers also look for any gaps or inconsistencies in the data and refine the theory accordingly. Throughout the analysis process, researchers engage in constant comparison, comparing new data with previously analyzed data to refine the emerging theory. This iterative process continues until theoretical saturation is reached, meaning that no new insights or categories are emerging from the data. 5.4.3 Advantages of grounded theory. Grounded theory offers several advantages for qualitative analysis. Flexibility. Grounded theory allows researchers to explore complex social phenomena in a flexible and iterative manner. It does not rely on preconceived theories or hypotheses, allowing for a more open and exploratory approach to data analysis. Theory development. Grounded theory enables researchers to develop theories directly from the data, providing a deeper understanding of the phenomenon under investigation. This can lead to the development of new theories or the refinement of existing ones. Rich and detailed analysis. Grounded theory analysis involves a thorough examination of the data, resulting in a rich and detailed understanding of the phenomenon. This can provide valuable insights and contribute to the existing body of knowledge. Contextual understanding. Grounded theory emphasizes the importance of understanding the context in which the phenomenon occurs. By analyzing the data in its natural context, researchers can gain a deeper understanding of the social, cultural, and environmental factors that influence the phenomenon. 5.4.4 Limitations of grounded theory. While grounded theory offers many advantages, it also has some limitations. Time-consuming. Grounded theory analysis can be a time-consuming process, as it involves multiple iterations of data collection, coding, and analysis. Researchers need to invest significant time and effort to ensure a thorough and comprehensive analysis. Subjectivity. Grounded theory analysis is subjective to some extent, as researchers interpret and code the data based on their own perspectives and biases. It is important for researchers to be aware of their own biases and take steps to minimize their influence on the analysis. Limited generalizability. Grounded theory aims to develop theories that are grounded in the specific context of the data. As such, the findings may have limited generalizability to other contexts or populations. However, the theories developed through grounded theory can serve as a basis for further research and theory development. Lack of reproducibility. Grounded theory analysis can be challenging to reproduce, as it relies heavily on the researcher's interpretation and coding of the data. It is important for researchers to document their analysis process and provide clear explanations of their coding decisions to enhance the transparency and reproducibility of the analysis. Despite these limitations, grounded theory remains a valuable qualitative research method for exploring complex social phenomena and generating theories directly from the data. It offers a flexible and iterative approach to analysis, allowing researchers to develop a deep and contextual understanding of the phenomenon under investigation. 6. Data visualization techniques. 6.1 Charts and graphs. Data visualization is a crucial aspect of data analysis as it allows us to present complex information in a clear and concise manner. Charts and graphs are powerful tools that help us visually represent quantitative and qualitative data, making it easier to understand patterns, trends, and relationships within the data. In this section, we will explore different types of charts and graphs commonly used in data analysis. 6.1.1 Bar charts. Bar charts are one of the most commonly used types of charts in data analysis. They are particularly useful for displaying categorical data and comparing the frequency or distribution of different categories. In a bar chart, each category is represented by a rectangular bar, with the height of the bar corresponding to the frequency or value of that category. Bar charts can be either vertical or horizontal, depending on the orientation of the bars. 6.1.2 Line charts. Line charts are ideal for visualizing trends and changes over time. They are particularly effective in displaying continuous data, such as stock prices, temperature variations, or population growth. In a line chart, data points are connected by lines, creating a continuous visual representation of the data. Line charts are especially useful for identifying patterns, trends, and fluctuations in the data over a specific time period. 6.1.3 Pie charts. Pie charts are commonly used to represent the composition or distribution of a whole. They are particularly effective in displaying categorical data and showing the proportion of each category in relation to the whole. In a pie chart, each category is represented by a slice of the pie, with the size of the slice corresponding to the proportion or percentage of that category. Pie charts are useful for quickly understanding the relative importance or contribution of different categories within a dataset. 6.1.4 Scatter plots. Scatter plots are used to visualize the relationship between two continuous variables. Each data point is represented by a dot on the graph, with the x-axis representing one variable and the y-axis representing the other variable. Scatter plots are useful for identifying patterns, trends, and correlations between variables. They can also help in detecting outliers or anomalies within the data. 6.1.5 Histograms. Histograms are used to display the distribution of continuous or interval data. They are similar to bar charts, but instead of representing categories, histograms represent ranges or intervals of data. The x-axis represents the range of values, while the y-axis represents the frequency or count of data points falling within each range. Histograms are useful for understanding the shape, central tendency, and spread of a dataset. 6.1.6 Box plots. Box plots, also known as box and whisker plots, are used to display the distribution of a dataset and identify outliers. They provide a visual summary of the minimum, first quartile, median, third quartile, and maximum values of a dataset. The box in the plot represents the interquartile range (IQR), which contains the middle 50% of the data. The whiskers extend from the box to the minimum and maximum values, excluding outliers. Box plots are useful for comparing distributions and identifying any unusual observations in the data. 6.1.7 Heat maps. Heat maps are effective for visualizing large datasets and identifying patterns or relationships between variables. They use color gradients to represent the magnitude or intensity of a variable across different categories or time periods. Heat maps are particularly useful in analyzing data with multiple dimensions, such as gene expression data, customer behavior data, or geographical data. By using different color scales, heat maps can highlight areas of high or low values, making it easier to identify patterns or clusters within the data. 6.1.8 Area charts. Area charts are similar to line charts but with the area below the line filled with color. They are useful for visualizing cumulative data or comparing the contribution of different categories over time. Area charts are particularly effective in showing the overall trend and the relative importance of different categories within a dataset. They are commonly used in financial analysis, market research, and sales forecasting. 6.1.9 Bubble charts. Bubble charts are used to display three-dimensional data, where the size of the bubble represents the value of a variable, and the x and y coordinates represent two other variables. Bubble charts are useful for visualizing relationships between variables and identifying clusters or patterns within the data. They are commonly used in social sciences, economics, and market research to analyze complex datasets with multiple dimensions. In conclusion, charts and graphs are essential tools in data analysis as they allow us to visually represent and interpret quantitative and qualitative data. Each type of chart or graph has its own strengths and is suitable for different types of data and analysis objectives. By choosing the appropriate chart or graph, we can effectively communicate insights, patterns, and trends within the data to a wide range of audiences. 6.2 Infographics. Infographics are powerful visual representations of data that combine text, images, and graphics to convey complex information in a clear and concise manner. They are widely used in various fields, including data analysis, to present data in a visually appealing and easily understandable format. In this section, we will explore the concept of infographics and how they can be effectively used in data analysis. 6.2.1 What are infographics? Infographics are visual representations of data that use a combination of text, images, and graphics to present information in a visually appealing and easily understandable format. They are designed to convey complex information quickly and efficiently, making them an effective tool for data analysis. Infographics can be used to present both quantitative and qualitative data, allowing analysts to communicate their findings in a visually engaging way. 6.2.2 Benefits of using infographics in data analysis. There are several benefits to using infographics in data analysis. Simplifies complex information. Infographics simplify complex data by presenting it in a visually appealing and easy to understand format. By condensing large amounts of information into a concise visual representation, infographics make it easier for viewers to grasp key insights and trends. Enhances data visualization. Infographics enhance data visualization by using visual elements such as charts, graphs, and icons to represent data. This visual representation makes it easier for viewers to interpret and understand the data, as compared to traditional text-based reports. Increases engagement. Infographics are visually engaging and capture the attention of viewers. By presenting data in a visually appealing manner, infographics can increase viewer engagement and interest in the data analysis findings. Improves retention. Infographics are more memorable than plain text, as they combine visual elements with information. This improves the retention of information and makes it easier for viewers to recall key findings from the data analysis. Facilitates data comparison. Infographics allow for easy comparison of data by using visual elements such as bar charts, line graphs, and pie charts. This enables viewers to quickly identify patterns, trends, and relationships between different data points. Promotes data-driven decision-making. Infographics provide a clear and concise representation of data, enabling decision-makers to make informed choices based on the insights derived from the data analysis. By presenting data in a visually appealing manner, infographics facilitate data-driven decision-making. 6.2.3 Designing effective infographics for data analysis. To create effective infographics for data analysis, it is important to consider the following design principles. Simplicity. Keep the design simple and avoid clutter. Use clear and concise language, and limit the amount of text to essential information. Focus on the key insights and trends that need to be communicated. Visual hierarchy. Use visual hierarchy to guide the viewer's attention. Highlight important information using larger fonts, bold text, or contrasting colors. Use visual cues such as arrows or icons to direct the viewer's gaze. Consistency. Maintain consistency in the design elements such as colors, fonts, and icons throughout the infographic. This creates a cohesive visual experience and makes it easier for viewers to understand the information. Balance. Ensure a balanced distribution of text and visuals. Avoid overcrowding the infographic with too much information. Use white space effectively to create a visually pleasing layout. Accessibility. Consider the accessibility of the infographic by using appropriate color schemes and providing alternative text for images. Ensure that the infographic is readable for individuals with visual impairments. Storytelling. Infographics should tell a story and guide the viewer through the data analysis process. Use a logical flow and narrative structure to present the information in a coherent and engaging manner. 6.2.4 Tools for creating infographics. There are several tools available that can help you create visually appealing and professional-looking infographics for data analysis. Some popular tools include Canva. Canva is a user-friendly online design tool that offers a wide range of templates, graphics, and fonts to create stunning infographics. Adobe Illustrator. Adobe Illustrator is a professional design software that provides advanced features for creating custom infographics. It offers a wide range of tools and options for precise design control. Pictochart. Pictochart is an online infographic maker that offers a drag-and-drop interface and a library of templates, icons, and images to create visually appealing infographics. Venngage. Venngage is an online tool that provides a variety of templates and design options to create infographics. It also offers data visualization features to present data in a visually engaging manner. Microsoft PowerPoint. PowerPoint is a widely used presentation software that can also be used to create simple infographics. It offers a range of design options and allows for easy integration of charts and graphs. When selecting a tool, consider your design skills, budget, and the specific requirements of your data analysis project. 6.2.5 Tips for using infographics in data analysis. Here are some tips to effectively use infographics in data analysis. Know your audience. Understand the target audience and tailor the infographic design and content to their needs and preferences. Consider their level of familiarity with data analysis concepts and their visual literacy. Focus on key insights. Highlight the most important findings and insights from the data analysis. Avoid overwhelming the viewer with excessive information. Keep the infographic focused and concise. Use appropriate visual elements. Select the appropriate charts, graphs, and icons to represent the data accurately. Choose visuals that best convey the message and make it easier for viewers to understand the information. Tell a story. Structure the infographic in a logical and coherent manner. Guide the viewer through the data analysis process by presenting the information in a narrative format. Use headings and subheadings to create a clear flow of information. Test and iterate. Test the effectiveness of the infographic by seeking feedback from colleagues or potential viewers. Iterate on the design based on the feedback received to improve the clarity and impact of the infographic. By following these tips and incorporating infographics into your data analysis process, you can effectively communicate complex information and engage your audience in a visually compelling way. Infographics provide a powerful tool for presenting data analysis findings and facilitating data-driven decision-making. 6.3 Dashboards. Dashboards are powerful tools that allow data analysts and decision-makers to visualize and monitor key performance indicators, KPIs, and metrics in real time. They provide a comprehensive and interactive view of data, enabling users to quickly and easily understand trends, patterns, and insights. In this section, we will explore the concept of dashboards, their benefits, and best practices for designing effective dashboards. 6.3.1 What are dashboards? Dashboards are visual representations of data that consolidate and display information in a clear and concise manner. They typically consist of a collection of charts, graphs, tables, and other visual elements that provide an overview of key metrics and performance indicators. Dashboards can be customized to suit the specific needs of different users and organizations, allowing them to focus on the most relevant data for their decision-making processes. 6.3.2 Benefits of dashboards. Dashboards offer several benefits for data analysis and decision-making. Data visualization. Dashboards provide a visual representation of data, making it easier to understand complex information and identify trends and patterns. Real-time monitoring. Dashboards can be updated in real time, allowing users to monitor KPIs and metrics as they change. This enables timely decision-making and the ability to respond quickly to emerging trends or issues. Data integration. Dashboards can integrate data from multiple sources, such as databases, spreadsheets, and online platforms. This allows users to consolidate data from different systems into a single view, providing a holistic perspective on performance. Interactivity. Dashboards often include interactive features that allow users to drill down into specific data points, filter information, and explore different visualizations. This interactivity enhances the user experience and enables deeper analysis. Collaboration. Dashboards can be shared with team members and stakeholders, facilitating collaboration and alignment. By providing a common view of data, dashboards promote data-driven discussions and decision-making. Efficiency. Dashboards eliminate the need for manual data analysis and reporting, saving time and effort. With automated data updates and visualizations, users can focus on analyzing insights and taking action, rather than spending time on data preparation. 6.3.3 Designing effective dashboards. To create effective dashboards, it is important to consider the following best practices. Define objectives. Clearly define the objectives and purpose of the dashboard. Identify the key metrics and KPIs that need to be monitored and determine the target audience for the dashboard. Keep it simple. Avoid clutter and complexity by focusing on the most important information. Use clear and concise visualizations that are easy to understand at a glance. Choose the right visualizations. Select visualizations that best represent the data and effectively communicate the intended message. Consider the type of data being presented and choose appropriate charts, graphs, and tables. Use consistent design elements. Maintain consistency in design elements such as color schemes, fonts, and layout. This helps users navigate the dashboard and understand the information more easily. Provide context. Provide context and explanations for the data being presented. Include titles, captions, and annotations to guide users and ensure they understand the meaning and significance of the data. Ensure data accuracy. Ensure that the data displayed on the dashboard is accurate and up to date. Implement data validation and cleaning processes to minimize errors and inconsistencies. Enable interactivity. Incorporate interactive features such as filters, drill-down options, and tooltips to allow users to explore the data in more detail. This enhances user engagement and facilitates deeper analysis. Consider responsiveness. Design dashboards that are responsive and adaptable to different devices and screen sizes. This ensures that users can access and view the dashboard effectively on desktops, laptops, tablets, and mobile devices. Regularly review and update. Regularly review the dashboard to ensure it remains relevant and aligned with the evolving needs of the organization. Update the dashboard as new data becomes available or when changes in metrics or KPIs occur. 6.3.4 Examples of dashboards. There are various types of dashboards that can be used for different purposes and industries. Here are a few examples. Sales dashboard. A sales dashboard may include visualizations of sales revenue, customer acquisition, conversion rates, and sales pipeline. It provides insights into sales performance and helps identify areas for improvement. Marketing dashboard. A marketing dashboard may display metrics such as website traffic, conversion rates, social media engagement, and campaign performance. It enables marketers to track the effectiveness of their marketing efforts and make data-driven decisions. Financial dashboard. A financial dashboard may include visualizations of key financial indicators such as revenue, expenses, profitability, and cash flow. It provides a comprehensive view of the financial health of an organization. Operational dashboard. An operational dashboard may focus on operational metrics such as production output, quality control, inventory levels, and customer satisfaction. It helps monitor and optimize operational processes. Conclusion. Dashboards are valuable tools for data analysis and decision-making. They provide a visual representation of data, enabling users to monitor key metrics and performance indicators in real time. By following best practices in dashboard design, organizations can create effective dashboards that facilitate data-driven decision-making and enhance overall performance. 6.4 Interactive visualizations. Interactive visualizations are a powerful tool in data analysis that allows users to explore and interact with data in a dynamic and engaging way. Unlike static visualizations, interactive visualizations enable users to manipulate and customize the display of data, providing a more immersive and personalized experience. In this section, we will explore the benefits and techniques of interactive visualizations in data analysis. 6.4.1 Benefits of interactive visualizations. Interactive visualizations offer several advantages over traditional static visualizations. Here are some key benefits. Enhanced exploration. Interactive visualizations allow users to drill down into the data, zoom in on specific details, and filter data based on different criteria. This enables users to gain deeper insights and discover patterns and trends that may not be apparent in static visualizations. Improved understanding. By interacting with the data, users can manipulate variables, change parameters, and observe the immediate impact on the visualization. This hands-on approach helps users develop a better understanding of the data and its underlying relationships. Increased engagement. Interactive visualizations are more engaging and captivating than static visualizations. Users can actively participate in the analysis process, making it more enjoyable and stimulating. This increased engagement can lead to better retention of information and a more immersive learning experience. Customization and personalization. Interactive visualizations allow users to customize the display of data according to their preferences. They can choose different chart types, color schemes, and layouts, making the visualization more visually appealing and tailored to their specific needs. Real-time feedback. Interactive visualizations provide real-time feedback, allowing users to see the immediate impact of their actions. This instant feedback loop enables users to make quick adjustments and iterate on their analysis, leading to faster insights and more efficient decision-making. 6.4.2 Techniques for interactive visualizations. There are various techniques and tools available for creating interactive visualizations. Here are some commonly used techniques. Hover and tooltip. This technique involves displaying additional information when the user hovers over a data point or element in the visualization. Tooltips can provide details such as the exact value, label, or description, enhancing the user's understanding of the data. Filtering and selection. Interactive visualizations often include filtering and selection options that allow users to focus on specific subsets of data. Users can choose to display or hide certain categories, time periods, or variables, enabling them to explore different aspects of the data. Zooming and panning. Zooming and panning functionality allows users to zoom in on specific areas of the visualization or pan across the entire dataset. This technique is particularly useful when dealing with large datasets or when users want to examine specific details in the data. Interactive controls. Interactive controls, such as sliders, buttons, and drop-down menus, enable users to manipulate variables or parameters in real time. Users can adjust these controls to see how changes affect the visualization, allowing for dynamic exploration and analysis. Linked views. Linked views connect multiple visualizations together, enabling users to interact with one visualization and see the corresponding changes in other linked visualizations. This technique facilitates the exploration of multidimensional data and helps users uncover complex relationships between variables. Animations and transitions. Animations and transitions can be used to guide the user's attention and highlight changes in the data. By animating the visualization, users can observe how the data evolves over time or in response to different actions, making it easier to understand patterns and trends. 6.4.3 Tools for interactive visualizations. There are several tools and libraries available for creating interactive visualizations. Here are some popular ones. D3.js. D3.js is a powerful JavaScript library for creating interactive and dynamic visualizations. It provides a wide range of tools and functions for manipulating data and generating custom visualizations. D3.js allows for fine-grained control over the visualization's behavior and appearance. Tableau. Tableau is a widely used data visualization tool that offers a user-friendly interface for creating interactive visualizations. It provides a drag-and-drop interface, making it easy to create complex visualizations without writing code. Tableau also offers a variety of interactive features and allows for seamless integration with other data analysis tools. Plotly is a Python library that provides interactive and customizable visualizations. It offers a wide range of chart types and allows users to create interactive plots with just a few lines of code. Plotly also supports collaboration and sharing of visualizations through its online platform. Power BI is a business intelligence tool that enables users to create interactive visualizations and dashboards. It offers a drag-and-drop interface and provides a wide range of visualization options. Power BI also allows for real-time data updates and integration with other Microsoft products. ggplot2 is an R package that provides a grammar of graphics for creating interactive visualizations. It follows a layered approach, allowing users to add and modify different components of the visualization. ggplot2 offers a high level of customization and is widely used in the R community. 6.4.4 Best Practices for Interactive Visualizations. When creating interactive visualizations, it is important to follow best practices to ensure a positive user experience and effective data analysis. Here are some best practices to consider. Keep it simple. Avoid cluttering the visualization with too many interactive elements. Focus on the most important features and provide clear instructions on how to interact with the visualization. Provide context. Include labels, legends, and captions to provide context and help users understand the meaning of the visualization. Provide tooltips or additional information to explain any complex concepts or terms. Test and iterate. Test the interactive visualization with different users to gather feedback and identify areas for improvement. Iterate on the design based on user feedback to create a more intuitive and user-friendly experience. Consider accessibility. Ensure that the interactive visualization is accessible to users with disabilities. Provide alternative text for images, use high-contrast colors, and ensure that the visualization can be navigated using keyboard controls. Optimize performance. Interactive visualizations can be resource-intensive, especially when dealing with large datasets. Optimize the performance of the visualization by using data aggregation, pre-computing calculations, and implementing lazy loading techniques. Interactive visualizations are a valuable tool in data analysis, allowing users to explore and interact with data in a dynamic and engaging way. By leveraging the benefits of interactive visualizations and following best practices, analysts can gain deeper insights, improve understanding, and make more informed decisions based on their data. 7. Data mining and machine learning. 7.1 Data mining concepts. Data mining is a process of discovering patterns, relationships, and insights from large datasets. It involves the use of various techniques and algorithms to extract valuable information and knowledge from data. In this section, we will explore the fundamental concepts of data mining and its applications in the field of data analysis. 7.1.1 Definition of data mining. Data mining is the process of analyzing large datasets to uncover hidden patterns, relationships, and trends that can be used to make informed decisions. It involves the use of statistical and mathematical techniques to extract meaningful information from data. Data mining techniques can be applied to various types of data, including structured, unstructured, and semi-structured data. 7.1.2 Data mining process. The data mining process consists of several steps that are followed to extract useful information from data. These steps include data collection. The first step in the data mining process is to collect relevant data from various sources. This can include structured data from databases, unstructured data from text documents, or semi-structured data from web pages. Data preprocessing. Once the data is collected, it needs to be preprocessed to remove any inconsistencies, errors, or missing values. This step involves data cleaning, data integration, data transformation, and data reduction. Data exploration. In this step, the data is explored to gain a better understanding of its characteristics. This can involve the use of descriptive statistics, data visualization techniques, and exploratory data analysis. Model building. After exploring the data, the next step is to build a data mining model. This involves selecting an appropriate algorithm or technique that is suitable for the specific data mining task. The model is trained using the available data to learn patterns and relationships. Model evaluation. Once the model is built, it needs to be evaluated to assess its performance. This can be done by comparing the predicted results with the actual results or by using various evaluation metrics such as accuracy, precision, recall, and F1 score. Model deployment. After the model is evaluated and deemed satisfactory, it can be deployed for use in real-world applications. This involves integrating the model into existing systems or developing new applications based on the insights gained from the data mining process. 7.1.3 Data mining techniques. There are various data mining techniques that can be used to extract valuable information from data. Some of the commonly used techniques include classification. Classification is a technique used to categorize data into predefined classes or categories. It involves the use of algorithms such as decision trees, logistic regression, and support vector machines to classify data based on their attributes. Clustering. Clustering is a technique used to group similar data points together based on their characteristics. It involves the use of algorithms such as k-means clustering, hierarchical clustering, and density-based clustering to identify clusters or groups in the data. Association rule mining. Association rule mining is a technique used to discover interesting relationships or associations between items in a dataset. It involves the use of algorithms such as a priori and FP growth to find frequent item sets and generate association rules. Anomaly detection. Anomaly detection is a technique used to identify unusual or abnormal patterns in data. It involves the use of algorithms such as outlier detection, clustering-based anomaly detection, and statistical methods to detect anomalies in the data. Regression analysis. Regression analysis is a technique used to predict a continuous target variable based on the values of one or more predictor variables. It involves the use of algorithms such as linear regression, polynomial regression, and support vector regression to build regression models. Text mining. Text mining is a technique used to extract useful information from unstructured text data. It involves the use of natural language processing techniques, sentiment analysis, and topic modeling to analyze and extract insights from text documents. 7.1.4 Applications of data mining. Data mining has a wide range of applications in various fields. Some of the common applications include customer segmentation. Data mining techniques can be used to segment customers based on their purchasing behavior, demographics, or preferences. This can help businesses target specific customer groups with personalized marketing campaigns. Fraud detection. Data mining can be used to detect fraudulent activities or transactions by analyzing patterns and anomalies in the data. This is particularly useful in the banking and financial industry to identify potential fraud cases. Healthcare analytics. Data mining techniques can be used to analyze patient data and medical records to identify patterns and trends. This can help in disease diagnosis, treatment planning, and predicting patient outcomes. Market basket analysis. Data mining techniques can be used to analyze customer purchase data to identify associations between products. This can help businesses in cross-selling and upselling strategies. Social media analysis. Data mining techniques can be used to analyze social media data to understand customer sentiment, identify trends, and detect emerging topics or events. Predictive maintenance. Data mining techniques can be used to analyze sensor data from machines or equipment to predict maintenance needs and prevent unplanned downtime. In conclusion, data mining is a powerful tool in the field of data analysis that allows us to extract valuable insights and knowledge from large datasets. By applying various data mining techniques, we can uncover hidden patterns, relationships, and trends that can be used to make informed decisions and drive business success. 7.2 Supervised learning. Supervised learning is a powerful technique in data mining and machine learning that involves training a model on labeled data to make predictions or classify new, unseen data. In this chapter, we will explore the concept of supervised learning, its applications, and the different algorithms used in this approach. 7.2.1 Introduction to supervised learning. Supervised learning is a type of machine learning where the algorithm learns from a labeled dataset. Labeled data refers to data that has both input features and corresponding output labels. The goal of supervised learning is to build a model that can accurately predict the output labels for new, unseen data based on the patterns and relationships learned from the labeled dataset. The process of supervised learning involves two main steps: training and testing. During the training phase, the algorithm learns from the labeled dataset by identifying patterns and relationships between the input features and output labels. The algorithm then uses this knowledge to make predictions on new, unseen data during the testing phase. 7.2.2 Types of supervised learning algorithms. There are various types of supervised learning algorithms, each with its own strengths and weaknesses. Some of the most commonly used algorithms include 7.2.2.1 Linear regression. Linear regression is a simple yet powerful algorithm used for predicting continuous numerical values. It assumes a linear relationship between the input features and the output labels and tries to find the best fit line that minimizes the difference between the predicted and actual values. 7.2.2.2 Logistic regression. Logistic regression is a binary classification algorithm used to predict categorical outcomes. It estimates the probability of an event occurring based on the input features and assigns a binary label, e.g., 0 or 1, to each data point. 7.2.2.3 Decision trees. Decision trees are versatile algorithms that can be used for both classification and regression tasks. They create a tree-like model of decisions and their possible consequences based on the input features. Each internal node represents a feature, each branch represents a decision rule, and each leaf node represents the outcome. 7.2.2.4 Random forests. Random forests are an ensemble learning method that combines multiple decision trees to make predictions. Each tree in the random forest is trained on a random subset of the data, and the final prediction is made by aggregating the predictions of all the individual trees. 7.2.2.5 Support vector machines, SVM. Support vector machines are powerful algorithms used for both classification and regression tasks. They find the optimal hyperplane that separates the data into different classes or predicts continuous values. SVMs work by maximizing the margin between the classes, making them robust to outliers. 7.2.2.6 Naive Bayes. Naive Bayes is a probabilistic algorithm based on Bayes' theorem. It assumes that the input features are conditionally independent of each other given the output label. Naive Bayes is commonly used for text classification and spam filtering tasks. 7.2.2.7 Neural networks. Neural networks are a class of algorithms inspired by the structure and function of the human brain. They consist of interconnected nodes, or neurons, organized in layers. Each neuron applies a mathematical function to its inputs and passes the result to the next layer. Neural networks can be used for both regression and classification tasks and have gained popularity due to their ability to learn complex patterns. 7.2.3 Applications of supervised learning. Supervised learning has a wide range of applications across various domains. Some common applications include 7.2.3.1 Predictive analytics. Supervised learning is widely used in predictive analytics to forecast future trends and make informed decisions. For example, it can be used to predict customer churn, stock prices, or demand for a product based on historical data. 7.2.3.2 Image and speech recognition. Supervised learning algorithms, particularly neural networks, have been successful in image and speech recognition tasks. They can learn to identify objects, faces, or speech patterns by training on large labeled datasets. 7.2.3.3 Fraud detection. Supervised learning algorithms can be used to detect fraudulent activities by learning patterns from historical data. For example, credit card companies use supervised learning to identify suspicious transactions and prevent fraud. 7.2.3.4 Medical diagnosis. Supervised learning algorithms have been applied to medical diagnosis tasks, such as predicting the likelihood of a disease based on patient symptoms and medical history. These algorithms can assist healthcare professionals in making accurate diagnoses and treatment decisions. 7.2.4 Model evaluation and selection. Once a supervised learning model is trained, it is essential to evaluate its performance and select the best model for deployment. Various evaluation metrics can be used, depending on the type of problem and the desired outcome. Some common evaluation metrics include accuracy, precision, recall, F1 score, an area under the receiver operating characteristic curve AUC-ROC. Cross-validation is a widely used technique for evaluating the performance of supervised learning models. It involves splitting the labeled dataset into multiple subsets, training the model on a subset, and evaluating its performance on the remaining subset. This process is repeated multiple times, and the average performance is calculated. Model selection involves comparing the performance of different models and selecting the one that performs the best on the evaluation metrics. It is important to consider factors such as model complexity, interpretability, and computational efficiency when selecting a model. In conclusion, supervised learning is a fundamental concept in data mining and machine learning. It allows us to build models that can make accurate predictions or classify new, unseen data based on patterns learned from labeled datasets. There are various types of supervised learning algorithms, each with its own strengths and applications. Evaluating and selecting the best model is crucial for ensuring the accuracy and reliability of the predictions. 7.3 Unsupervised learning. Unsupervised learning is a branch of machine learning that focuses on finding patterns and relationships in data without the need for labeled or pre-classified examples. Unlike supervised learning, where the algorithm is provided with labeled data to learn from, unsupervised learning algorithms work within labeled data and aim to discover hidden structures or patterns within the data. 7.3.1 Clustering. One of the most common techniques used in unsupervised learning is clustering. Clustering algorithms group similar data points together based on their characteristics or attributes. The goal is to identify natural groupings or clusters within the data, where data points within the same cluster are more similar to each other than to those in other clusters. There are various clustering algorithms available, each with its own strengths and weaknesses. Some popular clustering algorithms include k-means clustering, hierarchical clustering, and density-based clustering. These algorithms use different approaches to define the similarity or distance between data points and determine the optimal number of clusters. Clustering has a wide range of applications in various fields, such as customer segmentation in marketing, image segmentation in computer vision, and anomaly detection in cybersecurity. By identifying similar groups within a dataset, clustering can help uncover patterns, segment data into meaningful subsets, and provide insights for decision-making. 7.3.2 Dimensionality reduction. Another important technique in unsupervised learning is dimensionality reduction. In many real-world datasets, the number of features or variables can be large, making it difficult to visualize and analyze the data effectively. Dimensionality reduction methods aim to reduce the number of variables while preserving the important information and structure of the data. Principal component analysis (PCA) is a widely used dimensionality reduction technique. It transforms the original variables into a new set of uncorrelated variables called principal components. These principal components are ordered in terms of their importance, with the first component explaining the most variance in the data. By selecting a subset of the principal components, the dimensionality of the data can be reduced while retaining most of the information. Dimensionality reduction techniques are particularly useful in data visualization, as they allow for the representation of high-dimensional data in lower-dimensional spaces. They can also help improve the performance of machine learning algorithms by reducing the complexity and noise in the data. 7.3.3 Association rule mining. Association rule mining is another unsupervised learning technique that focuses on discovering interesting relationships or associations between variables in a dataset. It is commonly used in market basket analysis, where the goal is to identify patterns of co-occurrence or association between items in a transactional dataset. The most well-known algorithm for association rule mining is the a priori algorithm. It works by generating frequent item sets, which are sets of items that appear together in a significant number of transactions. From these frequent item sets, association rules are derived, which express the relationships between items in terms of if-then statements. Association rules are typically evaluated based on measures such as support, confidence, and lift. Support measures the frequency of occurrence of an item set, confidence measures the conditional probability of the consequent given the antecedent, and lift measures the strength of the association between the antecedent and consequent. Association rule mining can provide valuable insights into consumer behavior, product recommendations, and market segmentation. By identifying associations between items, businesses can optimize their marketing strategies, improve cross-selling opportunities, and enhance customer satisfaction. 7.3.4 Anomaly detection. Anomaly detection, also known as outlier detection, is the process of identifying data points that deviate significantly from the normal or expected behavior of the dataset. Unsupervised learning techniques can be used to detect anomalies by modeling the normal patterns in the data and identifying instances that do not conform to these patterns. There are several approaches to anomaly detection, including statistical methods, clustering-based methods, and density-based methods. Statistical methods assume that the normal data follows a specific statistical distribution and identify outliers based on deviations from this distribution. Clustering-based methods identify outliers as data points that do not belong to any cluster or belong to small clusters. Density-based methods identify outliers as data points that have low density compared to their neighbors. Anomaly detection has numerous applications in various domains, such as fraud detection in finance, network intrusion detection in cybersecurity, and equipment failure prediction in manufacturing. By identifying anomalies, organizations can take proactive measures to mitigate risks, improve system reliability, and enhance overall performance. 7.3.5 Advantages and limitations of unsupervised learning. Unsupervised learning offers several advantages in data analysis. It allows for the exploration and discovery of hidden patterns or structures in data without the need for labeled examples. Unsupervised learning techniques can handle large and complex datasets, making them suitable for big data analytics. They can also be used as a preprocessing step to extract meaningful features or reduce the dimensionality of the data before applying supervised learning algorithms. However, unsupervised learning also has its limitations. Since there are no predefined labels or targets, the evaluation of unsupervised learning models can be challenging. The interpretation of the results can be subjective and dependent on the domain knowledge of the analyst. Unsupervised learning algorithms may also be sensitive to the quality and noise in the data, requiring careful preprocessing and cleaning steps. Despite these limitations, unsupervised learning techniques play a crucial role in data analysis by providing valuable insights, uncovering hidden patterns, and enabling decision-making in various domains. By leveraging the power of unsupervised learning, analysts can gain a deeper understanding of their data and extract meaningful information that can drive business success. 7.4 Model evaluation and selection. Once we have built and trained our models using data mining and machine learning techniques, it is crucial to evaluate their performance and select the best model for our analysis. Model evaluation and selection play a significant role in ensuring the accuracy and reliability of our predictions or classifications. 7.4.1 Evaluation metrics. To assess the performance of a model, we need to use appropriate evaluation metrics that measure its effectiveness in making predictions or classifications. The choice of evaluation metrics depends on the nature of the problem and the type of model being evaluated. Here are some commonly used evaluation metrics. Accuracy. Accuracy measures the proportion of correct predictions or classifications made by the model. It is calculated by dividing the number of correct predictions by the total number of predictions. However, accuracy alone may not be sufficient in cases where the dataset is imbalanced or when the cost of misclassification varies across different classes. Precision. Precision measures the proportion of true positive predictions among all positive predictions made by the model. It is calculated by dividing the number of true positives by the sum of true positives and false positives. Precision is particularly useful when the focus is on minimizing false positives. Recall, also known as sensitivity or true positive rate, measures the proportion of true positive predictions among all actual positive instances in the dataset. It is calculated by dividing the number of true positives by the sum of true positives and false negatives. Recall is important when the emphasis is on minimizing false negatives. F1 score. The F1 score is the harmonic mean of precision and recall. It provides a balanced measure of a model's performance by considering both precision and recall. The F1 score is calculated as 2 precision * recall, precision plus recall. ROC curve and AUC. the receiver operating characteristic ROC curve is a graphical representation of the trade-off between the true positive rate, sensitivity, and the false positive rate, 1 specificity for different classification thresholds. The area under the curve AUC summarizes the performance of the model across all possible thresholds. A higher AUC indicates better performance. Mean squared error MSE. MSE is a common evaluation metric for regression models. It measures the average squared difference between the predicted and actual values. Lower MSE values indicate better model performance. R squared, also known as the coefficient of determination, measures the proportion of the variance in the dependent variable that is predictable from the independent variables. It ranges from 0 to 1, with higher values indicating a better fit of the model to the data. 7.4.2 Cross-validation. Cross-validation is a technique used to assess the performance of a model on unseen data. It involves splitting the dataset into multiple subsets or folds, training the model on a subset of the data, and evaluating its performance on the remaining fold. This process is repeated multiple times, with each fold serving as the test set once. The results from each iteration are then averaged to obtain a more robust estimate of the model's performance. The most commonly used cross-validation technique is k-fold cross-validation, where the dataset is divided into k equal-sized folds. The model is trained on k1 folds and evaluated on the remaining fold. This process is repeated k times, with each fold serving as the test set once. The performance metrics obtained from each iteration can be averaged to obtain a more reliable estimate of the model's performance. Cross-validation helps to assess the generalization ability of the model and provides insights into its stability and reliability. It also helps in identifying potential issues such as overfitting or underfitting. By evaluating the model on multiple subsets of the data, cross-validation provides a more comprehensive assessment of its performance. 7.4.3 Model selection. After evaluating the performance of different models using appropriate evaluation metrics and cross-validation techniques, we need to select the best model for our analysis. The choice of the model depends on various factors, including the problem at hand, the available data, and the specific requirements of the analysis. When selecting a model, it is important to consider both its performance and its interpretability. A highly accurate model may not always be the best choice if it is difficult to interpret or explain. On the other hand, a simple and interpretable model may not always provide the highest accuracy. The trade-off between accuracy and interpretability needs to be carefully considered based on the specific requirements of the analysis. In addition to performance and interpretability, other factors such as computational complexity, scalability, and implementation feasibility should also be taken into account. Some models may be computationally expensive or may require large amounts of memory, which may not be feasible in certain scenarios. It is also important to keep in mind that model selection is an iterative process. As new data becomes available or the problem evolves, it may be necessary to re-evaluate and update the selected model. Regular monitoring and evaluation of the model's performance are essential to ensure its continued effectiveness. In conclusion, model evaluation and selection are critical steps in the data analysis process. By using appropriate evaluation metrics, cross-validation techniques, and considering factors such as performance, interpretability, and feasibility, we can choose the best model for our analysis. Regular monitoring and evaluation of the selected model are essential to ensure its continued effectiveness and adaptability to changing circumstances. 8. Big Data Analytics. 8.1 Introduction to Big Data. In today's digital age, the amount of data being generated is growing at an unprecedented rate. This massive volume of data, known as big data, presents both challenges and opportunities for organizations across various industries. Big data refers to datasets that are too large and complex to be processed and analyzed using traditional data processing techniques. The field of big data analytics has emerged to address the unique characteristics and requirements of big data. 8.1.1 What is big data? Big data is characterized by the 3 V's: volume, velocity, and variety. Volume refers to the sheer amount of data being generated, which can range from terabytes to petabytes and beyond. Velocity refers to the speed at which data is being generated, often in real time or near real time. Variety refers to the diverse types of data being generated, including structured data e.g., databases, unstructured data e.g., text, images, videos, and semi-structured data e.g., XML, JSON. Big data is generated from various sources, such as social media platforms, sensors, mobile devices, and online transactions. This data can provide valuable insights and opportunities for organizations to improve decision-making, optimize operations, and gain a competitive advantage. However, the sheer volume and complexity of big data pose significant challenges in terms of storage, processing, analysis, and interpretation. 8.1.2 Data Storage and Processing. Traditional data storage and processing systems are not designed to handle the scale and complexity of big data. As a result, new technologies and architectures have emerged to address these challenges. One such technology is distributed file systems, which allow data to be stored across multiple servers or nodes in a cluster. This distributed storage approach enables scalability, fault tolerance, and high availability. Another key technology in big data analytics is distributed processing frameworks, such as Apache Hadoop and Apache Spark. These frameworks provide a scalable and fault-tolerant platform for processing and analyzing big data. They leverage the distributed storage infrastructure to parallelize data processing tasks across multiple nodes, enabling faster and more efficient analysis. In addition to distributed file systems and processing frameworks, organizations also utilize cloud computing platforms to store and process big data. Cloud platforms offer the advantage of scalability, flexibility, and cost-effectiveness, as they allow organizations to pay for the resources they need on demand. 8.1.3 Data Analysis Techniques for Big Data. Analyzing big data requires specialized techniques and algorithms that can handle the volume, velocity, and variety of the data. Traditional statistical methods and machine learning algorithms may not be suitable for big data due to their computational limitations. Therefore, new approaches have been developed to address the unique characteristics of big data. One such approach is parallel processing, which involves dividing the data and processing tasks into smaller subsets that can be analyzed concurrently. This parallelization allows for faster analysis and enables organizations to leverage the power of distributed computing. Another technique used in big data analytics is data sampling. Sampling involves selecting a representative subset of the data for analysis, rather than analyzing the entire dataset. This approach helps reduce the computational requirements and allows for faster analysis while still providing meaningful insights. Machine learning algorithms, such as deep learning and neural networks, are also commonly used in big data analytics. These algorithms can automatically learn patterns and relationships from large volumes of data, enabling organizations to make predictions and take data-driven actions. Furthermore, data visualization plays a crucial role in big data analytics. Visualizing big data helps in understanding patterns, trends, and outliers that may not be apparent from raw data. Interactive visualizations allow users to explore and interact with the data, gaining deeper insights and facilitating decision-making. 8.1.4 Challenges and Opportunities in Big Data Analytics. While big data analytics offers immense opportunities, it also presents several challenges that organizations need to overcome. One of the primary challenges is data quality. Big data often contains noise, errors, and inconsistencies, which can impact the accuracy and reliability of analysis results. Data validation and cleaning techniques are essential to ensure the quality of the data before analysis. Another challenge is data privacy and security. Big data often contains sensitive and personal information, raising concerns about privacy and the potential misuse of data. Organizations must implement robust security measures and comply with relevant regulations to protect the privacy of individuals and maintain data confidentiality. The sheer volume and complexity of big data also pose challenges in terms of storage and processing infrastructure. Organizations need to invest in scalable and cost-effective storage solutions and powerful processing capabilities to handle big data effectively. Despite these challenges, big data analytics offers significant opportunities for organizations. By harnessing the power of big data, organizations can gain valuable insights into customer behavior, market trends, and operational efficiency. These insights can drive innovation, improve decision-making, and enhance business performance. In conclusion, big data analytics is a rapidly evolving field that enables organizations to extract valuable insights from large and complex datasets. The introduction of big data has revolutionized the way data is stored, processed, and analyzed. With the right tools, techniques, and infrastructure, organizations can unlock the full potential of big data and gain a competitive advantage in today's data-driven world. 8.2 Data Storage and Processing. In the era of big data, the ability to store and process large volumes of data efficiently is crucial for effective data analysis. Data storage and processing refer to the methods and technologies used to store and manage data, as well as the techniques employed to process and analyze the data. In this section, we will explore the various aspects of data storage and processing in the context of big data analytics. 8.2.1 Data Storage. Data storage involves the physical or virtual storage of data in a structured manner to ensure its accessibility and availability for analysis. With the exponential growth of data, traditional storage systems have become inadequate to handle the sheer volume and variety of data generated. As a result, new storage technologies and architectures have emerged to address the challenges posed by big data. Distributed file systems. Distributed file systems are designed to store and manage large volumes of data across multiple servers or nodes. These systems provide fault tolerance, scalability, and high availability by distributing the data across multiple machines. One of the most popular distributed file systems is the Hadoop Distributed File System, HDFS, which is widely used in big data analytics. HDFS divides the data into blocks and replicates them across multiple nodes, ensuring data reliability and fault tolerance. NoSQL databases. NoSQL, not only SQL, databases are non-relational databases that provide flexible and scalable storage solutions for big data. Unlike traditional relational databases, NoSQL databases do not enforce a fixed schema, allowing for dynamic and unstructured data storage. NoSQL databases are well suited for handling large volumes of data with high velocity and variety, making them ideal for big data analytics. Some popular NoSQL databases include MongoDB, Cassandra, and Redis. Data warehouses. Data warehouses are centralized repositories that store structured and organized data from various sources for analysis and reporting. They are designed to support complex queries and provide a consolidated view of the data. Data warehouses typically use a relational database management system, RDBMS, to store and manage the data. They employ techniques such as indexing, partitioning, and data compression to optimize query performance. Data warehouses are commonly used in business intelligence and decision support systems. 8.2.2 Data processing. Data processing involves the transformation and manipulation of data to extract meaningful insights and knowledge. In the context of big data analytics, traditional data processing techniques are often inadequate due to the volume, velocity, and variety of data. Therefore, new approaches and technologies have emerged to enable efficient data processing at scale. Batch processing. Batch processing is a traditional approach to data processing where data is collected, stored, and processed in batches. In this approach, data is processed in predefined intervals or time windows. Batch processing is well suited for scenarios where real-time processing is not required, and data can be processed offline. Technologies such as Apache Hadoop and Apache Spark provide frameworks for distributed batch processing, enabling the processing of large volumes of data in parallel. Stream processing. Stream processing is an approach to data processing that deals with data in motion, processing it in real time as it arrives. Stream processing is particularly useful for applications that require real-time analytics, such as fraud detection, sensor data analysis, and stock market analysis. Technologies like Apache Kafka and Apache Flink provide frameworks for distributed stream processing, allowing for the processing of high-velocity data streams in real time. In-memory processing. In-memory processing refers to the practice of storing and processing data in the main memory (RAM) instead of traditional disk-based storage. By keeping the data in-memory processing enables faster data access and processing speeds, resulting in improved performance. In-memory processing is especially beneficial for applications that require real-time analytics and low-latency processing. Technologies like Apache Ignite and SAP HANA provide in-memory processing capabilities for big data analytics. Parallel processing. Parallel processing involves the simultaneous execution of multiple tasks or computations to speed up data processing. Parallel processing can be achieved by dividing the data into smaller chunks and processing them in parallel across multiple processors or nodes. This approach allows for faster data processing and improved scalability. Technologies like Apache Spark and Apache Hadoop provide frameworks for distributed parallel processing, enabling the processing of large-scale datasets in parallel. Conclusion. Data storage and processing are critical components of big data analytics. Effective data storage ensures the accessibility and availability of data for analysis, while efficient data processing enables the extraction of valuable insights from the data. Distributed file systems, NoSQL databases, and data warehouses provide scalable and flexible storage solutions for big data. Batch processing, stream processing, in-memory processing, and parallel processing are some of the techniques used for data processing in the context of big data analytics. By leveraging these storage and processing technologies, organizations can unlock the full potential of their big data and gain valuable insights to drive informed decision-making. 8.3 Data analysis techniques for big data. Big data refers to the vast amount of data that is generated from various sources such as social media, sensors, and online transactions. Analyzing big data requires specialized techniques and tools due to its volume, velocity, and variety. In this section, we will explore the data analysis techniques that are commonly used for big data. 8.3.1 Quantitative analysis for big data. Quantitative analysis involves the use of mathematical and statistical methods to analyze numerical data. When dealing with big data, traditional quantitative analysis techniques may not be sufficient due to the sheer volume of data. Here are some data analysis techniques that are commonly used for big data. 8.3.1.1 Descriptive statistics. Descriptive statistics provide a summary of the main characteristics of a dataset. In the context of big data, descriptive statistics can help in understanding the distribution, central tendency, and variability of the data. Techniques such as mean, median, mode, standard deviation, and percentiles can be used to analyze big data and gain insights into its characteristics. 8.3.1.2 Data mining. Data mining is the process of discovering patterns, relationships, and insights from large datasets. It involves the use of machine learning algorithms and statistical techniques to uncover hidden patterns and make predictions. Data mining techniques such as association rule mining, classification, clustering, and anomaly detection can be applied to big data to extract valuable information. 8.3.1.3 Regression analysis. Regression analysis is used to model the relationship between a dependent variable and one or more independent variables. In the context of big data, regression analysis can be used to predict future trends, identify factors that influence a particular outcome, and understand the strength of the relationship between variables. Techniques such as linear regression, logistic regression, and time series regression can be applied to big data for predictive modeling. 8.3.1.4 Hypothesis testing. Hypothesis testing is used to make inferences about a population based on a sample of data. It involves formulating a null hypothesis and an alternative hypothesis, collecting data, and using statistical tests to determine whether there is enough evidence to reject the null hypothesis. In the context of big data, hypothesis testing can be used to validate assumptions, test the significance of relationships, and make data-driven decisions. 8.3.2 Qualitative analysis for big data. Qualitative analysis involves the interpretation and understanding of non-numerical data such as text, images, and videos. Analyzing qualitative data from big data sources can be challenging due to the unstructured nature of the data. Here are some data analysis techniques that are commonly used for qualitative analysis of big data. 8.3.2.1 Text mining. Text mining is the process of extracting useful information from unstructured text data. In the context of big data, text mining techniques can be used to analyze large volumes of text data from sources such as social media, customer reviews, and news articles. Techniques such as sentiment analysis, topic modeling, and named entity recognition can be applied to big data to gain insights from textual information. 8.3.2.2 Image and video analysis. Analyzing images and videos from big data sources can provide valuable insights in various domains such as healthcare, surveillance, and entertainment. Image and video analysis techniques such as object detection, image classification, and video summarization can be used to extract meaningful information from large collections of visual data. 8.3.2.3 Social network analysis. Social network analysis involves the study of social relationships and interactions among individuals or organizations. In the context of big data, social network analysis techniques can be used to analyze large-scale social networks from sources such as social media platforms and online communities. Techniques such as network visualization, centrality analysis, and community detection can be applied to big data to understand social structures and dynamics. 8.3.2.4 Content analysis. Content analysis is a research method used to analyze the content of textual, visual, or audio data. In the context of big data, content analysis techniques can be used to analyze large volumes of data from sources such as online forums, blogs, and news articles. Techniques such as thematic analysis, coding, and content categorization can be applied to big data to identify patterns, themes, and trends. In conclusion, analyzing big data requires a combination of quantitative and qualitative analysis techniques. Quantitative analysis techniques such as descriptive statistics, data mining, regression analysis, and hypothesis testing can provide insights into the numerical aspects of big data. Qualitative analysis techniques such as text mining, image and video analysis, social network analysis, and content analysis can help in understanding the non-numerical aspects of big data. By applying these techniques, analysts can uncover valuable insights and make data-driven decisions in the era of big data. 8.4 Challenges and opportunities in big data analytics. Big data analytics has revolutionized the way organizations analyze and interpret vast amounts of data to gain valuable insights and make informed decisions. However, along with the numerous opportunities that big data analytics presents, there are also several challenges that organizations must overcome to effectively harness the power of big data. In this section, we will explore some of the key challenges and opportunities in big data analytics. 8.4.1 Volume, Velocity, and Variety. One of the primary challenges in big data analytics is the sheer volume, velocity, and variety of data. Big data refers to datasets that are too large and complex to be processed using traditional data processing techniques. The volume of data generated by organizations is growing exponentially, and it becomes increasingly difficult to store, process, and analyze such massive amounts of data. Moreover, the velocity at which data is generated is also a challenge, as organizations need to process and analyze data in real time to gain timely insights. Additionally, the variety of data sources, including structured, semi-structured, and unstructured data, poses a challenge in terms of data integration and analysis. However, these challenges also present opportunities for organizations. By effectively managing and analyzing large volumes of data, organizations can gain deeper insights and make data-driven decisions. Real-time data processing allows organizations to respond quickly to changing market conditions and customer needs. The variety of data sources provides organizations with a wealth of information that can be used to uncover hidden patterns and trends. 8.4.2 Data quality and data governance. Another significant challenge in big data analytics is ensuring data quality and maintaining data governance. With the vast amount of data being generated, organizations need to ensure that the data they collect is accurate, complete, and reliable. Data quality issues, such as missing values, inconsistencies, and errors, can significantly impact the accuracy and reliability of the analysis results. Additionally, organizations need to establish robust data governance practices to ensure data privacy, security, and compliance with regulatory requirements. However, addressing data quality and data governance challenges can lead to improved data accuracy and reliability. By implementing data quality control measures, organizations can enhance the integrity of their data and increase the trustworthiness of their analysis results. Effective data governance practices ensure that data is managed and used in a responsible and compliant manner, protecting the privacy and security of individuals' data. 8.4.3 Scalability and infrastructure. Scalability is a critical challenge in big data analytics. As the volume of data continues to grow, organizations need to ensure that their infrastructure can handle the increased data processing and storage requirements. Traditional data processing systems may not be able to handle the scale and complexity of big data analytics. Therefore, organizations need to invest in scalable infrastructure, such as distributed computing systems and cloud-based platforms, to effectively process and analyze large volumes of data. However, investing in scalable infrastructure presents an opportunity for organizations to leverage the power of big data analytics. By adopting scalable technologies, organizations can process and analyze data more efficiently, leading to faster insights and improved decision-making. Cloud-based platforms provide the flexibility and scalability required to handle large volumes of data, allowing organizations to focus on analysis rather than infrastructure management. 8.4.4 Data Privacy and Security. Data privacy and security are significant concerns in big data analytics. With the increasing amount of data being collected and analyzed, organizations need to ensure that individuals' privacy is protected and that data is secured from unauthorized access or breaches. Data privacy regulations, such as the General Data Protection Regulation (GDPR), impose strict requirements on organizations regarding the collection, storage, and use of personal data. However, addressing data privacy and security challenges can lead to increased trust and confidence in big data analytics. By implementing robust data privacy and security measures, organizations can demonstrate their commitment to protecting individuals' data and comply with regulatory requirements. This, in turn, can enhance customer trust and loyalty, leading to improved business outcomes. 8.4.5 Data Integration and Analysis. Integrating and analyzing diverse data sources is a complex challenge in big data analytics. Organizations often have data stored in various formats and systems, making it difficult to integrate and analyze data effectively. Data integration involves combining data from different sources and formats to create a unified view for analysis. Data analysis requires advanced techniques and algorithms to uncover patterns, trends, and insights from the integrated data. However, addressing data integration and analysis challenges can lead to a holistic view of the organization's data and enable more comprehensive analysis. By integrating data from various sources, organizations can gain a deeper understanding of their operations, customers, and market trends. Advanced data analysis techniques, such as machine learning and artificial intelligence, can uncover valuable insights that can drive innovation and competitive advantage. 8.4.6 Skills and Expertise. Big data analytics requires specialized skills and expertise. Organizations need professionals who are proficient in data analysis, statistics, programming, and data visualization. However, there is a shortage of skilled data analysts and data scientists in the industry. Finding and retaining talent with the necessary skills and expertise can be a significant challenge for organizations. However, investing in skills development and training presents an opportunity for organizations to build a strong data analytics team. By providing training and development opportunities, organizations can equip their employees with the necessary skills to effectively analyze and interpret big data. Collaboration with academic institutions and industry experts can also help bridge the skills gap and foster innovation in big data analytics. In conclusion, big data analytics offers numerous opportunities for organizations to gain valuable insights and make data-driven decisions. However, it also presents several challenges, including the volume, velocity, and variety of data, data quality and governance, scalability and infrastructure, data privacy and security, data integration and analysis, and skills and expertise. By addressing these challenges, organizations can unlock the full potential of big data analytics and drive innovation and growth. 9. Time series analysis. 9.1 Time series components. Time series analysis is a powerful technique used to analyze data that is collected over a period of time. It involves studying the patterns, trends, and relationships within the data to make predictions and gain insights. Before diving into the various forecasting methods and techniques, it is important to understand the components of a time series. A time series can be decomposed into four main components: trend, seasonality, cyclicality, and random or residual variation. Each component represents a different aspect of the data, and understanding these components is crucial for accurate analysis and forecasting. 9.1.1 Trend. The trend component of a time series represents the long-term movement or direction of the data. It shows whether the data is increasing, decreasing, or remaining relatively stable over time. Trends can be linear, where the data follows a straight line, or nonlinear, where the data follows a curved or irregular pattern. Identifying the trend component is important because it helps us understand the underlying behavior of the data and make predictions about future values. Trends can be influenced by various factors such as economic conditions, population growth, technological advancements, or natural phenomena. Analyzing the trend component allows us to identify and monitor these factors and their impact on the data. 9.1.2 Seasonality. Seasonality refers to the regular and predictable patterns that occur within a time series at fixed intervals. These patterns repeat over a specific period, such as daily, weekly, monthly, or yearly. Seasonality is often observed in data related to sales, weather, tourism, or any other phenomenon that exhibits recurring patterns. Identifying the seasonality component is crucial for understanding the cyclical patterns within the data and making accurate forecasts. By analyzing the seasonality component, we can identify the peak and off-peak periods, understand the impact of seasonal factors on the data, and adjust our forecasts accordingly. 9.1.3 Cyclicality. Cyclicality represents the fluctuations in a time series that occur at irregular intervals and are not necessarily of fixed duration. Unlike seasonality, which has a fixed and predictable pattern, cyclicality is more unpredictable and can be influenced by various external factors such as economic cycles, business cycles, or political events. Identifying the cyclicality component helps us understand the longer-term patterns and fluctuations within the data. It allows us to analyze the ups and downs of the data and identify any recurring patterns that are not necessarily tied to fixed intervals. Analyzing the cyclicality component can provide insights into the underlying factors that drive these fluctuations and help us make more accurate forecasts. 9.1.4 Random or residual variation. The random or residual variation component represents the unpredictable and random fluctuations within a time series that cannot be explained by the trend, seasonality, or cyclicality components. It includes factors such as measurement errors, random shocks, or other unforeseen events that affect the data. The random component is often considered as noise or error in the data and is typically represented by the residuals obtained from the analysis. Analyzing the random or residual variation component helps us understand the level of uncertainty or unpredictability within the data. It allows us to assess the accuracy of our forecasts and identify any unusual or outlier observations that may need further investigation. Understanding the different components of a time series is essential for accurate analysis and forecasting. By decomposing the time series into its trend, seasonality, cyclicality, and random components, we can gain valuable insights into the underlying patterns and behaviors of the data. This knowledge enables us to make informed decisions, identify potential risks or opportunities, and improve the accuracy of our forecasts. 9.2 Forecasting methods. Forecasting is a crucial aspect of time series analysis that involves predicting future values based on historical data patterns. It plays a vital role in various fields, including finance, economics, supply chain management, and weather forecasting. Forecasting methods utilize statistical techniques and mathematical models to estimate future values and trends, allowing businesses and organizations to make informed decisions and plan for the future. In this section, we will explore different forecasting methods commonly used in data analysis. These methods can be broadly categorized into two types: quantitative and qualitative forecasting. 9.2.1 Quantitative forecasting methods. Quantitative forecasting methods rely on historical data and mathematical models to predict future values. These methods are suitable when historical data is available and can be used to identify patterns and trends. Here are some commonly used quantitative forecasting methods. 1. Moving averages. Moving averages is a simple yet effective method for forecasting. It involves calculating the average of a specific number of past observations to predict future values. The number of past observations used in the calculation is known as the window size. Moving averages smooth out fluctuations in the data and provide a trend line that can be used for forecasting. 2. Exponential smoothing. Exponential smoothing is a popular forecasting method that assigns exponentially decreasing weights to past observations. It gives more weight to recent observations and less weight to older ones. This method is particularly useful when there is a trend or seasonality in the data. Exponential smoothing provides a more accurate forecast by adjusting the weights based on the level of trend or seasonality present in the data. 3. Autoregressive integrated moving average, ARIMA. ARIMA is a widely used forecasting method that combines autoregressive, AR, moving average, MA, and differencing, I, components. It is suitable for time series data that exhibit trend and seasonality. ARIMA models consider the relationship between an observation and a number of lagged observations to make predictions. The parameters of the ARIMA model are determined through a process called model identification, estimation, and diagnostic checking. 4. Seasonal decomposition of time series, STL. STL is a method that decomposes a time series into its trend, seasonal, and residual components. It separates the different components of the time series, allowing for a better understanding of the underlying patterns. Once the components are identified, forecasting can be done separately for each component and then combined to obtain the final forecast. STL is particularly useful when dealing with time series data that exhibits strong seasonality. 5. Box-Jenkins methodology. The Box-Jenkins methodology is a comprehensive approach to time series analysis and forecasting. It involves a systematic process of model identification, estimation, and diagnostic checking. The methodology focuses on identifying the best-fitting ARIMA model for the data by analyzing the autocorrelation and partial autocorrelation functions. The selected model is then used for forecasting future values. 9.2.2 Qualitative forecasting methods. Qualitative forecasting methods are used when historical data is limited or unavailable. These methods rely on expert opinions, surveys, market research, and other qualitative data sources to make predictions. Here are some commonly used qualitative forecasting methods. 1. Delphi method. The Delphi method is a structured approach that involves collecting opinions from a panel of experts. The experts provide their forecasts independently, and the results are aggregated and analyzed. The process is iterative, with experts revising their forecasts based on the feedback received from the group. The Delphi method is useful when there is a lack of historical data or when the future is uncertain. 2. Market research. Market research involves gathering data from customers, competitors, and other relevant sources to understand market trends and make predictions. Surveys, focus groups, and interviews are commonly used methods in market research. By analyzing the collected data, businesses can gain insights into customer preferences, buying behavior, and market dynamics, which can be used for forecasting future demand and trends. 3. Scenario analysis. Scenario analysis involves creating multiple scenarios or possible future outcomes based on different assumptions and variables. This method is particularly useful when there are significant uncertainties and risks involved. By considering various scenarios, businesses can assess the potential impact of different factors and make contingency plans accordingly. Scenario analysis helps in identifying potential risks and opportunities, enabling better decision-making. 4. Judgmental forecasting. Judgmental forecasting relies on the expertise and judgment of individuals or groups to make predictions. This method is subjective and based on personal opinions, experience, and intuition. Judgmental forecasting is often used when there is limited data available or when historical patterns are not reliable indicators of future trends. It is commonly used in situations where human judgment and expertise play a crucial role, such as in new product development or emerging markets. Forecasting methods, whether quantitative or qualitative, have their strengths and limitations. The choice of method depends on the availability of data, the nature of the problem, and the level of accuracy required. It is often beneficial to use a combination of methods or compare the results obtained from different approaches to improve the accuracy of forecasts. In the next section, we will explore the concepts of seasonality and trend analysis in time series data, which are essential for understanding and interpreting forecasting results. 9.3 Seasonality and trend analysis. Seasonality and trend analysis is an important aspect of time series analysis. Time series data often exhibit patterns that repeat over regular intervals, known as seasonality, as well as long-term trends that show the overall direction of the data. Understanding and analyzing these patterns can provide valuable insights into the underlying factors that influence the data. 9.3.1 Seasonality analysis. Seasonality refers to the regular and predictable patterns that occur in a time series data at fixed intervals. These patterns can be daily, weekly, monthly, quarterly, or yearly, depending on the nature of the data. Seasonality analysis involves identifying and quantifying these patterns to understand their impact on the data. Identifying seasonality. To identify seasonality in a time series, several methods can be used. One common approach is to plot the data over time and visually inspect for recurring patterns. If the data exhibits regular peaks and troughs at fixed intervals, it suggests the presence of seasonality. Another method is to calculate the autocorrelation function, ACF, and partial autocorrelation function, PACF, of the time series. A significant spike in the ACF or PACF at specific lags indicates the presence of seasonality. Quantifying seasonality. Once seasonality is identified, it is important to quantify its impact on the data. One way to do this is by decomposing the time series into its seasonal, trend, and residual components. This can be achieved using techniques such as moving averages, exponential smoothing, or the more advanced seasonal decomposition of time series (STL) method. By decomposing the time series, we can isolate the seasonal component and analyze its patterns separately. This allows us to understand the magnitude and timing of the seasonal fluctuations in the data. Seasonal adjustment. Seasonal adjustment is the process of removing the seasonal component from the time series data to obtain a deseasonalized series. This is done to better understand the underlying trend and to make accurate forecasts. There are various methods available for seasonal adjustment, including the X12ARIMA method, the seasonal trend decomposition using Loess (STL) method, and the seasonal adjustment using regression models (SEATS) method. These methods aim to estimate and remove the seasonal component while preserving the trend and other non-seasonal patterns in the data. 9.3.2 Trend analysis. Trend analysis focuses on identifying and analyzing the long-term direction or movement of a time series. It helps us understand the overall pattern and behavior of the data over an extended period. Types of trends. Trends can be classified into three main types: upward, positive, downward, negative, and horizontal, no trend. An upward trend indicates a consistent increase in the data over time, while a downward trend suggests a consistent decrease. A horizontal trend indicates no significant change in the data over time. Trend estimation. There are several methods available for estimating and quantifying trends in time series data. One common approach is to use simple linear regression, where the time variable is treated as the independent variable, and the data values are treated as the dependent variable. The slope of the regression line represents the trend, indicating the rate of change in the data over time. Another method is the moving average technique, where a series of averages is calculated over a fixed window of time. This smooths out the fluctuations in the data and helps identify the underlying trend. Trend analysis techniques. Once the trend is estimated, various techniques can be used to analyze and interpret the trend. Trend visualization. Plotting the data with the trend line can provide a visual representation of the trend. This helps in understanding the overall direction and magnitude of the trend. Trend testing. Statistical tests such as the Mann-Kendall test or the Sen's slope estimator can be used to determine the significance of the trend. These tests assess whether the observed trend is statistically significant or occurred by chance. Trend forecasting. Once the trend is identified, it can be used to make future predictions or forecasts. Time series forecasting methods such as exponential smoothing or ARIMA models can be employed to forecast the future values based on the trend. Conclusion. Seasonality and trend analysis are essential components of time series analysis. By identifying and quantifying seasonality patterns, we can better understand the cyclic behavior of the data. Similarly, trend analysis helps us identify the long-term direction and movement of the data. Both these analyses provide valuable insights into the underlying factors influencing the time series data and aid in making accurate forecasts and informed decisions. 9.4 Time series modeling. Time series modeling is a statistical technique used to analyze and forecast data that is collected over a period of time at regular intervals. It is a powerful tool for understanding and predicting patterns, trends, and behavior in time-dependent data. Time series modeling involves identifying the underlying structure and characteristics of the data, and then using this information to make predictions about future values. 9.4.1 Introduction to time series modeling. Time series modeling is widely used in various fields such as finance, economics, weather forecasting, and sales forecasting. It allows analysts to uncover hidden patterns and relationships in the data, which can be used to make informed decisions and predictions. Time series data is characterized by its sequential nature, where each observation is dependent on the previous observations. The goal of time series modeling is to develop a mathematical model that can capture the underlying patterns and dynamics of the data. This model can then be used to forecast future values, estimate the impact of different factors, and analyze the effects of interventions or policy changes. 9.4.2 Components of time series. Before diving into time series modeling, it is important to understand the components that make up a time series. A time series can be decomposed into four main components. Trend, the long-term movement or direction of the data. It represents the underlying pattern or tendency of the data over time. Trends can be upward, increasing, downward, decreasing, or stationary, no significant change. Seasonality, the repetitive and predictable patterns that occur within a fixed time period. Seasonality can be daily, weekly, monthly, or yearly. It is often associated with factors such as holidays, weather conditions, or economic cycles. Cyclical variation, the irregular fluctuations in the data that occur over a longer time period, typically more than 1 year. Cyclical variations are often influenced by economic, political, or social factors and are not as predictable as seasonality. Random or residual variation, the unpredictable and random fluctuations that cannot be explained by the trend, seasonality, or cyclical components. It represents the noise or error in the data. 9.4.3 Time series modeling techniques. There are several techniques available for modeling time series data. The choice of technique depends on the characteristics of the data and the specific objectives of the analysis. Some commonly used time series modeling techniques include autoregressive integrated moving average (ARIMA). ARIMA models are widely used for forecasting time series data. They combine autoregressive (AR) moving average (MA) and differencing (I) components to capture the trend, seasonality, and random variations in the data. ARIMA models are flexible and can handle both stationary and non-stationary data. Exponential smoothing. Exponential smoothing models are based on the idea of giving more weight to recent observations and gradually decreasing the weight as the observations become older. These models are particularly useful for short-term forecasting and are easy to interpret and implement. Seasonal decomposition of time series (STL). STL is a technique that decomposes a time series into its trend, seasonal, and residual components. It allows analysts to separately analyze and model each component, which can then be combined to make forecasts. Vector autoregression (VAR). VAR models are used when there are multiple time series variables that are interrelated and influence each other. They capture the dynamic relationships between the variables and can be used for forecasting and analyzing the impact of shocks or interventions. State space models. State space models are a flexible class of models that can handle complex time series data. They represent the underlying process as a set of unobserved states and observations. State space models can incorporate various components such as trends, seasonality, and exogenous variables. 9.4.4 Model evaluation and selection. Once a time series model is developed, it is important to evaluate its performance and select the best model for forecasting. Model evaluation involves assessing the accuracy and reliability of the model's predictions. Common techniques for model evaluation include mean absolute error (MAE). MAE measures the average absolute difference between the actual and predicted values. It provides a measure of the model's accuracy. Mean squared error (MSE). MSE measures the average squared difference between the actual and predicted values. It gives more weight to larger errors and is useful for penalizing large deviations. Root mean squared error (RMSE). RMSE is the square root of the MSE and provides a measure of the model's average prediction error in the original units of the data. Akaika Information Criterion (AIC) and Bayesian Information Criterion (BIC). AIC and BIC are statistical measures used for model selection. They balance the goodness of fit of the model with the complexity of the model. Model selection involves comparing the performance of different models and selecting the one that provides the best balance between accuracy and simplicity. Conclusion. Time series modeling is a valuable tool for analyzing and forecasting time-dependent data. By understanding the components of a time series and using appropriate modeling techniques, analysts can uncover patterns, trends, and relationships in the data. Time series modeling allows for informed decision-making, accurate forecasting, and the identification of factors that influence the data. It is a powerful technique that can be applied in various fields to gain insights and make predictions based on historical data. 10. Spatial analysis. 10.1 Spatial data types. Spatial data refers to data that is associated with a specific location or geographic area. It provides valuable insights into the relationships and patterns that exist in the physical world. In this section, we will explore the different types of spatial data and how they are used in spatial analysis. 10.1.1 Vector data. Vector data is one of the most common types of spatial data. It represents geographic features as points, lines, and polygons. Points are used to represent specific locations, such as the coordinates of a city or landmark. Lines are used to represent linear features, such as roads or rivers. Polygons are used to represent areas, such as the boundaries of countries or the shape of a lake. Vector data is often used in spatial analysis to perform operations such as buffering, overlaying, and spatial querying. These operations allow us to analyze the relationships between different geographic features and answer questions about proximity, containment, and connectivity. 10.1.2 Raster data. Raster data is another type of spatial data that is commonly used in spatial analysis. It represents geographic features as a grid of cells or pixels. Each cell in the grid contains a value that represents a specific attribute or characteristic of the geographic feature. Raster data is particularly useful for analyzing continuous phenomena, such as temperature, elevation, or vegetation cover. It allows us to perform operations such as interpolation, classification, and overlay analysis. These operations help us understand the spatial patterns and distributions of the attributes represented by the raster data. 10.1.3 Geospatial data formats. Spatial data can be stored in various formats, depending on the specific needs and requirements of the analysis. Some common geospatial data formats include Shapefile. This is a popular format developed by Esri for storing vector data. It consists of multiple files that store the geometry, attributes, and spatial index of the features. GeoJSON. This is a lightweight format for storing vector data in JSON, JavaScript object notation format. It is widely used for web mapping applications due to its simplicity and compatibility with JavaScript. GeoTIFF. This is a format for storing raster data that includes georeferencing information. It allows for the storage of multiple bands or layers, making it suitable for storing multidimensional data such as satellite imagery. NetCDF. This is a format commonly used for storing scientific data, including spatial data. It supports the storage of multidimensional arrays and includes metadata that describe the variables and their attributes. KML Keyhole Markup Language. This is a format developed by Google for storing and visualizing geographic data in applications such as Google Earth. It supports both vector and raster data and includes styling and annotation capabilities. 10.1.4 Geospatial data sources. Spatial data can be obtained from various sources, depending on the specific analysis requirements. Some common sources of geospatial data include government agencies. Many government agencies collect and maintain spatial data for various purposes, such as land use planning, transportation, and environmental monitoring. These agencies often provide access to their data through online portals or data clearinghouses. Remote sensing. Remote sensing involves the use of satellite or aerial imagery to capture information about the Earth's surface. This data can be used to derive various spatial attributes, such as land cover, vegetation indices, and surface temperature. Global Positioning System (GPS). GPS technology allows for the collection of precise location data using satellite signals. GPS data can be used to create point features or track the movement of objects or individuals over time. Crowdsourcing. Crowdsourcing platforms, such as OpenStreetMap, allow individuals to contribute spatial data by mapping features in their local area. This data can be used for various purposes, including navigation, disaster response, and urban planning. Sensor networks. Sensor networks consist of a network of sensors that collect data about the physical environment, such as temperature, humidity, or air quality. This data can be used to create spatial models or monitor environmental conditions in real time. 10.1.5 Geospatial data analysis. Spatial data analysis involves the application of statistical and analytical techniques to spatial data in order to gain insights and make informed decisions. It encompasses a wide range of methods and tools, including spatial querying. Spatial querying involves retrieving data based on their spatial relationships. For example, we can query for all the points within a certain distance of a given location or find all the polygons that intersect a specific area. Spatial join. Spatial join combines data from two or more spatial datasets based on their spatial relationships. For example, we can join a dataset of cities with a dataset of countries to assign the country name to each city. Spatial interpolation. Spatial interpolation is used to estimate values at unmeasured locations based on the values observed at nearby locations. This technique is commonly used in environmental modeling to estimate variables such as temperature or precipitation. Spatial regression. Spatial regression is a statistical technique that takes into account the spatial relationships between observations when modeling the relationship between a dependent variable and one or more independent variables. It is particularly useful when analyzing spatially correlated data. Spatial clustering. Spatial clustering is used to identify groups or clusters of similar features based on their spatial proximity. This technique is commonly used in market segmentation, crime analysis, and disease mapping. Spatial data analysis plays a crucial role in various fields, including urban planning, environmental management, transportation, and public health. It allows us to understand the spatial patterns and relationships that exist in the world around us and make informed decisions based on this knowledge. 10.2 Spatial data visualization. Spatial data visualization is a crucial aspect of spatial analysis, as it allows us to effectively communicate and understand patterns, relationships, and trends within geographic data. By visually representing spatial data, we can gain insights and make informed decisions in various fields such as urban planning, environmental science, transportation, and public health. In this section, we will explore different techniques and tools for visualizing spatial data. 10.2.1 Mapping. Mapping is one of the most common and intuitive ways to visualize spatial data. It involves representing geographic features and their attributes on a map. Maps can be created using various software tools, such as Geographic Information Systems (GIS) software or online mapping platforms like Google Maps or OpenStreetMap. When creating a map, it is important to consider the type of spatial data being visualized. For point data, such as the locations of cities or landmarks, simple markers or symbols can be used to represent each point. For example, a dot on a map can represent a city, and the size or color of the dot can indicate a specific attribute, such as population size or average temperature. For line data, such as roads or rivers, lines can be used to represent the features. The thickness or color of the lines can convey additional information, such as traffic volume or water flow rate. For polygon data, such as administrative boundaries or land use areas, different colors or patterns can be used to distinguish between different categories or classes. 10.2.2 Choropleth maps. Choropleth maps are a type of thematic map that uses color or shading to represent different values or attributes of a geographic area. This technique is commonly used to visualize spatial patterns and variations across regions. Choropleth maps are particularly useful for displaying data that is aggregated at a larger spatial scale, such as census data or election results. To create a choropleth map, the geographic area of interest is divided into smaller regions, such as states or counties. Each region is then assigned a color or shade based on the value of the attribute being visualized. For example, in a population choropleth map, darker shades can represent higher population densities, while lighter shades can represent lower densities. It is important to choose an appropriate color scheme for choropleth maps to ensure that the data is accurately represented and easily interpreted. Sequential color schemes, where colors gradually change from light to dark, are commonly used for representing ordered data, such as population or income levels. Divergent color schemes, where colors diverge from a central value, are used for representing data with a distinct midpoint, such as temperature anomalies. Qualitative color schemes, where each color represents a different category or class, are used for representing categorical data, such as land use types. 10.2.3 Heat maps. Heat maps are another effective way to visualize spatial data, particularly when dealing with large datasets or continuous variables. Heat maps use color intensity to represent the density or intensity of a particular phenomenon across a geographic area. They are commonly used to visualize patterns of activity, such as population density, crime rates, or disease prevalence. In a heat map, areas with higher values or densities are represented by darker or more intense colors, while areas with lower values or densities are represented by lighter or less intense colors. This allows us to quickly identify areas of high or low intensity and detect spatial patterns or clusters. Heat maps can be created using various software tools or libraries, such as Python's Matplotlib or R's ggplot2. These tools provide flexibility in customizing the color scheme, opacity, and resolution of the heat map to suit the specific needs of the analysis. 10.2.4 3D visualization. In addition to 2D maps, spatial data can also be visualized in 3D to provide a more immersive and realistic representation of the geographic environment. 3D visualization allows us to explore spatial relationships and terrain features in a more interactive and engaging manner. With the advancement of technology, 3D visualization tools have become more accessible and user-friendly. Geographic Information Systems (GIS) software, such as ArcGIS or QGIS, often include 3D visualization capabilities. These tools allow users to create and manipulate 3D models of the Earth's surface, buildings, and other features. 3D visualization is particularly useful in urban planning and architecture, where it can help stakeholders visualize proposed developments, assess the impact of new structures on the surrounding environment, and simulate different scenarios. It can also be used in environmental science to study terrain characteristics, analyze elevation data, and model the effects of natural disasters. 10.2.5 Interactive visualizations. Interactive visualizations provide users with the ability to explore and interact with spatial data in real time. These visualizations often include features such as zooming, panning, filtering, and tooltips, allowing users to focus on specific areas of interest and obtain detailed information about the data. Interactive visualizations can be created using various web-based tools and libraries, such as D3.js, Leaflet, or Mapbox. These tools allow users to create dynamic and responsive maps and visualizations that can be easily shared and accessed online. By incorporating interactivity into spatial data visualizations, users can gain a deeper understanding of the data and uncover hidden patterns or relationships. This can be particularly useful in decision-making processes, as it allows stakeholders to explore different scenarios and assess the potential impact of their choices. In conclusion, spatial data visualization plays a crucial role in understanding and analyzing geographic data. By effectively representing spatial patterns and relationships, we can gain valuable insights and make informed decisions in various fields. Whether through mapping, choropleth maps, heat maps, 3D visualization, or interactive visualizations, spatial data visualization allows us to communicate complex information in a clear and intuitive manner. 10.3 Spatial autocorrelation. Spatial autocorrelation is a statistical technique used to analyze the spatial patterns and relationships in data. It examines whether the values of a variable at one location are similar to the values at neighboring locations. This analysis helps us understand the degree of spatial dependence or clustering in the data. 10.3.1 Understanding spatial autocorrelation. Spatial autocorrelation is based on the concept that nearby locations tend to have similar values for a given variable. It is a measure of the spatial similarity or dissimilarity between observations. This analysis is particularly useful in fields such as geography, ecology, urban planning, and criminology, where spatial relationships play a crucial role. The presence of spatial autocorrelation can have important implications for data analysis. If spatial autocorrelation exists, it violates the assumption of independence between observations, which is a fundamental assumption in many statistical techniques. Ignoring spatial autocorrelation can lead to biased results and incorrect conclusions. 10.3.2 Measuring spatial autocorrelation. To measure spatial autocorrelation, various statistical methods are available. One commonly used measure is Moran's I, which quantifies the degree of spatial clustering or dispersion in the data. Moran's I ranges from -1 to 1, where positive values indicate positive spatial autocorrelation, clustering, negative values indicate negative spatial autocorrelation, dispersion, and values close to 0 indicate no spatial autocorrelation. Another measure is Geary's C, which is similar to Moran's I but focuses on the differences between neighboring observations. Geary's C also ranges from -1 to 1, with similar interpretations as Moran's I. These measures provide a quantitative assessment of spatial autocorrelation, allowing us to determine the strength and significance of the spatial patterns in the data. By understanding the spatial autocorrelation, we can gain insights into the underlying processes and factors that contribute to the observed patterns. 10.3.3 Interpreting spatial autocorrelation. Interpreting the results of spatial autocorrelation analysis requires considering both the magnitude and significance of the measures. A positive Moran's I or Geary's C value indicates spatial clustering, suggesting that similar values tend to occur in close proximity. Conversely, a negative value indicates spatial dispersion, where dissimilar values are more likely to be found near each other. The significance of the measures is determined through hypothesis testing. If the p-value associated with Moran's I or Geary's C is less than a predetermined significance level, e.g., 0.05, we can reject the null hypothesis of no spatial autocorrelation and conclude that there is a significant spatial pattern in the data. The interpretation of spatial autocorrelation results should also consider the spatial scale of analysis. Spatial patterns may vary at different scales, and it is important to choose an appropriate scale that aligns with the research question or objective. Additionally, the interpretation should be guided by domain knowledge and an understanding of the underlying processes that may be driving the observed spatial patterns. 10.3.4 Applications of spatial autocorrelation. Spatial autocorrelation analysis has numerous applications across various fields. In urban planning, it can help identify areas of high or low socioeconomic status, guiding the allocation of resources and interventions. In ecology, it can reveal patterns of species distribution and habitat suitability. In criminology, it can assist in identifying crime hotspots and understanding the spatial dynamics of criminal activities. Furthermore, spatial autocorrelation analysis can be used to assess the effectiveness of spatial policies and interventions. By examining changes in spatial patterns over time, we can evaluate the impact of interventions and identify areas where additional measures may be needed. 10.3.5 Limitations and considerations. While spatial autocorrelation analysis provides valuable insights, it is important to consider its limitations and potential pitfalls. One limitation is the reliance on the assumption of stationarity, which assumes that the spatial patterns remain consistent across the entire study area. Violation of this assumption can lead to biased results. Another consideration is the choice of spatial weighting scheme. Different weighting schemes, such as distance-based or contiguity-based, can yield different results. It is crucial to carefully select an appropriate weighting scheme that aligns with the research question and the characteristics of the data. Additionally, spatial autocorrelation analysis does not provide causal explanations for the observed patterns. It merely identifies the presence and strength of spatial relationships. To understand the underlying processes, further investigation and integration with other analytical techniques may be necessary. Conclusion. Spatial autocorrelation analysis is a powerful tool for understanding the spatial patterns and relationships in data. By quantifying the degree of spatial dependence, it helps us uncover hidden patterns, identify clusters or dispersion, and gain insights into the underlying processes. However, it is important to interpret the results carefully, considering both the magnitude and significance of the measures, as well as the limitations and considerations of the analysis. Spatial autocorrelation analysis has wide-ranging applications and can contribute to evidence-based decision-making in various fields. 10.4 Spatial regression. Spatial regression is a statistical technique used to analyze the relationship between a dependent variable and one or more independent variables in a spatial context. It extends traditional regression analysis by incorporating spatial dependencies and accounting for spatial autocorrelation. Spatial regression models are particularly useful when analyzing data that exhibit spatial patterns or when the location of the observations is an important factor in understanding the relationship between variables. 10.4.1 Introduction to spatial regression. Spatial regression models are designed to capture the spatial relationships between observations and account for the spatial autocorrelation that often exists in spatial data. Spatial autocorrelation refers to the tendency of nearby observations to be more similar to each other than observations that are farther apart. This spatial dependence can violate the assumption of independence in traditional regression models, leading to biased and inefficient parameter estimates. Spatial regression models address this issue by incorporating spatial weights matrices, which quantify the spatial relationships between observations. These weights matrices can be based on various criteria, such as distance, contiguity, or similarity. By including these weights matrices in the regression model, spatial regression accounts for the spatial autocorrelation and produces more accurate and reliable estimates. 10.4.2 Types of spatial regression models. There are several types of spatial regression models, each with its own assumptions and specifications. The choice of model depends on the nature of the data and the research question at hand. Some commonly used spatial regression models include 10.4.2.1 Spatial lag model. The spatial lag model incorporates the spatial autocorrelation of the dependent variable into the regression equation. It assumes that the value of the dependent variable for each observation is influenced not only by its own characteristics but also by the characteristics of neighboring observations. The spatial lag term captures this spatial dependence and allows for the estimation of the direct and indirect effects of the independent variables on the dependent variable. 10.4.2.2 Spatial error model. The spatial error model accounts for the spatial autocorrelation in the error term of the regression equation. It assumes that the error term is spatially correlated and that the spatial dependence is not captured by the independent variables. The spatial error term captures the unobserved spatial factors that affect the dependent variable but are not included in the model. This model is particularly useful when there are omitted variables that exhibit spatial autocorrelation. 10.4.2.3 Spatial Durbin model. The spatial Durbin model combines the spatial lag and spatial error models by including both a spatial lag term and a spatial error term in the regression equation. This model allows for the estimation of direct and indirect effects of the independent variables on the dependent variable, while also accounting for the spatial autocorrelation in the error term. The spatial Durbin model is a flexible and powerful tool for analyzing spatial data. 10.4.3 Estimation and inference in spatial regression. Estimating spatial regression models involves solving a system of equations that account for the spatial dependencies between observations. The most common estimation method is maximum likelihood estimation, MLE, which maximizes the likelihood function to obtain the parameter estimates. Other estimation methods, such as generalized method of moments, GMM, and Bayesian methods, can also be used depending on the specific model and data characteristics. Inference in spatial regression models requires addressing the issue of spatial autocorrelation in the residuals. Traditional hypothesis tests and standard errors assume independence of the residuals, which is violated in the presence of spatial autocorrelation. To address this, various diagnostic tests and robust standard errors can be used to adjust for spatial autocorrelation and obtain valid statistical inference. 10.4.4 Applications of spatial regression. Spatial regression has a wide range of applications in various fields, including geography, economics, environmental science, and public health. Some common applications include spatial econometrics. Spatial regression is widely used in economics to analyze the spatial distribution of economic variables, such as income, employment, and housing prices. It helps to understand the spatial patterns and determinants of economic phenomena. Environmental modeling. spatial regression is used to analyze the relationship between environmental variables, such as air pollution, water quality, and land use, and their spatial determinants. It helps to identify the factors influencing environmental conditions and develop effective environmental management strategies. Public health research. Spatial regression is employed to study the spatial patterns of diseases, such as infectious diseases and cancer, and their relationship with environmental, socioeconomic, and demographic factors. It helps to identify high-risk areas and understand the underlying factors contributing to disease prevalence. Urban planning. Spatial regression is used in urban planning to analyze the spatial distribution of urban phenomena, such as crime rates, transportation patterns, and land use. It helps to identify spatial patterns, assess the impact of urban policies, and guide urban development. 10.4.5 Challenges and limitations of spatial regression. While spatial regression is a powerful tool for analyzing spatial data, it also has some challenges and limitations that need to be considered. Model specification. Choosing the appropriate spatial regression model and specifying the spatial weights matrix can be challenging. The choice of model depends on the nature of the data and the research question, and the specification of the spatial weights matrix requires careful consideration of the spatial relationships between observations. Data availability. Spatial regression models require spatially referenced data, which may not always be readily available. Collecting and preparing spatial data can be time-consuming and resource-intensive, especially for large-scale studies or studies covering multiple geographic areas. Interpretation of results. Interpreting the results of spatial regression models can be complex due to the inclusion of spatial dependencies. The coefficients of the independent variables represent the average effect across all observations, including the direct and indirect effects. Understanding the spatial patterns and interpreting the coefficients require careful analysis and consideration of the spatial context. Assumptions and limitations. Spatial regression models rely on several assumptions, such as linearity, normality, and stationarity. Violation of these assumptions can affect the validity of the results. Additionally, spatial regression models may not be suitable for all types of spatial data or research questions, and alternative methods may need to be considered. Despite these challenges, spatial regression provides a valuable framework for analyzing spatial data and understanding the spatial relationships between variables. It allows researchers to account for spatial autocorrelation, incorporate spatial dependencies, and gain insights into the spatial patterns and determinants of phenomena. With the increasing availability of spatial data and advancements in spatial analysis techniques, spatial regression continues to be a vital tool in data analysis and decision-making. 11. Data ethics and privacy. 11.1 Ethical considerations in data analysis. Data analysis plays a crucial role in various fields, including business, healthcare, social sciences, and more. As data becomes increasingly abundant and accessible, it is essential to address the ethical considerations associated with data analysis. Ethical considerations ensure that data analysis is conducted in a responsible and morally sound manner, protecting the rights and well-being of individuals and communities involved. In this section, we will explore some of the key ethical considerations in data analysis and discuss the importance of upholding ethical standards throughout the data analysis process. 11.1.1 Privacy and confidentiality. One of the primary ethical considerations in data analysis is privacy and confidentiality. When working with data, it is crucial to respect the privacy of individuals and ensure that their personal information is kept confidential. This involves taking appropriate measures to protect data from unauthorized access, use, or disclosure. Researchers and analysts must adhere to legal and ethical guidelines, such as obtaining informed consent from participants and anonymizing data to prevent the identification of individuals. To maintain privacy and confidentiality, data analysts should implement robust security measures, including encryption, access controls, and secure data storage. Additionally, data sharing should be done responsibly, with proper consent and anonymization techniques in place to protect the identities of individuals involved. By prioritizing privacy and confidentiality, data analysts can build trust with participants and stakeholders, fostering a positive and ethical data analysis environment. 11.1.2 Data accuracy and integrity. Another critical ethical consideration in data analysis is ensuring the accuracy and integrity of the data. Data analysts have a responsibility to ensure that the data they analyze is reliable, valid, and representative of the population or phenomenon under study. This involves employing rigorous data collection methods, validating data for errors or inconsistencies, and addressing any biases or limitations in the data. Data accuracy and integrity are essential for producing reliable and trustworthy analysis results. Analysts should document their data collection and cleaning processes, making it transparent and reproducible. By maintaining data accuracy and integrity, analysts can contribute to the advancement of knowledge and decision-making based on sound evidence. 11.1.3 Informed consent and voluntary participation. Informed consent and voluntary participation are fundamental ethical principles in data analysis, especially when working with human subjects. Researchers and analysts must obtain informed consent from participants, ensuring that they understand the purpose, risks, and benefits of the study or analysis. Informed consent involves providing clear and understandable information to participants, allowing them to make an informed decision about their participation. Voluntary participation ensures that individuals have the right to choose whether or not to participate in a study or analysis. Coercion or undue influence should be avoided, and participants should have the freedom to withdraw from the study at any time without facing negative consequences. Respecting the autonomy and rights of participants is crucial in maintaining ethical standards in data analysis. 11.1.4 Bias and Fairness. Data analysis should be conducted in a fair and unbiased manner. Bias can arise at various stages of the data analysis process, including data collection, cleaning, analysis, and interpretation. It is essential for analysts to be aware of their own biases and take steps to minimize their impact on the analysis. To address bias and ensure fairness, analysts should strive for diversity and inclusivity in their data collection and analysis. This involves considering different perspectives, including underrepresented groups, and avoiding discriminatory practices. Transparency in the analysis process, including documenting any assumptions or limitations, can also help mitigate bias and promote fairness. 11.1.5 Social and Cultural Implications. Data analysis can have significant social and cultural implications. Analysts must consider the potential consequences of their analysis on individuals, communities, and society as a whole. This includes being aware of the potential for harm, such as stigmatization or discrimination, and taking steps to minimize these risks. Cultural sensitivity is crucial in data analysis, especially when working with diverse populations. Analysts should be mindful of cultural norms, values, and beliefs that may influence the interpretation and application of the analysis results. Engaging with stakeholders and involving them in the analysis process can help ensure that their perspectives and concerns are considered. 11.1.6 Transparency and Accountability. Transparency and accountability are essential in maintaining ethical standards in data analysis. Analysts should be transparent about their methods, assumptions, and limitations, allowing others to evaluate and replicate their analysis. This includes documenting the data analysis process, including data collection, cleaning, analysis techniques, and interpretation. Accountability involves taking responsibility for the consequences of the analysis and being open to feedback and criticism. Analysts should be receptive to different viewpoints and willing to address any concerns or errors in their analysis. By promoting transparency and accountability, analysts contribute to the credibility and trustworthiness of the data analysis field. In conclusion, ethical considerations are integral to responsible and meaningful data analysis. Privacy and confidentiality, data accuracy and integrity, informed consent and voluntary participation, bias and fairness, social and cultural implications, and transparency and accountability are all crucial aspects of ethical data analysis. By upholding these ethical principles, data analysts can ensure that their analysis is conducted in a manner that respects the rights and well-being of individuals and communities, contributing to the advancement of knowledge and decision-making. 11.2 Data privacy and security. In today's digital age, data privacy and security have become increasingly important considerations in data analysis. As organizations collect and analyze vast amounts of data, it is crucial to ensure that this data is protected from unauthorized access, misuse, and breaches. Data privacy refers to the protection of personal and sensitive information, while data security focuses on safeguarding data from unauthorized access or alteration. 11.2.1 Importance of data privacy and security. Data privacy and security are essential for several reasons. Firstly, they help build trust between organizations and individuals. When individuals provide their personal information to organizations, they expect that their data will be handled with care and kept confidential. Failure to protect data can lead to a loss of trust, reputation damage, and legal consequences. Secondly, data privacy and security are crucial for compliance with legal and regulatory requirements. Many countries have enacted laws and regulations to protect individuals' privacy rights and ensure the secure handling of data. Organizations that fail to comply with these regulations may face severe penalties and legal consequences. Thirdly, data privacy and security are essential for maintaining a competitive advantage. Organizations that prioritize data privacy and security can differentiate themselves from their competitors by demonstrating their commitment to protecting customer information. This can attract customers who value their privacy and are more likely to trust organizations that prioritize data security. 11.2.2 Data privacy principles. To ensure data privacy, organizations should adhere to certain principles when collecting, storing, and analyzing data. These principles include consent. Organizations should obtain informed consent from individuals before collecting their data. Individuals should be aware of how their data will be used and have the option to opt out if they choose. Purpose limitation. Data should only be collected for specific and legitimate purposes. Organizations should clearly communicate the purpose of data collection and ensure that it aligns with the consent provided by individuals. Data minimization. Organizations should only collect the minimum amount of data necessary to achieve the intended purpose. Collecting excessive or unnecessary data increases the risk of data breaches and compromises individuals' privacy. Data accuracy. Organizations should take steps to ensure the accuracy and integrity of the data they collect. Inaccurate or outdated data can lead to incorrect analysis and decision-making. Data retention. Organizations should establish clear policies regarding the retention and deletion of data. Data should only be retained for as long as necessary and securely disposed of when no longer needed. Data security. Organizations should implement appropriate technical and organizational measures to protect data from unauthorized access, loss, or alteration. This includes encryption, access controls, regular security audits, and employee training on data security best practices. 11.2.3 Data security measures. In addition to data privacy principles, organizations should implement various data security measures to protect their data. These measures include access controls. Organizations should implement access controls to ensure that only authorized individuals have access to sensitive data. This can include password protection, multi-factor authentication, and role-based access controls. Encryption. Encryption is the process of converting data into a form that can only be accessed with a decryption key. Organizations should encrypt sensitive data both during transit and at rest to protect it from unauthorized access. Firewalls and intrusion detection systems. Firewalls and intrusion detection systems help protect networks from unauthorized access and monitor for any suspicious activity. These systems can detect and block potential threats, such as malware or unauthorized access attempts. Regular data backups. Regular data backups are essential to ensure that data can be recovered in the event of a data breach or system failure. Backups should be stored securely and tested regularly to ensure their integrity. Employee training. Organizations should provide regular training to employees on data security best practices. This includes educating employees about the importance of data privacy, how to handle sensitive data, and how to identify and report potential security threats. Data breach response plan. Organizations should have a well-defined data breach response plan in place. This plan should outline the steps to be taken in the event of a data breach, including notifying affected individuals, conducting an investigation, and implementing measures to prevent future breaches. 11.2.4 Privacy laws and regulations. Many countries have enacted laws and regulations to protect individuals' privacy rights and regulate the handling of data. Some notable privacy laws include General Data Protection Regulation (GDPR). The GDPR is a comprehensive privacy regulation that applies to all European Union (EU) member states. It sets out strict requirements for the collection, storage, and processing of personal data and provides individuals with greater control over their data. California Consumer Privacy Act (CCPA). The CCPA is a privacy law that applies to businesses operating in California. It gives California residents certain rights over their personal information and requires businesses to be transparent about their data collection and sharing practices. Health Insurance Portability and Accountability Act (HIPAA). HIPAA is a U.S. law that sets standards for the protection of individuals' health information. It applies to healthcare providers, health plans, and healthcare clearinghouses and requires them to implement safeguards to protect patients' privacy. Personal Information Protection and Electronic Documents Act (PIPEDA). PIPEDA is a Canadian privacy law that governs the collection, use, and disclosure of personal information by private sector organizations. It sets out principles for the fair handling of personal information and provides individuals with certain rights over their data. 11.2.5 Ethical considerations in data analysis. Data analysis also raises ethical considerations that go beyond legal compliance. Organizations should consider the following ethical principles when conducting data analysis. Transparency. Organizations should be transparent about their data collection and analysis practices. Individuals should be informed about how their data will be used and have the option to opt out if they choose. Anonymization. Whenever possible, organizations should anonymize or de-identify data to protect individuals' privacy. Anonymized data removes personally identifiable information, reducing the risk of re-identification. Fairness. Organizations should ensure that their data analysis processes are fair and unbiased. This includes avoiding discriminatory practices and ensuring that decisions based on data analysis do not disproportionately impact certain groups. Informed consent. Organizations should obtain informed consent from individuals before using their data for analysis. Individuals should be aware of how their data will be used and have the option to withdraw their consent at any time. Data sharing. Organizations should consider the ethical implications of sharing data with third parties. They should ensure that appropriate safeguards are in place to protect the privacy and security of the data. In conclusion, data privacy and security are critical considerations in data analysis. Organizations must prioritize the protection of personal and sensitive information to build trust, comply with legal requirements, and maintain a competitive advantage. By adhering to data privacy principles, implementing data security measures, and considering ethical considerations, organizations can ensure the responsible and ethical use of data in their analysis processes. 11.3 Legal and regulatory frameworks. In the era of data-driven decision-making, it is crucial for organizations and individuals to understand and comply with the legal and regulatory frameworks that govern data analysis. The use of data, especially personal and sensitive information, comes with ethical and legal responsibilities. This section will explore the legal and regulatory considerations that data analysts need to be aware of when conducting quantitative and qualitative analysis. 11.3.1 Data protection laws. Data protection laws are designed to safeguard the privacy and rights of individuals whose data is being collected, processed, and analyzed. These laws vary across different countries and regions, but they generally aim to ensure that personal data is collected and used in a fair and lawful manner. Data analysts must be familiar with the applicable data protection laws in their jurisdiction to ensure compliance. One of the most well-known data protection regulations is the General Data Protection Regulation, GDPR, in the European Union. The GDPR sets out strict rules for the collection, storage, and processing of personal data. It requires organizations to obtain explicit consent from individuals before collecting their data and provides individuals with the right to access, rectify, and erase their personal information. Data analysts working with data from EU citizens must adhere to the principles and requirements outlined in the GDPR. In addition to the GDPR, many countries have their own data protection laws. For example, the United States has the California Consumer Privacy Act, CCPA, which grants California residents certain rights regarding the collection and use of their personal information. Other countries, such as Canada, Australia, and Japan, also have their own data protection laws that data analysts must consider when working with data from these jurisdictions. 11.3.2 Intellectual Property Rights. Intellectual property rights play a significant role in data analysis, particularly when it comes to using copyrighted materials or proprietary data. Data analysts must be aware of the legal frameworks surrounding intellectual property rights to avoid infringing on the rights of others. When conducting quantitative analysis, data analysts often work with datasets that may contain copyrighted information, such as text, images, or audiovisual content. It is essential to understand the principles of fair use and ensure that the use of copyrighted materials falls within the legal boundaries. Fair use allows for the limited use of copyrighted materials for purposes such as criticism, commentary, research, or education. However, the specific criteria for fair use can vary depending on the jurisdiction, and it is advisable to consult legal experts or refer to the applicable laws to determine if the use of copyrighted materials is permissible. In qualitative analysis, researchers may conduct interviews, surveys, or focus groups that involve the collection of proprietary data. It is crucial to respect the intellectual property rights of the data owners and obtain proper permissions before using or sharing the data. This includes obtaining informed consent from participants and ensuring that any confidential or sensitive information is appropriately protected. 11.3.3 Industry-specific regulations. Certain industries have specific regulations and guidelines that govern the collection, analysis, and use of data. Data analysts working in these industries must be familiar with the industry-specific regulations to ensure compliance and ethical data practices. For example, the healthcare industry is subject to regulations such as the Health Insurance Portability and Accountability Act, HIPAA, in the United States. HIPAA sets standards for the protection of individuals' medical records and other personal health information. Data analysts working with healthcare data must adhere to HIPAA regulations, which include requirements for data security, privacy, and the proper handling of protected health information. Similarly, the financial industry is regulated by laws such as the Gramm-Leach-Bliley Act, GLBA, in the United States. The GLBA requires financial institutions to protect the privacy and security of customers' personal financial information. Data analysts working with financial data must comply with the GLBA and ensure that appropriate safeguards are in place to protect sensitive financial information. Other industries, such as telecommunications, education, and e-commerce, also have their own regulations and guidelines that data analysts must consider when working with data from these sectors. 11.3.4 Ethical Considerations. In addition to legal and regulatory frameworks, data analysts must also consider ethical considerations when conducting quantitative and qualitative analysis. Ethical guidelines provide a framework for responsible and ethical data practices, ensuring that the rights and well-being of individuals are respected. Ethical considerations in data analysis include obtaining informed consent from participants, ensuring data anonymity and confidentiality, minimizing harm to individuals or groups, and being transparent about the purpose and use of the data. Data analysts should also be mindful of potential biases in data collection and analysis and strive for objectivity and fairness. Ethical guidelines, such as those provided by professional organizations like the American Statistical Association (ASA) or the International Statistical Institute (ISI), can help data analysts navigate the ethical challenges that may arise during the analysis process. These guidelines provide principles and best practices for conducting ethical data analysis and promote responsible and accountable use of data. In conclusion, legal and regulatory frameworks play a crucial role in data analysis, ensuring the protection of individuals' rights and privacy. Data analysts must be aware of the data protection laws, intellectual property rights, industry-specific regulations, and ethical considerations that govern their work. By adhering to these frameworks, data analysts can conduct quantitative and qualitative analysis in a responsible and ethical manner, building trust and ensuring the integrity of their findings. 11.4 Ethical decision-making in data analysis. In the field of data analysis, ethical decision-making plays a crucial role in ensuring that data is collected, analyzed, and interpreted in a responsible and unbiased manner. As data analysts, we have a responsibility to consider the ethical implications of our work and make informed decisions that prioritize the well-being and privacy of individuals and communities. 11.4.1 Ethical considerations in quantitative analysis. Quantitative analysis involves the use of numerical data to draw conclusions and make predictions. When conducting quantitative analysis, it is important to consider the following ethical considerations. 11.4.1.1 Informed consent. Obtaining informed consent from individuals whose data is being collected is essential. Researchers must clearly explain the purpose of the study, the types of data that will be collected, and how the data will be used. Participants should have the option to withdraw their consent at any time without facing any negative consequences. 11.4.1.2 Data anonymization and privacy. Protecting the privacy of individuals is of utmost importance in quantitative analysis. Researchers should ensure that data is anonymized and aggregated to prevent the identification of individuals. Personal identifiers such as names, addresses, and social security numbers should be removed or encrypted to minimize the risk of data breaches and unauthorized access. 11.4.1.3 Data security. Data security measures should be implemented to safeguard the data from unauthorized access, loss, or theft. This includes using secure storage systems, encryption techniques, and access controls. Data analysts should also be aware of the legal and regulatory requirements regarding data security and take necessary precautions to comply with them. 11.4.1.4 Bias and fairness. Quantitative analysis should be conducted in a manner that is free from bias and promotes fairness. Researchers should be aware of their own biases and take steps to minimize their impact on the analysis. It is important to ensure that the data collection process is unbiased and representative of the population being studied. Any biases in the data should be acknowledged and addressed during the analysis and interpretation stages. 11.4.2 Ethical considerations in qualitative analysis. Qualitative analysis involves the interpretation and analysis of non-numerical data such as interviews, observations, and textual data. When conducting qualitative analysis, the following ethical considerations should be taken into account. 11.4.2.1 Informed consent. Similar to quantitative analysis, obtaining informed consent from participants is crucial in qualitative analysis. Participants should be fully informed about the purpose of the study, the types of data that will be collected, and how the data will be used. They should also have the option to withdraw their consent at any point during the study. 11.4.2.2 Confidentiality and anonymity. Maintaining the confidentiality and anonymity of participants is essential in qualitative analysis. Researchers should ensure that the identities of participants are protected and that their responses are kept confidential. Any personal identifiers should be removed or anonymized to prevent the identification of individuals. 11.4.2.3 Reflexivity and positionality. Qualitative researchers should be reflexive and aware of their own biases, assumptions, and positionality. It is important to acknowledge and critically reflect on how their own background, experiences, and beliefs may influence the interpretation and analysis of the data. Researchers should strive to be transparent about their own biases and take steps to minimize their impact on the analysis. 11.4.2.4 Respect for participants. Respect for participants is paramount in qualitative analysis. Researchers should treat participants with dignity, respect their autonomy, and ensure that their voices are accurately represented in the analysis. It is important to avoid misrepresentation or distortion of participants' views and experiences. 11.4.3 Ethical decision-making framework. To guide ethical decision-making in data analysis, researchers can adopt a framework that incorporates the following steps. 11.4.3.1 Identify ethical issues. The first step is to identify the ethical issues that may arise during the data analysis process. This involves considering the potential risks and harms to individuals or communities, as well as any legal and regulatory requirements that need to be followed. 11.4.3.2 Gather relevant information. Researchers should gather all relevant information about the data, the research context, and the potential impact of the analysis. This includes understanding the purpose of the study, the data collection methods, and any potential biases or limitations in the data. 11.4.3.3 Evaluate ethical implications. In this step, researchers should evaluate the ethical implications of the data analysis. This involves considering the potential benefits and harms of the analysis, as well as the rights and interests of the individuals or communities involved. 11.4.3.4 Make ethical decisions. Based on the evaluation of ethical implications, researchers should make informed and ethical decisions about how to proceed with the data analysis. This may involve modifying the analysis methods, seeking additional consent, or taking steps to protect the privacy and confidentiality of participants. 11.4.3.5 Monitor and review. Ethical decision-making is an ongoing process. Researchers should continuously monitor and review the ethical implications of their data analysis and make adjustments as necessary. This includes staying updated on relevant ethical guidelines and regulations and seeking input from colleagues or ethics committees when needed. By following an ethical decision-making framework and considering the specific ethical considerations in quantitative and qualitative analysis, data analysts can ensure that their work is conducted in a responsible and ethical manner. This not only protects the rights and privacy of individuals but also enhances the credibility and validity of the data analysis process. 12. Data analysis in practice. 12.1 Case studies. In this section, we will explore several case studies that demonstrate the application of quantitative and qualitative analysis in real-world scenarios. These case studies will provide practical examples of how data analysis techniques can be used to gain insights, make informed decisions, and solve complex problems across various industries and domains. 12.1.1 Customer Satisfaction Analysis. One common application of data analysis is in measuring and improving customer satisfaction. Let's consider a case study of a retail company that wants to understand the factors influencing customer satisfaction and identify areas for improvement. The company collects quantitative data through customer surveys, which include ratings and feedback on various aspects of their shopping experience. By analyzing this data, they can calculate key performance indicators such as overall satisfaction scores, satisfaction with specific products or services, and likelihood to recommend the company to others. Using quantitative analysis techniques, such as measures of central tendency and dispersion, the company can identify areas where customer satisfaction is particularly high or low. They can also segment their customer base to understand if satisfaction levels vary across different demographics or customer segments. To complement the quantitative analysis, the company also conducts qualitative analysis by analyzing open-ended survey responses. By using techniques such as coding and categorizing, they can identify recurring themes and sentiments expressed by customers. This qualitative analysis provides deeper insights into the reasons behind customer satisfaction or dissatisfaction, allowing the company to address specific issues and improve their overall customer experience. 12.1.2 Fraud Detection. Another important application of data analysis is in fraud detection. Let's consider a case study of a financial institution that wants to identify fraudulent transactions and prevent financial losses. The institution collects large volumes of transaction data, including information such as transaction amount, location, and customer details. By applying quantitative analysis techniques, such as anomaly detection and pattern recognition, they can identify unusual or suspicious transactions that deviate from normal patterns. For example, the institution may use statistical models to establish baseline patterns of customer behavior and identify transactions that fall outside these patterns. They can also use machine learning algorithms to detect patterns of fraudulent behavior based on historical data. In addition to quantitative analysis, the institution also conducts qualitative analysis by investigating individual transactions flagged as potentially fraudulent. They may analyze transaction details, customer profiles, and any additional information available to determine the likelihood of fraud. This qualitative analysis helps validate the findings of the quantitative analysis and provides a more comprehensive understanding of potential fraud cases. 12.1.3 Healthcare Outcome Analysis. Data analysis is also widely used in the healthcare industry to improve patient outcomes and optimize healthcare delivery. Let's consider a case study of a hospital that wants to analyze patient data to identify factors influencing treatment outcomes for a specific medical condition. The hospital collects quantitative data on patient demographics, medical history, treatment protocols, and treatment outcomes. By applying quantitative analysis techniques, such as correlation and regression analysis, they can identify factors that are associated with better or worse treatment outcomes. For example, they may find that certain patient characteristics, such as age or comorbidities, are associated with higher treatment success rates. They can also analyze the impact of different treatment protocols on patient outcomes, helping them optimize treatment plans and improve overall patient care. In addition to quantitative analysis, the hospital also conducts qualitative analysis by conducting interviews or focus groups with patients and healthcare providers. This qualitative analysis helps uncover additional insights into the patient experience, treatment challenges, and potential areas for improvement in healthcare delivery. 12.1.4 Market Research Analysis. Market research is another area where data analysis plays a crucial role in understanding consumer behavior and informing business strategies. Let's consider a case study of a consumer goods company that wants to launch a new product in the market. The company collects quantitative data through surveys and sales data, which provide insights into consumer preferences, purchasing behavior, and market trends. By applying quantitative analysis techniques, such as data visualization and statistical analysis, they can identify market segments, understand consumer preferences, and forecast demand for the new product. For example, they may use clustering techniques to group consumers based on their preferences and buying behavior. This helps the company tailor their marketing strategies and product positioning to specific consumer segments. In addition to quantitative analysis, the company also conducts qualitative analysis by conducting focus groups or interviews with potential customers. This qualitative analysis helps uncover deeper insights into consumer motivations, preferences, and unmet needs, which can inform product development and marketing strategies. Conclusion. These case studies highlight the diverse applications of quantitative and qualitative analysis in various industries and domains. Whether it is improving customer satisfaction, detecting fraud, optimizing healthcare outcomes, or conducting market research, data analysis techniques provide valuable insights and inform decision-making processes. By combining quantitative and qualitative analysis, organizations can gain a comprehensive understanding of complex problems and make data-driven decisions to drive success. 12.2 Real-world applications. Data analysis is a crucial component of decision-making processes in various industries and sectors. Both quantitative and qualitative analysis techniques are employed to extract meaningful insights from data and inform strategic actions. In this section, we will explore some real-world applications of data analysis and how organizations leverage these techniques to drive innovation, improve efficiency, and gain a competitive edge. 12.2.1 Market Research and Consumer Behavior Analysis. One of the most common applications of data analysis is in market research and consumer behavior analysis. Companies collect vast amounts of data on consumer preferences, purchasing patterns, and demographics to understand their target audience better. Quantitative analysis techniques, such as regression analysis and hypothesis testing, are used to identify correlations between variables and make predictions about consumer behavior. For example, a retail company may analyze sales data to identify trends and patterns in customer purchasing behavior. By examining factors such as product preferences, price sensitivity, and customer demographics, the company can optimize its marketing strategies, product offerings, and pricing models to meet customer demands effectively. Qualitative analysis techniques, such as focus groups and surveys, are also employed to gather insights into consumer perceptions, opinions, and preferences. These qualitative data provide a deeper understanding of consumer motivations and help organizations develop more targeted marketing campaigns and product innovations. 12.2.2 Healthcare and Medical Research. Data analysis plays a vital role in healthcare and medical research, enabling professionals to make evidence-based decisions and improve patient outcomes. Quantitative analysis techniques are used to analyze large datasets, such as electronic health records, clinical trials, and medical imaging data, to identify trends, patterns, and correlations. For instance, in medical research, statistical analysis is employed to determine the effectiveness of new drugs or treatment methods. Researchers use techniques like t-tests and ANOVA to compare the outcomes of different groups and assess the significance of the results. This information helps medical professionals make informed decisions about patient care and treatment options. Qualitative analysis techniques, such as content analysis of patient interviews or medical records, are also used to gain insights into patient experiences, satisfaction levels, and quality of care. These qualitative data provide a more holistic understanding of patient needs and help healthcare providers improve service delivery and patient outcomes. 12.2.3 Financial Analysis and Risk Management. Data analysis is extensively used in the financial industry to assess risk, make investment decisions, and develop financial models. Quantitative analysis techniques, such as time series analysis and regression analysis, are employed to analyze historical financial data and predict future market trends. For example, investment firms use quantitative analysis to develop trading strategies based on statistical models and algorithms. By analyzing historical market data, they can identify patterns and trends that help them make informed investment decisions and manage risk effectively. Qualitative analysis techniques, such as sentiment analysis of news articles or social media data, are also used in financial analysis. By analyzing qualitative data, financial analysts can gauge market sentiment and investor behavior, which can influence investment decisions and market predictions. 12.2.4 Operations and Supply Chain Management. Data analysis is instrumental in optimizing operations and supply chain management processes. Quantitative analysis techniques, such as statistical process control and optimization models, are used to identify bottlenecks, reduce costs, and improve efficiency. For instance, manufacturing companies use data analysis to monitor production processes, identify defects, and implement quality control measures. By analyzing production data, they can identify areas for improvement, optimize production schedules, and reduce waste. Qualitative analysis techniques, such as interviews and observations, are also employed to gain insights into operational challenges and identify areas for improvement. By understanding the experiences and perspectives of employees and customers, organizations can implement changes that enhance operational efficiency and customer satisfaction. 12.2.5 Social Sciences and Public Policy. Data analysis is widely used in social sciences and public policy research to understand societal trends, evaluate programs, and inform policy decisions. Quantitative analysis techniques, such as survey data analysis and regression analysis, are employed to analyze large datasets and draw conclusions about social phenomena. For example, in education research, data analysis is used to evaluate the effectiveness of educational interventions and programs. Researchers analyze student performance data, demographic information, and survey responses to assess the impact of different educational strategies and policies. Qualitative analysis techniques, such as content analysis of interviews or focus groups, are also used to gain insights into social issues and inform policy decisions. By analyzing qualitative data, policymakers can understand the experiences and perspectives of different stakeholders and develop policies that address societal challenges effectively. Conclusion. Data analysis has become an indispensable tool in various industries and sectors. Whether it is market research, healthcare, finance, operations, or social sciences, organizations rely on quantitative and qualitative analysis techniques to extract valuable insights from data. By leveraging these techniques, organizations can make informed decisions, optimize processes, and drive innovation. As technology continues to advance, the field of data analysis will continue to evolve, offering new opportunities and challenges for organizations seeking to harness the power of data. 12.3 Best Practices in Data Analysis. In the field of data analysis, there are certain best practices that can help ensure accurate and reliable results. These practices apply to both quantitative and qualitative analysis and are essential for researchers and analysts to follow. By adhering to these best practices, analysts can minimize errors, enhance the validity of their findings, and make informed decisions based on the data. In this section, we will discuss some of the key best practices in data analysis. 12.3.1 Clearly define the research question. Before starting any data analysis, it is crucial to clearly define the research question or objective. This helps guide the entire analysis process and ensures that the analysis is focused and relevant. By having a well-defined research question, analysts can determine the appropriate data collection methods, analysis techniques, and interpretation strategies. 12.3.2 Use reliable and valid data. The quality of the data used for analysis greatly impacts the validity and reliability of the results. It is important to use reliable and valid data sources that are relevant to the research question. Primary data collection methods, such as surveys or experiments, should be designed carefully to ensure the accuracy and representativeness of the data. Secondary data sources should be evaluated for their credibility and relevance to the research question. 12.3.3 Clean and prepare the data. Data cleaning and preparation are essential steps in the data analysis process. This involves checking for missing values, outliers, and inconsistencies in the data. Missing values can be imputed or handled appropriately, outliers can be identified and addressed, and inconsistencies can be resolved. By cleaning and preparing the data, analysts can ensure that the data is ready for analysis and minimize the risk of biased or inaccurate results. 12.3.4 Choose appropriate analysis techniques. Selecting the appropriate analysis techniques is crucial for obtaining meaningful insights from the data. Depending on the research question and the type of data, different analysis techniques may be required. For quantitative analysis, techniques such as regression analysis, hypothesis testing, or clustering can be used. For qualitative analysis, techniques such as thematic analysis, content analysis, or grounded theory can be employed. It is important to choose the techniques that are most suitable for the research question and the data at hand. 12.3.5 Validate the results. Validation of the analysis results is an important step to ensure the accuracy and reliability of the findings. This can be done through various means, such as cross-validation, sensitivity analysis, or peer review. By validating the results, analysts can have confidence in the conclusions drawn from the data and can identify any potential errors or biases. 12.3.6 Interpret the results carefully. Interpreting the results of the data analysis requires careful consideration and attention to detail. It is important to avoid making unwarranted assumptions or overgeneralizing the findings. Analysts should critically evaluate the results in the context of the research question and the limitations of the data. They should also consider alternative explanations or interpretations and acknowledge any uncertainties or limitations in the analysis. 12.3.7 Communicate the findings effectively. Effective communication of the analysis findings is essential for the impact and usefulness of the research. Analysts should present the results in a clear, concise, and understandable manner. Visualizations, such as charts, graphs, or infographics, can be used to enhance the presentation of the findings. It is important to tailor the communication to the intended audience and provide sufficient context and explanations to facilitate understanding. 12.3.8 Document the analysis process. Documenting the analysis process is crucial for transparency, reproducibility, and future reference. Analysts should keep a detailed record of the data sources, data cleaning and preparation steps, analysis techniques used, and any assumptions or decisions made during the analysis. This documentation helps ensure the integrity of the analysis and allows others to replicate or build upon the work in the future. 12.3.9 Continuously learn and improve. Data analysis is an iterative process, and there is always room for improvement. Analysts should continuously learn and stay updated with the latest developments in data analysis techniques and tools. They should seek feedback from peers or experts to identify areas for improvement and incorporate new insights into their analysis practices. By embracing a growth mindset and a commitment to continuous learning, analysts can enhance their skills and deliver more robust and impactful data analysis. In conclusion, following best practices in data analysis is essential for obtaining accurate, reliable, and meaningful insights from the data. By clearly defining the research question, using reliable data sources, cleaning and preparing the data, choosing appropriate analysis techniques, validating the results, interpreting the findings carefully, communicating effectively, documenting the analysis process, and continuously learning and improving, analysts can ensure the integrity and validity of their data analysis. These best practices contribute to the overall quality and credibility of the research and enable informed decision-making based on data-driven insights. 12.4 Future trends in data analysis. Data analysis is a rapidly evolving field, driven by advancements in technology, increasing availability of data, and the growing demand for insights to drive decision-making. As we look to the future, several trends are emerging that will shape the way data is analyzed and utilized. In this section, we will explore some of these future trends in data analysis. 12.4.1 Artificial Intelligence and Machine Learning. Artificial intelligence (AI) and machine learning (ML) are revolutionizing the field of data analysis. AI refers to the development of computer systems that can perform tasks that would typically require human intelligence, such as speech recognition, decision-making, and problem-solving. ML, on the other hand, is a subset of AI that focuses on the development of algorithms that can learn from and make predictions or decisions based on data. The integration of AI and ML into data analysis processes allows for more efficient and accurate analysis. These technologies can automate repetitive tasks, identify patterns and trends in large datasets, and make predictions based on historical data. As AI and ML continue to advance, they will play an increasingly important role in data analysis, enabling organizations to gain valuable insights and make data-driven decisions more effectively. 12.4.2 Big Data Analytics. The era of big data has arrived, and organizations are grappling with the challenge of analyzing and extracting insights from vast amounts of data. Big data analytics involves the collection, storage, and analysis of large and complex datasets to uncover patterns, trends, and correlations that can inform decision-making. In the future, big data analytics will continue to evolve, driven by advancements in technology and the increasing availability of data. Organizations will need to invest in scalable infrastructure and advanced analytics tools to handle the volume, velocity, and variety of big data. Additionally, techniques such as distributed computing, parallel processing, and cloud computing will become more prevalent in big data analytics, enabling faster and more efficient analysis. 12.4.3 Predictive and Prescriptive Analytics. While descriptive and diagnostic analytics have been the focus of traditional data analysis, the future will see a shift towards predictive and prescriptive analytics. Predictive analytics involves using historical data and statistical algorithms to make predictions about future events or outcomes. Prescriptive analytics, on the other hand, goes a step further by providing recommendations on the best course of action to achieve a desired outcome. Predictive and prescriptive analytics have the potential to revolutionize decision-making by providing organizations with actionable insights. These techniques can help businesses anticipate customer behavior, optimize operations, and mitigate risks. As data analysis tools and techniques continue to advance, predictive and prescriptive analytics will become more accessible and widely adopted. 12.4.4 Natural Language Processing. Natural language processing (NLP) is a branch of AI that focuses on the interaction between computers and human language. NLP enables computers to understand, interpret, and generate human language, allowing for more effective communication and analysis of textual data. In the future, NLP will play a crucial role in data analysis, particularly in the analysis of unstructured data such as social media posts, customer reviews, and news articles. NLP techniques can extract valuable insights from textual data, such as sentiment analysis, topic modeling, and entity recognition. As NLP continues to advance, it will become an essential tool for analyzing and understanding the vast amount of textual data generated every day. 12.4.5 Data Visualization and Storytelling. Data visualization is an essential component of data analysis, as it enables the effective communication of insights and findings. In the future, data visualization techniques will continue to evolve, driven by advancements in technology and the increasing complexity of data. Interactive and immersive visualizations will become more prevalent, allowing users to explore data in a more engaging and intuitive way. Virtual reality (VR) and augmented reality (AR) technologies will enable users to visualize and interact with data in three-dimensional space, providing a more immersive and impactful experience. Additionally, storytelling will become an integral part of data analysis, as analysts strive to communicate insights in a compelling and meaningful way. Data storytelling involves using narratives, visuals, and interactive elements to convey the story behind the data, making it easier for stakeholders to understand and act upon the insights. 12.4.6 Ethical Considerations in Data Analysis. As data analysis becomes more pervasive and powerful, ethical considerations will become increasingly important. Organizations will need to ensure that data analysis is conducted in a responsible and ethical manner, respecting privacy, confidentiality, and data protection regulations. In the future, there will be a greater emphasis on transparency and accountability in data analysis. Organizations will need to establish clear guidelines and frameworks for ethical data analysis, including the responsible use of AI and ML algorithms, the protection of personal data, and the mitigation of biases and discrimination in data analysis. 12.4.7 Data Governance and Data Quality. With the increasing volume and complexity of data, data governance and data quality will become critical factors in data analysis. Data governance involves the management and oversight of data assets, ensuring that data is accurate, reliable, and secure. Data quality, on the other hand, refers to the fitness for use of data, including its accuracy, completeness, and consistency. In the future, organizations will need to invest in robust data governance frameworks and data quality management processes to ensure the integrity and reliability of their data. This will involve implementing data quality controls, establishing data governance policies and procedures, and leveraging technologies such as data profiling and data cleansing tools. 12.4.8 Privacy-Preserving Data Analysis. As concerns about data privacy and security continue to grow, privacy-preserving data analysis techniques will become more important. These techniques allow for the analysis of sensitive data while preserving the privacy and confidentiality of individuals. In the future, organizations will need to adopt privacy-preserving data analysis techniques, such as differential privacy, secure multi-party computation, and homomorphic encryption. These techniques enable data analysis to be conducted without exposing sensitive information, ensuring compliance with privacy regulations and building trust with customers and stakeholders. 12.4.9 Collaboration and democratization of data analysis. In the future, data analysis will become more collaborative and accessible to a wider range of users. Collaboration tools and platforms will enable teams to work together on data analysis projects, facilitating knowledge sharing and fostering innovation. Additionally, the democratization of data analysis will empower non-technical users to perform basic data analysis tasks. User-friendly data analysis tools and intuitive interfaces will make it easier for individuals without a background in data analysis to explore and analyze data, democratizing access to insights and enabling data-driven decision-making at all levels of an organization. 12.4.10 Continuous learning and adaptability. As data analysis continues to evolve, professionals in the field will need to embrace continuous learning and adaptability. The rapid pace of technological advancements and the ever-changing data landscape require data analysts to stay updated with the latest tools, techniques, and best practices. In the future, data analysts will need to invest in ongoing professional development, attending training programs, participating in online courses, and engaging in communities of practice. Continuous learning will enable data analysts to stay ahead of the curve, adapt to new technologies and methodologies, and deliver valuable insights to drive organizational success. In conclusion, the future of data analysis is exciting and full of possibilities. Advancements in AI, ML, big data analytics, NLP, data visualization, and ethical considerations will shape the way data is analyzed and utilized. As organizations embrace these future trends, they will be better equipped to harness the power of data and make informed decisions that drive success.